Hey guys, are you all able to hear me well? Are you all able to see me well? Are you all able to see my PPT well? Yes, can I get some fire in the chat box if everything is audible and clearly visible? Good morning, good morning, good morning everybody. Good morning everybody. Just give me a minute. I'm just adjusting your chat over here so that I can see your chats. Okay. Yes. Good morning, good morning, good morning, good morning people. Yes. Yes, very good, very good, very good. I can see a lot of fires in the chat. Very good. Okay, we'll just wait a minute for your friends to join. Okay, you can say the part 2 has started. Yes, complete class 11th part 2 has started over here, and we are going to complete in a very in a very magical way, I would say. Okay, yes, thank you. Oh yes, no problem, Ruhi, no problem, no problem. Okay, after this class please conduct a class on only important topics. Okay, you can ask Yavar sir for it. Okay, so yeah, no issues, no issues, no issues. Okay people, okay people, so how are you all doing? How are you all doing, and how is the preparation going, people? Yes, how is the preparation going? And I would be very honest, so I would be very honest. I was supposed to take this marathon yesterday, but as soon as I woke up, I don't know what happened. I guess some case of food poisoning or something. I vomited 4 to 5 times, and that is the reason I was not able to take the class. I'm still on medicines. Okay, I'm still on medicines right now. So let's see. Okay, let's see how it goes. Okay, people. Nothing happened to Yavar sir Ramen. Yeah, nothing happened. Okay. Okay. Okay, question practice. Yeah, we'll do ample of question practice. Okay, and in this slides, okay, yes, I will give an introduction of myself, and in this slide, if you all see, I have more than 500 slides over here. So you don't fear, my God, what is he about to teach in 500 slides? Because most of them are questions actually, and I want you all to practice them at home also. That is the reason I've given them. You will receive this PPT on your Telegram as well, so you can download it and you do the practice as well. Yes, I will teach from basics. Yes, now I'm okay. I'm okay. Okay, so I'll just give my introduction right now. Okay, so my name is Jonathan. Okay, you can all call me John sir. Okay, that's what my students call me. They call me John sir. Yes, I will say everything. So my name is Jonathan. My students call me John sir. Okay, you can also call me John sir. And today we are going to cover thermal physics, which consists of thermal properties of matter, heat transfer, KTG, thermodynamics. Then we are going to move on to elasticity, that is mechanical properties of solids, then fluid mechanics, and then we are going to cover SHM and then waves. So that is going to be our flow for today. Okay, that is going to be our flow for today. Okay, people, I want you all to like this session. Okay, good morning, good morning, good morning, good morning. Okay, yes. So what will be the duration? So we'll start at 9, and I'll try to keep it as short as possible because I don't want you all to just cram up all the theory. I want you all to understand everything. Okay, and okay. Sir, no, it's not going to be a 12-hour class. That is something which I'll promise. Okay, before that, people, I just want you all to understand one thing. Before I take the class, there is one word I want you all to understand. Okay, and that is chamka. Okay, now what is chamka, people? Okay, yes, yeah, I'm starting the class. What is chamka, people? Chamka, how many? I don't know how many of you all know Hindi over here, but in Hindi, chamka means dimag ki batti jalna. Okay, so there is a tube light inside your head, and if you understand a thing, then you have to say chamka in the chat box. If you do not understand a thing, then you have to say no chamka in the chat box. Okay, people. So that is going to be the drill that we are going to follow. Okay, so chamka. Okay, people. As usual, chamka. Okay, people. So that's it. And also one more thing. That I am from Kerala. Okay, I'm in Kerala. I'm from Kerala, so I know a little bit of Malayalam also. So ellarum ivide sugamano, pinne vanakkam. And let's start with the one shot. Okay, let's start with the one shot. Okay, people. So can I get some fire in the chat box? Can I get some fire in the chat box? And then we'll start the session. Okay, then we'll start the session. Okay. 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 Yeah, I can understand a little bit of Tamil. Okay, chalo, let's start. Let's start with complete class 11th physics part 2, and let's go. Okay, so the first chapter that we're going to start is thermal properties of matter. Okay, so I've covered the entire one shot. I have covered the entire one shot with all of the self-written notes. Okay, you're gonna get this self-written notes in your Telegram as well. Okay, I've already discussed about all the chapters that I'm going to cover. Okay, so right now let's start with basics. Okay, thermal properties of matter. So what we know matter. So matter is something which occupies space and volume. That is something which we are very sure of. Now we are going to study about the properties of matter. But which properties of matter? We are going to study about those properties which are respectively with respect to thermal properties. Okay, are you able to understand this? Now, for understanding thermal properties, we need to understand what is temperature actually. Now, if I go back to layman's language, okay, so temperature is basically the degree of hotness or coldness of a body. That is exactly what the NCERT also says over here. No, so if I say that this is cold, this is cold water. But if I say this over here, this is hot water, or I can say that this is much more hot than this. Yes, J students can also listen to this class. So this water is much more cold than this. So this hot water is much more hot than this. So this is just a degree. Now this degree is not able to give me a perfect value of the temperature. That is the reason we have invented thermometers over here, by which we can basically calculate the temperature. Am I clear over here? Is this chamka for you all? Okay. Now, in your syllabus, there is Celsius scale. Okay, there is Celsius scale. Just a second, people. Okay, there is Celsius scale, there is Kelvin scale, and there is Fahrenheit scale. Now one thing, okay, one thing that I want you all to understand this, I will be targeting your NEET exams specifically. Okay, I'll not be wandering around those topics which are not frequently asked in your NEET exams, but I will be covering everything. Okay, so this is one thing that you're gonna get in your NEET exams. So one thing that you have to keep in mind is that whenever you want to form a relationship between your between your Celsius scale, Kelvin scale, Fahrenheit scale, or any X scale, there are basically three parameters which are required. What are those three parameters? The first parameter is basically the ice point. Okay, the ice point. So basically the temperature at which your water turns into ice, that is basically ice point. And then steam point. And then that is steam point, or 100 degrees Celsius in your Celsius scale. And the third parameter which is required is basically the number of units between the steam point and the ice point. Are you all able to understand this, people? Is this chamka? Is this chamka for you all? Everybody? Yes or no? Yes or no? Okay. Now how do we find out the difference between these two? It's very easy. Just subtract the steam point and the ice point, and whatever answer you get is basically the number of divisions between the ice point and the steam point. That is exactly what we're doing. Now in Kelvin scale, what is the ice point? The ice point is 273 degree Kelvin. The Kelvin and the steam point is 373 Kelvin. What is the difference? Good morning, Pari. Okay, so chamka means, for all those who have joined now, chamka means you have understood the concept. Okay, that is a word in Hindi. Okay, so 273 Kelvin is the ice point, 373 Kelvin is the boiling point. Okay, so what are the number of divisions between them? Again, 373 minus 273, you will get 100 units. So that is for Kelvin scale. Coming back to Fahrenheit scale, again the ice point is 32 degree Fahrenheit, the boiling point is 212 degree Fahrenheit, and the difference between them, this thing is a very important thing that you have to note, is that the difference is 180 units. It is not 100 units, it is 180 units. Okay, I hope so you have all understood this thing very carefully. Okay, people, I'm okay, I'm doing okay. I'll not say that I'm doing absolutely well, but I'm doing okay. Okay, manageable. Now, this is a very important thing which comes in your exam. Okay, this is a very important thing which comes in your exam. I want you all to like the session, people. Okay, now in your exams, they'll ask you to convert from Celsius to Fahrenheit, from Fahrenheit to Kelvin, from Celsius to Fahrenheit, or from Celsius to some random scale. Okay, from Celsius or to some random scale. Are you all able to understand this, people? Now, how to do that? It's a very simple formula. It's a very, very, very simple formula. What is the formula, sir? The formula is the temperature in that scale, that is Celsius, minus the ice point, okay, divided by the number of divisions, or divided by boiling point minus ice point. That's it. Is this clear? Is this clear? Is this clear? Okay. So in Kelvin, what is this Kelvin? Kelvin, minus the ice point. What is the ice point in Kelvin? That is 273. So Kelvin minus 273. Hello Luna, divided by 100. Now how did I get this 100? It is basically 373 minus 273, that is 100. Now with respect to Fahrenheit scale, this is Fahrenheit scale. What is the ice point? That is 32 degree Fahrenheit. F minus 32 divided by 212 minus 32, that is 180. Did you all understood this? Yes, this is a very important relation. Now, if they ask you some random scale, so basically that is going to be the temperature in that scale minus the lower limit, which is basically the ice point, divided by the difference between the boiling point and the ice point. Is this a very clear? Chamka, yes or no? Yes, Chamka, yes or no? Okay, so I'll just solve a question over here. So that you can basically understand what I'm basically saying over here. Yeah, so this is the question. Yeah, this is the question over here. Please solve it before I do. Okay, please solve it before I do. This is the question for you all. Okay, let's solve it. What does it say? On a new scale of temperature which is linear and called the W scale, the freezing point and the boiling point of water are so and so. Okay, 39 and 239 respectively. Okay, what will be the temperature on the new scale corresponding to a temperature of 39 degrees Celsius on the Celsius scale? Okay, so let us basically use that trick which we have just learned right now. Okay, so let's do this. So they basically want us to do the relationship between Celsius scale and a new random W scale. No problem. So we know Celsius scale minus 0, because that is basically the ice point, okay, divided by 100, that is boiling point minus the ice point, which is equal to W minus 39, because 39 is the freezing point. So this is 39 and divided by 239 minus 39. Is this clear, people? Is this clear, people? I want the answers in the chat box. Okay, so so they need what will be the temperature on the new scale corresponding to a temperature of 39 degrees Celsius. They substitute 39 over here. Good morning Gopinath. So this is basically 39 divided by 100, which is equal to W minus 39, and this becomes 200. So this is 1s are, this is 2s are, this goes over here. So this is 39 into 2 is equal to W minus 39, and everybody should get W is equal to, yes, that is 117 over here. Yes, 117 over here. Okay, D, everybody is getting D. Very good people, very good. That's how it should go. Okay, just a second, people, let me just drink water. Very good people. Yes, so okay, yeah, this is also that we can do. Okay, no, this is not something which I have covered. Let's move back to the theory. Okay, now, very important, people, very important over here. That is, now we have to understand the conversions actually. Okay, now see, it's very easy to convert from Celsius to Kelvin. We have just learned how to do that, but there are some formula that you need to keep in mind. Okay, because again, a NEET is again a very speed and accuracy intensive exam. Okay, so that is the reason you need to remember a few things. So the first formula that you need to remember is Kelvin is equal to Celsius plus 273. So if you have a temperature in Celsius scale, you just need to add 273 to it to get the Kelvin reading. That is it. Okay, the second formula is basically the relationship between Celsius and Fahrenheit scale. Okay, the relationship is between the Celsius and the Fahrenheit scale. It is basically C is equal to 5 by 9 F minus 32. Now many of you all will be thinking, from where did I get this? Simple, people, I just solved this equation. This C divided by 100 is equal to F minus 32 divided by 180. I'll exactly get this relation. Am I clear? Is this Chamka? People? Yes or no? Is this Chamka? Yes or no? Okay, so this is basically, now what is absolute zero, people? Absolute zero is that, okay, I thought Jonathan, okay, so absolute zero. What is absolute zero? Absolute zero is basically at that temperature in which molecular motion stops. So basically, if I have a gas over here, so this gas molecules are moving randomly. Exactly, they are moving randomly. They are performing Brownian motion actually. Hai na? They are moving randomly. You do not know wherever they are going. So basically, they are moving randomly. But Absolute zero is basically at that temperature where the molecular motion stops, where the molecules of the gas are not moving at all. That is basically absolute zero. Now, what the temperature with respect to Kelvin is a 0 Kelvin. With respect to Celsius is minus 273. Now, this is an approximate value. It should be minus 273.15. And Fahrenheit, it is minus 460 degree Fahrenheit. Is this clear, people? Is this clear, people? Yes or no? Yes or no? Chamka. Yes, that is exactly what I want to understand. Okay, because see, I'm going to cover entirety. Okay, I'm going to cover each and every point. Okay, I'm going to cover each and every point. Now this is one question which you will get. Sir, it is C is equal to, no, people. No. Okay. No, I'm not from Tamil Nadu. I'm not from Tamil Nadu. Okay, I'm not from Tamil Nadu. Repeat absolute zero. See, basically, what is absolute zero? Absolute zero is that temperature. Absolute zero is that temperature in which the molecular motion stops. So basically, you have gas molecules moving here randomly, but if you have temperature as 0 Kelvin or minus 273 degrees Celsius or minus 460 degree Fahrenheit, the molecular motion stops. Okay. Okay, people. Yeah. So now this is something which you can get as a theoretical question also. In your NEET exam, they will basically ask at what temperature basically the Celsius scale and the Fahrenheit equalize. Hai na ji? So this is the formula. This is the formula, people. Okay, this is the formula. So I just substituted C with X and F with X because both of them have the same numerical value. So X is equal to 5 by 9, X minus 32. That's it. Okay. Okay. Yes, understood, people. Understood, people. So I just substituted C with X, F with X, and that's it. You just solve this equation over here and you'll get X is equal to minus 40 degrees. So minus 40 degrees, is that numerical value in which you get degree Celsius and Fahrenheit as equalized. Okay, people. Now a very important thing. Over here. Now, people, if you'll notice over here, in the Celsius scale, there are 100 units in between. Okay. In Kelvin scale, there are 100 units in between. In Fahrenheit scale, there are 180 units in between. Now, why is this very important? I'll say why is this very important. That is basically because the difference between the steam point and the ice point is the difference between the ice point and the steam point in the Celsius scale and the Kelvin scale is the same. That means the change, whatever change you do in the Celsius scale, that same change will be reflected in the Kelvin scale because the number of divisions is both the same is same in both the cases. Are you all able to understand this? I'll repeat again. That is, the change that is reflected in the Celsius scale is the same change which is reflected in the Kelvin scale as well. Okay. Okay. Are you all able to understand this? Okay. Just a second, people. Yes. So see, many of you all have this confusion over here. Just a second, people. Okay. See this. Many of you all have this confusion over here. I'll just solve this. Okay, people. So this is basically C by 100. This is basically C by 100, which is equal to F minus 32. F minus 32 divided by 180. Okay. So this is 0. This is 0. This 0 gets cancelled. So what I'm getting over here, C is equal to 10 divided by 18, and this is F minus 32. And this becomes C is equal to, this is 2 5s are. Yes, this is 2 5s are. And this is 2 9s are, and this is F minus 32. Yes, this is exactly the formula that I've written. Yes, this is exactly the formula that I've written. C is equal to F 5 by 9 F minus 32. That is exactly the formula I've written. Now, whoever is saying that the formula is wrong, you must have learned this formula with respect to Fahrenheit scale. Yes, yes. So in Fahrenheit scale, it will be basically F is equal to 9 by 5. So, okay, 9 by 5 times of C plus 32. Yeah, something like this. Yes or no? Something like this you must have learned. Okay. Now, what do you want? Yes. Okay, people. So, that is basically what I want to say. So, yeah. So, the change in temperature. The change in temperature is something which we are looking over here. Okay. So, change in temperature. Okay. Now, this is very easy to understand actually. This is very, very easy to understand actually. See this. Now, I know that the formula is C is equal to, that is K is equal to C plus 273. This is one formula that I know. Okay. If I want to convert from Celsius to Kelvin, I just need to add 273 and then it will get converted. Now, I'm just going to use basic mathematics over here. So, if I differentiate, okay, what I get the change in Kelvin is equal to the change in Celsius, 273 being a constant, that becomes 0. So what do I get over here? That the change in Kelvin is equal to the change in degree Celsius. The same change, people. So a 2 degree rise in Kelvin is equal to a 2 degree rise in Celsius. So basically a 2 degree decrease in Kelvin is going to be a 2 degree decrease in Celsius. That's it. Are you all able to understand this, people? Are you all able to understand this? Yes or no? Now, with respect to this formula as well. Okay, this formula, that is Celsius, just a second. That is Celsius is equal to 5/9 times of F minus 32. F minus 32. If I want to understand the formula, how did it came? It's very easy. So basically, I'm gonna multiply this 5/9 under. So this becomes 5/9 F, and this becomes minus of 5/9 times of 32. Now just differentiate on both the sides. I'll get this is delta C is equal to 5/9 times of delta F, and this whole thing becomes 0 because it's a constant. So this is what I get. Are you all able to understand this? How is this formula coming over here? I want you all to like the session, people. I all want you all to like the session. Okay, people. So this is what you're getting. A very, 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 very important formula when it comes to your NEET exams. That is delta C is equal to delta K, and delta C is equal to 5/9 times of delta F. Is this clear? Yes, chamka. Okay, let's move ahead. Okay. Now we're going to understand thermal expansion. Okay. Now before that, we can basically all solve a numerical over here, so that you can all practice also. Okay, practice. Okay, yeah, this is the form. Yeah, this is the question. A centigrade and a Fahrenheit thermometer, okay, are dipped in boiling water. The water temperature is lowered until the Fahrenheit thermometer registers 140 degrees. Sorry, the fall in temperature as registered by the centigrade thermometer will be, okay. So basically, what do I have two temperature scales. I have a Celsius scale. Sorry, I have a Celsius scale and a Fahrenheit scale. Both of them are dipped in boiling water. Okay, the water temperature is lowered until the Fahrenheit thermometer registers 140 degrees. Okay, the fall in temperature as registered by the centigrade thermometer will be how much? That is exactly what I want to find out. This is an AIMS question. It has come in your AIMS exam. I just decrease the brightness so that it will be much more clear. Okay, yes. Okay, so let's solve this. People. So see this. Sorry, where is it? Just a second, people. Yes. So see this. In your Fahrenheit scale, it is 212 degree. Fahrenheit. A very important thing. 212 degree Fahrenheit. Okay, 212 degree Fahrenheit is your boiling point. Where is it? Okay. Yes. So basically, you have a Celsius thermometer. So earlier it was at 100 degrees Celsius. You have a Fahrenheit thermometer. It was at 212 degree Fahrenheit. Now, what did I said? That the water temperature is lowered until the Fahrenheit thermometer registers 140 degrees. Okay. So basically, the final temperature gets converted into 140 degree Fahrenheit. So basically, what is the delta F over here? Delta F is basically going to be 212 minus 140. 212 minus 140. Is this clear? People? Yes or no? It's going to be 212 minus 140. Yes. Okay, so this comes out to be 72 degrees. Now we have already learned that the change in degree centigrade is equal to 5/9 times of delta F. Just substitute this fellow over here. What do you get? That is delta C is equal to 5/9 of 72, and this becomes 9 ones are, this is 8, and this is 40 for y'all. Are you all able to understand this, people? That means the fall in temperature as registered by the centigrade thermometer is going to be 40 degrees Celsius. not 60 degrees. People, again, in the question, they did not ask you what is the temperature of degree Celsius. No. They did, what have they asked? The fall in temperature as registered. They have asked you delta C over here. They have not asked you to calculate the exact temperature of centigrade. Are you all able to understand? Now, if they ask you what is the new temperature of centigrade scale, it's going to be 100 minus 40, that is going to be 60 degrees Celsius. That is going to be 60 degrees Celsius. Clear? Chamka? Yes. Okay. Very good. Very good. Now we are going to move ahead to thermal expansion. Okay, so before we do thermal expansion, I just want you all to solve this question. Okay, I'm so sorry if you're not able to see this option D. Okay, yeah, I'm so sorry if you're not able to see this option D. What jumka? It's not jumka, it's called chamka. Okay, it's called chamka. So basically, if you understand the concept, you just have to type chamka. Okay, so two holes of unequal diameters D1 and D2, where D1 is greater than D2, are cut in a metal sheet. If the sheet is heated, what is going to take place? Both D1, D2 increases, both D1, D2 will decrease, D1 will increase, D2 will decrease, D1 will decrease and D2 will increase. That is exactly the options that you have. Now, when it comes to your thermal expansion, okay, the only thing that you have to keep in mind is that you just take 2 points, and increase the length. That's it, and increase the length. Okay, so I'm just going to repeat what all chapters I'm going to take: complete thermal physics, solid mechanics, fluid mechanics, SHM and waves. That is exactly what I'm going to do. Okay. Okay, so basically, if you all notice over here, if I take these 2 points, this is the 2 points, and if I'm going to take these 2 points as well, when you're going to heat it, the distance between these 2 points is going to increase for sure. For sure, it's going to increase. Are you all able to understand? Yes, no matter any situation, it's going to increase. Are you all able to understand this? So basically, these 2 points, the distance between them is going to increase. These 2 points, the distance between them is going to increase. You do not have to use any other logic. So the answer is going to be both D1 and D2 will increase. Okay. Okay, are you all able to understand this? So now we are gonna go back to the theory. Where is the theory? Okay, so thermal expansion. Okay, chalo, let's learn about thermal expansion. So what is it? So we are gonna talk about thermal expansion with respect to solids first. So this is the key point that you have to keep in mind. Okay, so distance between any 2 points on a solid increases with increase in temperature. That is exactly what I was going to say. That is exactly what I was saying. Hai na? So you just take 2 points, just increase the distance between them, and that is your thermal expansion. Okay, so basically, if you have a rod over here, and if you have taken 2 random points A and B, and the distance between the 2 random points is X over here, if you heat it, this delta sign is basically the heat thing. If you heat it, the distance between A and B is going to increase, and finally it's going to be X plus delta X. Now, how much is this going to be? How much this delta X is going to be? That is something which we're going to look in the future. Okay. Yes. Clear. Okay. Very good. So let's solve one more question. Where is the question? Question. So I have a lot of questions and it's very difficult to find out. Okay, yeah, this is the question. Okay, this is the question, people. It's a very, very easy question. Very, very easy question to start with. A solid ball of metal has, okay, yes, a solid ball of metal has a concentric spherical cavity within it. If the ball is heated, the volume of the cavity will what? Okay, will what? What is going to happen? What is going to happen to the volume of the cavity? That is something that we have to notice. So basically, we have a solid ball. Inside there is a cavity. Okay, and that cavity is also going to be spherical cavity. That spherical cavity is going to have some radius. So this is the radius. Okay, this is the radius. When you heat it, the radius is going to increase, and if the radius increases, the volume is going to increase. Exactly. Increase. That is your answer. Okay. Okay, cool. Very good, people. Okay, now let's move ahead. Okay, now we are going to study linear expansion. Now we are going to study linear expansion. Okay, now there are some assumptions that we are going to do with respect to linear expansion. Okay, the linear expansion, the first assumption is that whatever material that you're going to take, or whatever thing that you're going to take, it basically only has one dimension. It basically has only one dimension. Are you all able to understand this? So it has only length. It does not have any breadth. Okay, it does not have any breadth. So if it does have breadth, then we're going to study it in areal expansion. Okay, people. Okay, let's understand. So we have a rod over here. I've considered the initial length as to be L0. That is the initial length. So the initial length is L0 over here. I've heated it, and due to that there is a change in temperature, that is delta T. Okay, so it was at some temperature T initial. Because of heating, it becomes T final. So there is some change in temperature, that is delta T. And because of this heating, it has expanded. So basically I'm going to say that the final temperature is L. How much it has expanded? It has expanded by delta L. Are you all able to understand this? The initial length was L0. The final length is right now L0 plus delta L, because it has expanded by delta L. So this L0 plus delta is equal to L. Yes, you can get the notes in the Telegram. I'll ask Yavar sir to send these notes. Okay, so don't worry about that. Okay, cool people, clear. Is this chamka? Yes, is the chamka for you all people? Okay, chalo, let's move ahead. Now the relation that you get over here is delta L is equal to L0 alpha delta T. That is basically the relationship that you get over here. That is the change in length, or how much it has expanded. That is the change in length is equal to L0, that is the initial length, alpha, coefficient of linear expansion, delta T, that is the change in temperature. A very important formula. I hope so you have all understood this. Now, when it comes to your alpha, that is coefficient of linear expansion, a very important thing that you have to basically keep in your mind. Now, if I talk with practical purposes, if I talk with practical purposes, alpha is actually temperature dependent. I am going to prove it to you. But in your exams, you are going to consider alpha as a constant. Am I clear? So in reality, it is temperature dependent. But for your exams, you are going to consider it as a constant. Okay. And now, coming back. So this is your original length. This is your final length. So the final length is delta L time. So delta L more than the final length, than the initial length. Yes. Now, can I basically write this equation that L is equal to L0 plus delta L? That is, L is equal to L0 plus delta L. You will be like, Haji. Yes. Now I'm just going to substitute the value of delta L over here. That is L0 alpha delta T. When I substitute over here, I'll get L is equal to L0 plus L0 alpha delta T. I'll take L0 common, and I'll get a very important relation. Okay. That is L is equal to L0 1 plus alpha delta T. This is basically a very important relation that you get over here. Okay, people. Now see this. Okay, the very important thing. Now I'm just gonna take the value of alpha from this equation. What is the value of alpha that you get from this equation? Now basically the L0 goes over here, delta T goes over here. So alpha is equal to delta L divided by L0 alpha, delta L divided by L0 delta T. That is something which you're gonna get. So with respect to units, this delta L and this L0 gets cancelled out. What is the only thing that remains? That is delta T. Delta T is basically T inverse minus 1, or T inverse. So in this formula, you are able to understand that alpha is temperature dependent. But as I said, practically temperature is dependent. For your exams, you are going to take alpha as a constant. Are you all able to understand this? Okay. Chamka, yes or no? Okay, so I have basically explained you everything about linear expansion. Now this same thing applies for your areal expansion as well as your volumic or cubical expansion. Okay. So that time I'm not gonna waste my time over there. Okay. Now a very important graph that may come in your NEET exam. The graph is basically between L versus delta T. L versus delta T, that is the final length and the change in temperature, delta T. How are we going to draw this graph? We all know that the final length is basically equal to the initial length base plus the change in length. Yes. Then you can basically substitute the value of delta L as L naught alpha delta T. You will be like, Hanji, you can do that. Now just compare this equation. So this becomes Y, this becomes the constant C, this X becomes, the delta T becomes X, and the slope becomes alpha dot alpha into L naught. That is exactly what we are getting. Okay, Samina, what do you want me to repeat? Just अच्छा वो box वाला. Okay, box बता देंगे. Okay, so this is the graph that we are getting. Y is equal to mx plus c. So basically we have a slope m and an intercept also. What is the intercept, people? Y intercept is basically L naught. So it's gonna cut the y axis at L naught. So this is basically a straight linear graph that we're gonna get. Okay, people. Okay, what is the theta, people? What is the theta or the slope? Slope is basically m is equal to tan theta. That comes out to be alpha into L naught. Is this graph clear? Is this graph clear? Yes. Yes. Anyone from Kerala? I am from Kerala. Okay. So this box is basically, what I'm saying is, what is the units of alpha? What are the units of alpha? The units of alpha is going to be T inverse, Kelvin inverse, or Celsius inverse. Depends upon which unit you're going to play. Okay. It depends on which unit you're going to play with. Okay. I hope so. I'm very much clear. I hope so. I'm very much clear over here. Now let's understand a bimetallic strip. Bimetallic strip. Now from the name only you are able to understand that bimetallic. Bi means two metal, that is two metals, and a strip made up of two metals, which is called as bimetallic. Okay, a strip which is made up of two metals is called a bimetallic strip. Okay. Now, so I basically shown you two different metals over here with two different colors. Okay, now what I have done over here, this is the first metal, this is the first metal. Yes, this is the second metal. Okay, originally they had the same original length, that is L naught. Initially they had the same original length, that is L naught, and I have pivoted them at these 2 points. Now what do I mean by pivoted them? So pivoted them is basically so let me just okay, yeah, okay. So see this, pivot is basically, this is your first rod, this is your second rod. I'm gonna basically fix the ends basically together. So this is pivoted over here and this is pivoted over here. Are you all able to understand this, people? I'm going to pivot it over here, I'm going to fix this over here, and I'm going to fix this over here. Now this is a very crucial thing when it comes to your bimetallic strip. Am I clear? Okay, so I've fixed this point over here and I've fixed this point over here. That is exactly what I've done. Okay, then what I do, then basically I heat this. Now a very important thing when it comes to your alpha, is basically, if you all notice over here, the delta L is directly proportional to alpha. Delta L is directly proportional to alpha. That means more the alpha, more the expansion. Are you all able to get this? More the value of alpha, more the value of delta L. So that means if I have two metals, obviously these two metals are going to have some values of alpha. You will be like, yes sir. You will be like, yes sir. Now if I am basically saying the value of alpha 1 is greater than alpha 2, so this pink metal has alpha 1 and this green metal has alpha 2 as its values. Are you able to understand this? Now if I heat this, it is very much obvious, due to the first metal having a higher linear coefficient, it is going to expand more. It is going to be, yes, more the value of alpha, more the expansion. Yes, so it's going to expand more, but as it is pivoted, it cannot expand. That is the reason it bends. Are you all able to understand this? So this pink metal wants to expand more, but this green metal does not allow it to expand more, because the green metal has a lower level of coefficient of linear expansion. Are you able to understand this? So this cannot grow. So it bends. Are you able to understand this? People? Okay. Now this L1 is equal to R1 theta. That is not something which you have to keep in mind. Okay. The only thing that you keep in mind is basically this. Okay, people. Yes. Chamka. Good morning, Simi. Okay, people. Yes. Okay. So just a second. Okay, just a second. Okay, so what is going to happen over here? What is going to happen over here, people? The question says a bimetallic strip is made up of aluminium and steel where the coefficient of linear expansion of aluminium is greater. Good morning, Savitha. Is greater than steel. On heating, the strip will, what will happen? The strip will, what will happen? That is your question. It will get twisted. I don't think so. It will not get twisted. That is wrong. Remain straight. No. Now the confusion arises between these two. Okay, that is will bend with aluminium on the concave side, will bend with steel on the concave side. Okay, so that is something which we're gonna understand over here. Okay, I need the answers in the chat. I need the answers in the chat, people. Okay, I need the answers. So aluminium is greater than steel. So I have aluminium over here. This is aluminium. Okay, and this is steel over here. Okay, I'm going to heat it, so it's going to pivot. It's at a pivoted point. So we all know it's going to bend something like this. Okay, it's going to bend something like this. Okay, so this is aluminium and this is steel for you all. And so right now, will bend with aluminium on the concave side. Oh ho ho. Will bend with steel on the concave side. So what is concave, people? The cave. This is cave, no? This is cave. So steel is on the concave side. Steel is on the concave side. So option D is your right answer. Option D is your right answer. Okay. Okay, people. Is this clear? Is this clear, people? Yes or no? Yes or no, people? Yes. Oh, okay. Clear. That is the reason I took this question. Because many of you all, they do not understand the meaning of concave side. This is your cave, right? This is your cave. Yes, sir. Done. Very good. Next question. Two metal strips that constitute a bimetallic strip must necessarily differ in their what? They should differ in their length, their mass, coefficient of linear expansion, or resistivity. That is exactly what is. Yes. That is exactly what they've asked. Okay. So you have two strips. So a bimetallic strip is there. What exactly they should differ in? That is your question. Okay. Yes. Okay. I've got the answers in the chat, people. So length again does not matter. Okay. Length again does not matter. Mass again does not matter. What is resistivity? Nah. So the only option is C, that is coefficient of linear expansion, because both of them should have different values of linear expansion. Otherwise, why would they bend? Why would they bend? They would have the same delta L. Then why would they bend? Ji. Chalo ji. Very good. Very good. Let's move ahead. Okay. Let's move ahead. Okay, people. People, are you all able to understand the class? Are you all able to understand the class? Yes. Are you all able to understand the class? Okay. Very good. Let's move ahead. Yes. Okay. Now we're going to understand the time period of a pendulum. Okay. Now we're going to understand the time period of the pendulum. So people, we all know the formula of time period of pendulum. We all know that the formula of time period of pendulum is basically T is equal to 2 pi square root of L by G. Yes. So now it is very much clear that the time period itself is dependent upon the length of the pendulum. Okay. Now we all know that the length itself can get changed due to the temperature difference. Now, this is the pendulum, it has a length of, the string has the length as L, and it's oscillating. Now, it's very much clear, if you heat it, the temperature is going to increase, and because of this increase, the string is going to expand, and because of that expansion, the length is going to increase. Now, if the length is going to increase, obviously, as time period and the length are directly proportional, if the length increases, the time period also increases. At the same time, if you're cooling it, the temperature decreases. Because of the temperature decreasing, the length is going to contract, and as the length decreases, the time period also decreases. Is this clear? Chamka. Okay. Now, this is something which we are very clear. Now, over here, people, you have to understand this thing. Now, this gets confusing for many people. See this. If I'm heating it, the temperature increases, the length increases, the time period increases. Okay. Now, when I'm saying the time period increases, has the clock slowed down or is it fast? That is the question. Is your clock or your watch slow or fast? That is exactly what I want to ask. Okay. So, what is the question? If the time period has increased, your clock or your watch is slow or is it fast? That is exactly what I want to ask. Is it slow or fast? Okay, Elizabeth says slow, Harika says fast. Okay. More answers. I need more answers. Fast. Okay, Tina says fast. Okay, slow. Okay, I need. Okay, see this. Okay, what is time period, people? Time period is basically the time required by the pendulum to complete one oscillation. है ना जी? What is one oscillation? Ne. Okay, one oscillation. So 1, 2, 9. This is one oscillation. The time required for a pendulum to complete one oscillation is basically time period. You all will be like, yes, sir. Now, earlier, the time period of pendulum was 2 seconds. But due to the temperature increase, the length has increased, the time period has increased. Right now, the pendulum takes 4 seconds. That means for completing the same level of oscillation, the time period has increased. That means your clock is slow right now, not fast. Are you all able to understand this? It is slow right now. So people, the increase in time period is basically means that there is your clock is slow, or there is a time loss. Okay. Are you all able to understand this? At the same time, if the length has increased, the time period decreases. That means your clock is fast. So there is a time gain. Okay, people. So this is one formula that you have to keep in mind. That is the delta T. What is delta T? Change in time period is equal to half alpha delta theta. What is delta theta? Delta theta is basically your change in temperature, and T is basically your original time period. ठीक है? चमका everybody. Yes, चमका. Okay. Let's move ahead. Yeah, now we're going to understand something called as thermal stress. Okay, we're going to understand something called as thermal stress. I want you all to like this session, people. Okay, let's understand thermal stress. Now let me basically understand you the overview of the situation over here. Okay, so this is, I have a rod over here. Which has length L and the coefficient of linear expansion as alpha. Okay, and I'm basically gonna heat it. Now you all will be like, sir, on heating the rod, obviously the rod will try to expand, and what will be the expansion gonna be? The expansion is gonna be delta L is equal to L alpha delta T. है ना जी? You all will be like, हाँ जी, एकदम बराबर. Now, but what I'm gonna do is basically I'm gonna basically place two boulders over here. Okay, two boulders or two pillars over here. Okay, so what is gonna happen? That this rod will try to expand. By delta L, but due to these boulders, it is not able to expand. So basically, can I basically say that due to these boulders are basically gonna act a compressive force, on this rod? Are you able to understand this? So what I wanna say is, if due to the heat, the rod tries to expand by delta L, due to these boulders, the rod compresses by delta L. Are you all able to understand this? That means the rod tries to expand by delta L, but due to these boulders, it gets compressed by delta L. So the net change is again zero. That is, the rod has not changed in length. And due to this fight, a thermal stress develops in this rod. Are you all able to understand this? Yes or no? है ना? So what I have written? Compressive stress acts on the rod, which compresses the rod by delta L and limits any change. So basically, the delta L due to heat is equal to the delta L due to compressive stress. So the net change is zero. No change in length. Now this is something which we'll learn in mechanical properties of solids, but as you all know, you're going to give NEET exams. So this is a quick revision for you all. You all know that the strain is basically change in length divided by the original length. The change in length is L alpha delta T divided by L. L gets cancelled. So the strain that you get is alpha delta T. This is basically the strain that you're getting, a very, very important formula. So if they ask you what is the strain, it is alpha delta T. Okay. Next, you all know that this ratio of stress divided by strain is basically Young's modulus.
So from this formula, you can write the formula of stress as Young's modulus multiplied by strain. What is the strain? Strain is alpha delta T. So it becomes stress is equal to Y alpha delta T. So this is basically the thermal stress that you're getting over here. This is basically the thermal stress that you're getting over here. A very, 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 very important formula. A very, 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 very important formula. Next, if they want you all to find out the thermal force or the compressive force again, you all know stress can be written as force divided by area. That is exactly what I've written over here. Force divided by area is equal to Y alpha delta T. A goes to the other side, so you get F is equal to Y Young's modulus A alpha delta T. Chamka, yes or no? Chamka, yes or no? Chamka, yes or no? Okay, good morning, good morning. Okay, let's understand. Superficial or aerial expansion? Superficial or aerial expansion. So earlier you had an area, initial area is A0, you heated it, so it got expanded, है ना? So this is the change in area. This is the change in area or delta A over here. Again, I'm not gonna waste my time because I have explained everything thoroughly in detail in linear expansion. Same thing over here, just the variables change. Just the variables change. So delta A is equal to A0 beta delta T, where beta is basically coefficient of aerial expansion. That's it. That's it. Same thing. Final length is equal to original length plus change in area, that is delta A. Okay, and you get this formula again. Very easy. Very easy to understand. Very easy to understand. Okay. Next. Volume or cubical expansion. Volume or cubical expansion. What is it, people? What is it, people? That means, again, initial volume was V0. You heated it. It got expanded. This is the change in volume, that is delta B. That is delta B. Okay. So again, same, everything is same, just the variables change, people. That is the change in volume is V0 gamma times of delta T, where gamma is basically coefficient of cubical expansion. Okay. Clear? Okay. Now, the new change in the new volume is original volume versus delta V. Substitute this thing and you will get this formula. Okay. Now, this is a very, very important thing. Please star it. Yes, please start this. Okay. Okay, people. Okay. Now for a linear anisotropic solid. Okay, now this anisotropic solid you study in solid state, which is not there in your syllabus anymore in your chemistry. So what is anisotropic? Anisotropic is that solid which has different properties in different directions. Now what do I mean by that? So if I take this thing, if I go over here, the density is going to be same. If I go over here, the density is going to be same. But in anisotropic solids, in every direction, you're going to get different values or different properties. That is exactly anisotropic. Okay, people. So this is the relation that you have to keep in mind. That is, coefficient of cubical expansion is 3 times of alpha. Coefficient of beta or aerial expansion is 2 times of alpha. Am I clear over here? This is something that you have to keep in mind. Okay, this is something that you have to keep in mind. Okay, people. Like the session, people. Like the session. Okay. Very good. Okay. Let's move ahead. Okay. Don't worry. We're going to solve numericals as well. I just want to complete. Okay. Now, this is a very, 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 very important thing. A very, 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 very important thing. Okay, people. That means now we have to understand variation of density with temperature. How does density vary with temperature? That is something which you have to look over here. Okay, very, very easy, people. Now what is density? First of all, let us understand what is density. Okay, let us understand what is density. So you all know that density D, if I'm right, okay, I'll write it as rho. Density rho is basically mass divided by volume. Now, obviously, mass is not going to change. Mass is constant for you all. So whatever relation that we are going to get is with respect to volume. And mass is constant. Yes or no? Haji. Now, so what happens over here? See this. The temperature increases. Now, if the temperature is increasing, it's going to expand. So if the expansion is going to take place, the volume is going to increase. Now, as the volume and density are inversely proportional to each other, So if the volume increases, the density has to decrease. That is something which we are very clear. Yes. So that is the reason density decreases over here. Density decreases over here. Okay. Now, this is the relation of change in density. Again, same thing. That is, change in density is equal to initial density gamma times of delta T. Now, why gamma over here? People, that is because density, okay, density we take, now what do we take over here? We take volume over here. What is volume? Volume is length, breadth into height. It's a three-dimensional thing. It's a cubical expansion that we are going to take place over here. है ना जी? That is the reason we take gamma over here. We're going to take gamma over here. Okay. So delta rho is equal to rho naught gamma times of delta T. Are you all okay with this formula? Now, as the temperature increases, the volume increases, the density decreases. That means the final volume, the final density is going to be lesser than the initial density. That is exactly what I've written over here. The final density is equal to initial density minus the change in density. Now the change in density is basically this formula. Just substitute over there and you'll get this formula. Yes or no? Chamka, yes or no? Okay. Okay, very good. Okay, now we're going to talk about anomalous behavior of water. Okay, we're going to talk about anomalous behavior of water. Now for that, just give me a second, people. Yes, just give me a second. I also want, to make you explain everything. Okay. Just give me a second. Okay. Yes, this is exactly what I want to say. Okay, let's study from the NCERT itself. Okay, people, see this what's happening over here. Okay, now, people, this is volume and this is temperature over here. Okay, this is basically the graph of volume versus temperature. What is happening? This is temperature. Okay, see, this is temperature over here. As soon as the temperature is decreasing, you are able to see that the volume is decreasing. Are you all able to understand this, people? Yes. Now comes the most important part. Now this is something which is very much, it follows your trend. That means temperature decreases, volume decreases. That is something which we are going to get over here. But as soon as it reaches your 4 degrees Celsius, in your 4 degrees Celsius, when you decrease the temperature further, when it becomes 3.9 or something, according to the trend, if you're decreasing the temperature, the volume should decrease, it should contract. But what is happening over here? The volume starts to increase. It's a very crucial point over here. That means you're getting a curve over here. Yes or no? Yes, you are getting a curve over here. So over here, see, the volume is decreasing. This is basically the minimum volume that you are getting, because after this 4 degrees Celsius, the volume of water is increasing. That is the anomalous behavior of water. That is something which we did not predict. It is not going according to the trend. Are you able to understand this? Yes or no? So from 0 to 4 degrees Celsius, or from 4 degrees Celsius to 0 degrees Celsius, the water is expanding. Okay, people. Now, the volume and density being inversely proportional, you are getting this graph. The inverse of this graph is exactly this. This is exactly what you are getting. Now, we all know that density is equal to mass by volume. Now at 4 degrees Celsius, okay, at 4 degrees, you are getting volume minimum. So rho is equal to mass divided by V minimum. Now if volume is minimum, you will get density as maximum, and that is exactly what you are getting at 4 degrees Celsius. You are getting the density as maximum. as maximum. Are you all able to understand this? That is, so the value of density of water, that is 10 raised to 3 kg per meter cube, that is exactly at 4 degrees Celsius. Okay, people. Is this clear? Is this clear, people? Chamka? Is this graph clear? Is this graph clear? Yes or no? Okay. Now what we are going to do? We are going to do calorimetry. Okay, we are going to do calorimetry. Calorimetry. Okay, people. Okay. Now, let's understand calorimetry. It's the crux of this chapter, actually. The crux of this chapter. What is calorimetry? Again, it's the measurement of heat, which is again a form of energy. It is called as calorimetry. Okay. Now, let's understand. The SI unit is again joule, because again it is the measurement of heat, and heat you measure in terms of joules. Okay, a very important relation when it comes to your joules, that is 1 calorie is equal to 4.2 times of joule or 4.18 joules. Okay, so 4.18 joules is the most accurate value. The approximate value is basically 4.2 joules. The approximate value is 4.2 joules. Okay, now the symbols used with respect to heat is Q, delta Q, and sometimes H also, but H we are not going to use. The only symbol that we are going to use is Q and delta Q. Clear? 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 Yes or no?
मेरे पास पेन टाइप का स्टाइलस है एक्स्ट्रा।
अरे मैंने तुझे दिया था ना, उधर ही होगा वो, मेरे पास मैंने लिया नहीं है। Okay. Yes, people. Clear? Okay. So this is the symbol that we are going to use. Okay. Yes. Let's move ahead. Now let's understand specific heat capacity. Now, people, please keep in mind that this definition is one of the most important definitions in your thermodynamics. It's one of the most important definitions. Sir, your voice is breaking. Sir, please listen to me. Is the voice breaking, people? Is the voice breaking? Is the voice breaking, people? Yes. Is it breaking? No. Okay. Chalo. Now, this is a very important thing to understand, people. Okay. Now, what is specific heat capacity? All your attention in the screen, okay, people. What is specific heat capacity? What is the amount of heat? What is the amount of heat that should I give to this object of unit mass? Okay, again, a very important thing. What is the amount of heat should I give to this object of unit mass to increase the temperature of this object by 1 degree centigrade is called as specific heat capacity. Is this clear? Is this clear? Again, I am repeating. What is the amount of heat should I give to this object of unit mass so that it increases the temperature by 1 degree centigrade? That is exactly what is called as specific heat capacity. Are you all clear about this? That is exactly what I have written over here. Now, let me explain you through this example. I have 1 gram H2 over here. I have to increase. Now, this right over here, it's again unit mass. That is 1 gram H2. 1 gram unit mass. Now, this can be 1 kilogram, 1 ton, anything, but it has to be unit. 1 gram H2. I have to increase the temperature by 1 degree centigrade. So what is the amount of heat should I give? I have to give 4.2 joules or 1 calorie heat to increase the temperature by 1 degree centigrade. That is exactly the specific heat capacity, or in this case, the specific heat capacity of water. So if I want to define it, so specific heat capacity is C over here. C is equal to delta Q, amount of heat required to increase the temperature by 1 degree centigrade. So I divided by delta T to get 1 degree centigrade. Of a unit mass, I divided by mass. So this is exactly the formula that I get over here. Now, delta Q can be terms of joules, mass is kg, and delta T is Kelvin. Chamka, yes or no? Okay. That is specific heat capacity for you all. Next. So now this, people, see this. Now this specific heat capacity can have many units. Now you have to change according to your question. So delta Q is basically joules, mass kg, temperature Kelvin. Sometimes it can be kg, can be gram also. over here it is joule gram centigrade, calorie gram centigrade, calorie kg centigrade. It can be anything, है ना? So depending upon question, you just have to convert it from one unit to another. That is exactly what I'm saying. Now some of the values that you have to keep in mind. Okay, some of the values that you have to keep in mind. Specific heat capacity of ice is basically 0.5 calorie gram centigrade. What do I mean by that? That means I'll have to give 0.5 calories of heat to 1 gram of ice. Okay, 0.5 calories of heat to 1 gram of ice to increase the temperature of that particular ice by 1 degrees. That is exactly what do I mean by this statement. Okay, so specific heat capacity of ice is 0.5 calorie per gram centigrade. Specific heat capacity of water is 4200 joules per kilogram per centigrade, or 4.2 joules per gram per centigrade, or 1 calorie per gram per centigrade. Okay, and specific heat capacity of water. Acha, now this is something, why copper over here? I'll make you explain. Now people, if you all notice over here, specific heat capacity of water is 1 calorie per gram centigrade, and of copper is 0.4 joules per gram centigrade. So that means for the same change in temperature, of 1 degrees, with respect to water, I'll have to give 1 calorie of heat. But with respect to copper, I just have to give 0.4 calories of heat. So which one is a better conductor? Copper or water? Yes, copper or water? Yes, I need the answers. Copper, very good. Because I just need to give 0.4 calories of heat. So 0.4 joules of heat. Are you able to understand this? Yes, 0.4 joules of heat, but over here I have to give 4.2 joules of heat, and for the same temperature decrease. That is the reason lower specific heat capacity is a better conductor. Okay, now we're going to understand. If a body has specific heat capacity infinity, what do I mean by that? Let's relate with the definition. The definition says amount of heat required by unit mass to increase the temperature by 1 degree. So I have to give infinite amount of heat energy to increase the temperature by 1 degree, but it's not possible. So in this case, I'm going to talk about heat reservoir. So heat reservoir is basically that case. In which you have the specific heat capacity as infinity, or the temperature remains as constant. Any amount of heat you give, the temperature remains constant. That is exactly what do I mean by that. If you want to increase the temperature of heat reservoir, you have to give infinite amount of heat energy. Are you all able to understand this? Yes or no? Okay. Yes or no? Let's move ahead. Now we are going to understand principle of calorimetry. Okay, now principle of calorimetry is dependent upon based upon conservation of energy, and it is also based upon second law of thermodynamics. Okay, now what is conservation of energy? Again, energy can neither be created nor destroyed. It can only flow from one part to another, or it can get converted from one form to another form. That is exactly conservation of energy. Second law of thermodynamics is again that heat can only flow from hot body to cold body. It cannot go opposite. It cannot go from opposite side. Okay, so if there is no loss of heat lost by the hot body is equal to heat gained by the cold body. So whatever heat gets lost by the hot body, that much amount of heat is gonna get gained by the cold body. That is exactly what I am talking over here. Okay, now heat transfer takes place until both bodies attain the same temperature. Now again, sir, which lesson is this? This is thermal properties. Okay, so heat energy is basically a flow of energy. Similarly like current. What is current? Current is the flow of electrons. Why is it flowing? Due to some difference. Which difference? Potential difference. Over here, heat flows due to the temperature difference. If the temperature difference is 0, there is not going to be any heat flow. Are you all able to understand this? Yes or no? Okay. Chalo, let's move ahead. Okay, now we are going to talk heat capacity or thermal capacity. Okay, chalo. Now, heat capacity or thermal capacity is actually mass dependent, because in specific heat capacity, है ना जी, in specific heat capacity it was not mass dependent. It was not mass dependent because again we are just talking about unit mass. But over here it is mass dependent. Why it is mass dependent? Because we are going to talk about whole of the body. We are going to talk about whole of the body. Are you all able to understand this, people? That means specific heat capacity depends upon the material, just like density. Just like density. Obviously, so the density of water is 10�3 kg per meter cube. है ना? So like that same thing, in that same way, the specific heat capacity also depends upon the material. For every material you're gonna have some value of specific heat capacity. What is specific heat capacity? Specific heat capacity is basically the amount of heat that I should give to this particular object to increase the temperature by 1 degree centigrade. Whole mass, I'm not taking unit mass over here. I'm not taking unit mass over here. Whole mass of the body. So the amount of heat that I should give to this whole mass of the body to increase the temperature by 1 degree centigrade. Chamka. That is exactly I have written over here. है ना? So it becomes capital C is equal to delta Q divided by delta T. No delta M this time. No M this time because I am not concerned about unit mass. I'm talking about whole of the body. I'm talking about whole of the body. Chamka. Yes. Yes, people. Now this delta Q can be written as MC delta T, where C is basically what? Specific heat capacity. है ना? Delta T gets cancelled. This is a very important relation that you get. That is, heat capacity capital C is equal to M into small c, and that is something which is very intuitive. Specific heat capacity was for unit mass. If you multiply it by small m, you will get the heat capacity for the entire body. You'll get the heat capacity for the entire body. That is something which we are very much intuitive. Okay, people. So let's move it. Now we are going to understand water equivalent. Okay, people. Okay, don't worry. We'll solve numericals as well. Okay. Now, what is water equivalent? Now, people, how many of you all face issues with respect to water equivalent? You are not able to understand what is water equivalent. Yes, people? Okay. Thank you, Simi. Okay. Yes, sir. Okay, chalo, let's understand. Okay, what is water equivalent? Okay, now I'll explain you this water equivalent by only this example. This example is only required for understanding water equivalent. Okay, what is water equivalent? Now, if in your question it comes, water equivalent of A is 10 grams. Water equivalent of A is 10 grams. What does it mean? It exactly means that the heat capacity of 10 gram H2O is equal to the heat capacity of A. That is exactly what it means. Are you able to understand this? That means how much gram of water I have to take so that its thermal capacity, that is, so that the water thermal capacity matches with the capacity of A. Are you able to understand this, people? Are you all able to understand this? Chamka, yes or no? Again, I'm going to repeat the same thing. Okay, That means if somebody says water equivalent of A is 10 grams, that means I have to take 10 grams of H2O, and the 10 gram H2O, the thermal capacity of this 10 gram H2O is going to be equal to the heat capacity of A. Are you all able to understand this? Chamka. So if somebody says water equivalent of A is 50 grams, that means the thermal capacity of 50 grams of H2O is going to be equal to thermal capacity of body A. Chamka. And that is how you get this. That is, thermal capacity of water equivalent is equal to thermal capacity of body. Thermal capacity can be written as MWCW, where CW is specific heat capacity of water, and this becomes MBCB. That's it. Chamka, a very important thing. That, don't worry, we'll solve the numericals also. Clear. Next, moving on. Now we're going to study latent heat. What exactly do I mean by latent heat? Latent heat is basically, people, the hidden heat. Latent heat is basically the hidden heat. Okay. Now, What is latent heat? Latent heat is basically the amount of heat required to change the state or phase of an object, provided the temperature remains constant. That means if I have ice over here, if this is ice, what is the amount of heat should I give to this ice so that it completely changes to water, provided the temperature remains constant? Now what happens is that when you have ice, at 0 degrees Celsius, you are heating it, you are able to see that the ice is melting into water. But the temperature is still at 0 degrees Celsius. You all will be like, "Hai ji, ye kya ho gaya?" So I'm basically providing the heat, but the temperature is not increasing, but the ice is melting. What is happening? So basically, we are going to enter the molecular level now. Right now. What is the molecular level? I'll basically tell you. So that is the reason we have told it is at hidden heat. You are not able to see where is this heat going. What is happening when you are continuously heating this substance? This heat goes inside and tries to break the bonds. Are you all able to understand this? So ice, it's a solid. So it will have bonds. So this heat tries to break the bonds, and due to this, the ice gets converted into water. So whatever heat you are giving, it is responsible for converting the phase change. It is responsible for converting the state change. So it is not responsible for increasing the temperature. Nah, it is only responsible for the state change or the phase change, provided the temperature remains constant. Chamka, yes or no? Okay, that is exactly what it is. So state change happens in constant temperature, and L is equal to delta Q divided by M, or delta Q is equal to M into L. Is this clear? Okay, nice. Latent heat of vaporization. Let us understand latent heat of vaporization. I have 1 gram H2O, which is at 100 degrees Celsius, It is at right now in liquid state. Okay. I need to convert this into steam. I need to convert this water into steam. So see, the temperature is still same. Because the phase change is happening. So I have to give 2260 joules per gram, or 540 calories per gram of heat to this 1 gram H2O to convert all of these things into steam. Chamka. Very good. Are you able to understand? So this is the latent heat of vaporization for steam. Next, latent heat of fusion or melting. What is happening? I have ice over here, 0 degrees Celsius. 1 gram ice, 0 degrees Celsius. I need to convert it into 1 gram H2O at 0 degrees Celsius. So what is the amount of heat I have to give? 336 joules per gram, or 80 calories per gram. That is exactly. Chamka, everybody. Chamka. Yes or no? People, I need likes, people. I need likes. Okay. That is exactly what I want to do. Okay. Now this is a very important thing. This is a very, 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 very important thing. Okay. No problem, Simmi. No problem. Okay. Now people, so the question over here is that I have 1 gram ice at 0 degrees Celsius. I need to convert it into steam at 100 degrees Celsius. So what is going to be the flow over here? The flow is very simple. I have 0 degrees Celsius ice. First I'll do the phase change. I'll convert the ice entirety into water at the same temperature, 0 degrees Celsius. So I'm going to use ML, latent heat over here. Then I'm going to increase the temperature till 100 degrees Celsius. I'm going to use MC delta T over here to increase the temperature. Then as soon as I reach 100 degrees Celsius, I'm going to convert it into steam. Again, I'm going to use latent heat over here. So again, M into LF for this thing, MC delta T for this thing, MLV for this thing. That's it. M I take common. LF value is 80 calorie per gram. CW is again 1. Delta T again we know the delta T value is again 1. So and MLV, LV is basically 540. Just add. So you need 720 calories for converting 0 degrees Celsius ice to 100 degrees Celsius steam. That is exactly the equation over here. Chamka, yes or no? Okay. Okay, so people, last, yes, now we are going to understand heating curves. We are going to understand heating curves. Okay, yes, you can, yes, you can, yes, you can, yes, yes, okay. We'll solve numericals, don't worry. Okay, now let's understand heating curves. Okay, let's understand heating curve. So heating curve is nothing. Heating curve is nothing. It is basically the graph of temperature and heat. It is the graph of temperature and heat. Okay, people. Now, if you all understand, over here, just a second. Okay, if you'll understand over here, yes, yes, you will get it in the Telegram channel. Okay, so people, this is temperature, this is heat, hai na ji? So right now I have water which is I have ice which is at minus 10 degrees Celsius, hai na? I have ice at minus 10 degrees Celsius. I need to convert it into steam which is at 110 degrees Celsius. Now let's understand the flow over here. The flow is something, it's very easy. First of all, I have to convert ice into 0 degrees Celsius ice. So I have to give MC delta T heat, okay. Then from ice to water, phase change is happening, so temperature has to remain constant. So latent heat, M into L. Over here, so once all of the ice has been converted into water at 0 degrees Celsius, hai na ji? So we have to convert this water into water at 100 degrees Celsius. So again MC delta T. Then I have to convert water at 100 degrees Celsius to steam at 100 degrees Celsius. So again ML, hidden heat, ML. Then again from 100 to 110, it is MC delta T. That is exactly what we are going to do. So see this curve, heat. So minus 10 degrees Celsius to 0 degrees Celsius, I have to give heat. So it reaches over here. I'm still continuously giving heat. See, I'm still continuously giving heat, but the temperature is constant. So over here, the phase change is taking place. Over here, the ice, over here, the phase, no, sorry, exactly. So this is ice. Yes, the phase change is taking place. So over here, all of the ice has been converted into water. Again, MC delta T. Heat increases, temperature increases. It has reached 100 degrees Celsius. Okay, people, are you able to understand this? Then again, this is the temperature constant. Again, the phase change is taking place. Over here, everything has been converted into steam. Then again, you have increased the temperature over here. Everybody clear? Now, what does the slope give us? That is dt by dq. What does the slope give us? That is dt by dq. So dt is dt, dq can be written as mc dt, dt cancel, that is 1 divided by mc or 1 divided by heat capacity. The slope of a heating curve basically gives you the inverse of heat capacity. Okay, people, chamka, yes or no? Okay, so people, we have all completed the theory of this chapter, hai na? We've all completed the theory of this chapter. So let's solve let's solve a problem. This is your problem. Okay, we'll just solve a few problems and then we'll move on to the next chapter. Okay, let's move ahead. The length of a steel rod is 5 centimeter greater than that of a brass rod. Okay, if this difference in the length is to remain the same at all temperatures, then the length of the brass rod will be. Now people, one thing that you have to keep in mind. Okay, you're Malayali too, nice. If the difference in the length is to remain same at all temperature, so this length is same to remain at all temperature. If you get this statement in your NEET exam, hai na? Okay, so if you get this statement, if this difference in the length is to remain the same at all temperatures, you can directly use this equation, that is alpha L1 is equal to alpha 2 L2. You can directly use this equation. Okay, people, that is one trick that we are going to follow over here. But okay, let's solve this equation full and square. So the length of the steel rod is 5 centimeter greater than of the brass rod. That means, can I say length of steel minus length of brass is exactly equal to 5 centimeter? Okay, this is exactly what I'm saying. Now, if this difference in the length is to remain the same at all temperature, that means even if I heat it, so obviously the length of steel will be L dash S minus L dash B, hai na? they are basically saying even if after heating the temperature, the difference between the length is going to be same. So basically if the steel has increased by 2 centimeters, the brass length has also increased by 2 centimeters. That is the reason the difference is still constant. The difference is still constant. Samjha, chamka. So this is still going to be 5. This is still going to be 5. That is exactly what we're gonna. That is exactly what we are gonna use over here. Okay. I hope I have made you clear what do I mean by this. Okay. Now, basically, can I basically say that the change in length of steel is equal to the change in length of brass? This is exactly what I want to solve over here. Now, delta LS can be written as LS alpha S delta T, which is equal to LB alpha B delta T. LB alpha B delta T. Okay. So what you are getting over here? Delta T gets cancelled, and that is exactly what we are getting. Even if, so in your question, if the difference in the length is to remain the same at all temperatures, you can basically write this alpha 1 into L1 is equal to alpha 2 into L2. Okay, people. What is the value of alpha S? Alpha S comes out to be 12. This is 12 into 10 to the power minus 6. LS we don't know. LS we don't know, which is equal to LB also we don't know. Alpha B comes out to be 18 into 10 to the power minus 6. Hai na ji? Now, when we solve this, this gets cancelled. This is 6 3s are, this is 6 2s are. So 2 times of LS is equal to 3 times of LB, or 2 times of LS minus 3 times of LB is equal to 0. Now this is your first equation, this is your second equation. I hope so. You can all solve these two equations and basically solve the correct value. Okay. Okay, people. Yes or no? Are you all clear with this? Are you all clear with this? Yes or no? Okay. Just a second, people. Just a second, okay? Just a second. Okay. So this comes out to be 10 centimeters, people. Okay, people. So you can all solve, and this comes out to be 10 centimeters. Okay. Chalo, let's move ahead. Okay. Okay, people, this is a very important one. A very important one. Okay, people, a very important one. Okay, I'm gonna basically give you a new formula over here. Okay, I'm gonna basically give you a new formula over here. What is the formula? If the two rods of length L and 2L having coefficients of linear expansion alpha and 2 alpha respectively are connected so that the total length becomes 3L, the average coefficient of the linear expansion of the composition rod will be. A new formula over here, people. The formula is the alpha of the composite rod. Alpha of the composite rod is basically going to be equal to alpha L1 plus alpha 2 L2 divided by L1 plus L2. This is basically the formula that you have to keep in mind. This is basically the formula that you have to keep in mind. Okay, people. Yes, please solve this and tell me your answers in the chat. So what they have said, two rods, length are L and 2L and linear expansion alpha 2 alpha. Okay, chalega. So this is basically alpha into L and this becomes 2 alpha, right? Yeah, 2 alpha into 2L and this becomes 3L for you all. So this becomes 4 alpha L, this becomes 5 alpha L divided by 3L, and this becomes 5 alpha divided by 3, 5 alpha divided by 3, and that is your answer, option C. Okay. Okay, people. Okay, people. Yes or no? Yes or no? I have given a lot of problems in this PPT, people. So you can all solve this if you want to solve after the session. Okay, you can all solve this after the session. Okay. Yeah. Next question. Next question. What is the question, people? When a rod is heated but prevented from expanding, the stress developed is independent of what? The stress developed is independent of what? Now, people, we all know we all know that the stress, that the stress is basically y alpha delta t. Y alpha delta t. This was the formula that we got. Hello, very good. Yes, y alpha delta t. Now, when a rod is the stress developed is independent of. Acha. So material of the rod, no, it is dependent. Young's modulus is dependent. So this is wrong. This is wrong. Alpha rise in temperature, is independent. No, it is dependent. It is dependent. Length of the rod and none of these and none of these. So basically, what I'm saying is that length of the rod does not come up in the formula. So obviously, length of the rod is your answer. Okay. Everybody able to understand? Everybody able to understand? Yes. Cool. Two rods of different materials having coefficients of linear expansion alpha 1, alpha 2 and Young's moduli y1, y2 respectively are fixed between two rigid massive walls. Okay. So the rods are heated such that they undergo the same increase in temperature. Now people, again, the rods are heated that they undergo the same increase in temperature. A very important line. The rods are, okay, there is no bending of the rods. If alpha 1 is to alpha 2 is 2 is to 3, the thermal stress developed in the two rods are equal, provided y1 is to y2 is equal to what? So basically what they have said, thermal stress is equal. Thermal stress is equal. So basically, can I say sigma 1 is equal to sigma 2? That is basically the thermal stress. The thermal stress can be written as y alpha delta t. So this is y1 alpha 1 delta t is equal to y2 alpha 2 and delta t. So delta t gets cancelled. We need to find out y1 by y2. So y1 by y2 is basically alpha 2 by alpha 1. The value of alpha 2 by alpha 1 by alpha 2 is 2 is to 3. So this becomes 3 is to 2 and that is your answer. 3 is to 2 and that is your answer, option A. Very good. Very good, people. Very good. That's how you keep up the josh. Nice. Yes, this is a question. What is the question? If the length of the cylinder on heating increases by 2%, the area of its base will increase by what? The area of its base will increase by what? Acha. Okay, if the length of the cylinder on heating increases by 2%. So they basically said that delta L divided by L, this is basically the change in length, increases by 2%. So this is basically 2% over here. So this becomes 2 by 100. 2 by 100. Junction temperature I will be teaching. Don't worry. Heat transfer, that is the next one. That is the next one. Don't worry. Okay, that is the next one. Okay, the area of its base will increase by how much? Okay. How to do this, people? How to do this, people? Anybody? Okay, chalo. Okay, people, so let's understand this. If the length of the cylinder on heating increases by 2% over here, so okay, what I'm going to do is, I'm going to take the initial length, that is L0 to be 100. So the final length will be 102. Yes, I will, Sara. Don't worry. I will, Sara. So the delta L is basically 2 over here. That is exactly what I'm going to take. So I can write delta L is equal to L0 alpha delta T. What is delta L? Delta L is 2. L0 is basically 100 and this is alpha delta T. Okay. This is alpha delta T. So what do you get over here? Alpha delta T is basically 2 by 100. That is 1 divided by 50. 1 divided by 50. That is something which you are getting. Okay, points to pointer in English. Oh my goods. Okay, I will try. Okay, next. So now the area of its base. So the area is basically delta A is equal to A naught beta delta T. A naught beta delta T. What is the change in area? Achha, area of its base will increase by. So basically they have asked delta A divided by A naught percentage, which is basically beta times of delta T. Now what can I write beta? Beta is basically 2 times of alpha. Beta is basically 2 times of alpha. I've already taught this. So basically substitute this. What you'll get? 2 alpha delta T, 2 alpha delta T. Alpha delta T value, you know, that is 1 by 50. So this becomes a 2 divided by 50, which is basically 1 by 25. Now you want the percentage of it, just multiply by 100. What you'll get is 4%. 4%, and that is your answer. And that is your answer. Chamka? Chamka? Yes or no? Okay, let's understand this one. Let's understand this one. If 20 grams of water at 60 degrees Celsius is mixed with 60 gram of water at 20 degrees Celsius, then the resultant temperature is, so Sarah, so whatever you have told me right now over here, it has come. Yeah. So you just said that you want this, so you have got this. Hai na ji? So let's solve. Let's solve. Hai na? 20 gram of water at 60 degrees Celsius. So people, you just have a very common method of doing this. 20 gram of water at 60 degrees Celsius. Hai na ji? 60 gram. Achha. So this is cold body. Hai na? This is cold body. That is 60 gram H2O. Hai na? I'm just gonna solve it once. After complete, shall we take a break? So let's see. Okay. So, so 60 grams. So I'm just going to solve it once in a detailed manner. Then we're going to use. Then we're going to solve it fast. Okay. So to cold 60 gram H2O at a 20 degrees Celsius. Okay. This is at 20 degrees Celsius, and this is the hot body. Okay. This is the hot body. Hot body is basically 60 degree. 20 gram of water. Okay. So this is 20 gram H2O at 60 degrees Celsius. At 60 degrees Celsius, this is basically what's happening. Okay. Now, what I'm doing is I'm going to assume that when we're going to mix these things together, it's going to reach an equilibrium temperature of some T. It's going to reach some equilibrium temperature of some T. Hai na? So obviously this water will get converted into some temperature T. This water also will get converted into temperature T. So again, I can use this equation that whatever heat is gonna get lost by this hot body is gonna get gained by this cold body. So I can write that the heat gained by this cold body is basically heat lost by the hot body. Now, what is QC over here? Again, MC delta T. What is the mass? 60 over here. Mass is 60. What is CW? What is CW, people? Oh my god. Oh, that is CW. Okay, I do not want the value. So this is CW. And delta T. What is delta T, people? Again, delta T should always be big minus small. Should always be big minus small. So this is the cold body. This is the equilibrium temperature. So obviously cold body, when it gains heat, it's going to increase the temperature. So obviously T is going to be the bigger temperature. So over here, this becomes T minus 20, which is equal to, now for QH, mass is 20 grams. This is CW. What is delta T? Heat is getting lost by the hot body. That means the final temperature is going to be the less. This is going to be higher. So this is basically becomes 60 minus T over here. 60 minus T over here. Everybody clear? Everybody clear? Everybody clear on how did I write this equation? So over here, CW gets cancelled. 0 gets cancelled. This is 2 1s. This is 2 3s are. What do I get over here is 3 times of T minus 20 is equal to 60 minus T. Good, very good. So this is 3T minus 60 is equal to 60 minus T. 4T is equal to 120 and T is equal to 30 degrees, and that is your answer. That is your answer. Pakka, maja aaya. Yes, very good. Okay, people, I hope so you're absolutely clear. Okay, we are going to solve okay, let's solve one more, hai na? Let's solve one more. Okay, Yeah, this one people. Okay, this is the question that you have to solve, people. Yes, let's solve this, people. Okay, let's solve this. Okay, let's solve this. Okay, a vessel of copper of mass 0.21 kg contains 20 gram of water at 8 degrees Celsius, है ना? If 100 gram of water at 10 degrees Celsius is poured into it, find the final temperature of the mixture, है ना? So see, this is a very the common sense question. This is a common sense question. So what they have said, that a vessel of copper of mass 0.21 kg contains 20 gram of water at 80 degrees Celsius. By this only you should know that the temperature of the vessel is also 80 degrees Celsius. है ना? The temperature of the vessel itself is at 80 degrees Celsius, है ना? So if the water is at 80 degrees Celsius, obviously the temperature of the vessel is also going to be 80 degrees Celsius. So that is basically the biggest clue that you get from this equation. Okay, people. So again, Q hot is equal to Q cold. That's it. Q hot is equal to Q cold. Am I clear? Let's solve this, people. Let's solve this. Okay, so a vessel of copper of mass 0.21 kg contains 20 gram of water at 80 degrees Celsius. Let's assume they all reach an equilibrium temperature T, है ना? If 100 gram of water at 10 degrees Celsius is poured into it, find the temperature of the mixture. Okay, so heat lost by the hot body. Right now over here the heat is gonna get lost by the copper vessel and the water inside it also. Yeah, that you have to keep in mind. Okay, people. Okay, let's understand. Q of hot. What is hot? Let's understand for copper. So heat lost by the copper will be 0.21 kg. So this is specific heat of copper in grams. Acha, in grams. So let's convert this into grams. है ना? Let's convert this into grams. So this is basically gonna be 0.21 m into 10 ki power 3. That is m. C of copper. C of copper is 0.4 into delta T. What is delta T, people? What is delta T? It's gonna get lost. The temperature is gonna decrease. This will be 80 minus T. This is 80 minus T. Okay, I don't know. Let's see. Okay, this is the equation, people. This is for copper. Now I have to write for water as well. The water inside the copper vessel also. Okay, now okay, it contains 20 gram of water. So this becomes 20 gram of water, m into Cw, that is Cw into delta T. Delta T is again going to be 80 minus T. So this is the equation. For the hot body. Now for the cold body, I'm going to write it over here only. Okay, for the cold body, it's going to gain this heat. The mass is 100 grams. Cw, delta T is going to be how much? It is going to be if 100 grams is the final temperature 10 degrees Celsius. So this is going to be, it's going to increase, it's going to increase. So this is basically T minus 10. Yes or no, people? Is this clear, people? Yes or no? Yes, is this clear? Okay, is this equation clear? Yes. So the value of water Cw is 4.2. The value is 4.2, है ना? So just substitute over here, and the value that you get is something like this: 2 into 80 minus T, 2 into 80, yes, 2 into 80 minus T, and this becomes 5 into T minus 10. This is exactly what you are getting. So this is 160 minus 2T is equal to 5T minus 50. When you solve this, you get value of T is equal to 30 degrees Celsius. Okay, you will get Mahalakshmi, you will get this. Okay, Mahalakshmi, you will get this. Yeah, I'll ask Yavar sir to send this. Okay, chalo, let's move ahead, people. Okay, let's move ahead. Okay, so I have, so we're going to solve one more question. And this is your question. I'm so sorry for the bad quality over here, but this is a good question. I wanted you all to solve. Okay, yeah. What is it? It's based upon last question. Which chapter was this question from? This thermal properties. Okay, last question, and then we are going to move on to heat transfer. Okay, 10 gram of ice cubes at 0 degrees Celsius are released in a tumbler. Okay, please read the question and answer it, people. Please read the question and answer it. Okay. Okay. What is it? 10 gram of ice cubes at 0 degrees Celsius are released in a tumbler. That the water equivalent of tumbler is 55 grams. Water equivalent of tumbler is 55 grams. That means, what do I mean by that? Okay, what do I mean by that? What do I mean by that? Water equivalent 55 grams. That means thermal capacity of 55 grams of H2O is equal to the thermal capacity of the tumbler. Yes or no? Did you all understood it? Did you all understood it, people? Did you all understood it? That means, what do I mean by this statement? What do I mean by this statement? That means MWCW is equal to MBCB. MBCB. That means thermal capacity of 55 grams of water is equal to the thermal capacity of the body itself. Are you all able to understand this, people? Are you all able to understand this, people? Yes or no? Yes or no? So mass of water is 55. This is 1 calorie, that is 1 calorie per gram, and that is equal to MBCB. So you know the value of MBCB from here. You know the value of MBCB from here. Are you all able to understand this? Are you all able to understand this? Yes or no? Are you all able to understand that? Then it's a very easy question. It's a very, very easy question. That means 10 gram of ice cubes at 0 degrees Celsius are released in tumbler at 40 degrees Celsius. Assuming negligible heat is taken from the surrounding, the temperature of the water in the tumbler becomes nearly what? So again, Q of heat is equal to Q of cold. That means, khatam. End of story. So heat lost by the tumbler is going to be MBCB delta T. You know the value of MBCB. You know the value, it's going to be 55. So 55 delta T is going to be how much? Delta T is going to be 40 minus T. It's going to be 40 minus T. Heat gained by the cold body. What will be the heat gained by the cold body? Heat gained by the cold body is M, that is 10 grams CW, and delta T is basically T. Hai na? T, yes. So T minus 0. It's going to be this thing. It's going to be this thing. Everybody clear? Everybody clear? Yes or no? Okay. So this is exactly what you want to find out. Okay. Okay, I just did one mistake, people. I just did one mistake. So first of all, you have to convert the ice to water. We did not do that. So basically, latent heat. So it's basically going to be M into L plus MC delta T. Okay, plus MC delta T. Please solve this and you'll get it. Okay, people, and you'll get it. Okay, please do the values and the units properly, and you'll get it. Okay. So first we have converted all the ice into water, and then the temperature difference is going to take place. Okay, people, I missed that point. Okay, so that is exactly what I want to do. Okay, everybody clear? Can we move on to the next chapter? Okay, we'll increase the speed a little bit. Okay, so we're going to start with modes of heat transfer. That is heat transfer right now. Okay, we're going to heat transfer right now. Okay, people, everybody understood thermal properties? Very good. Let's move ahead. You want, do you all need break? Yes, do you all need break? We'll meet 11 o'clock then. Okay, we'll meet 11 o'clock. Okay, 11 o'clock. That is, you have 10 minutes. I'm giving you 10 minutes break. Okay. No. Okay, just a 10-minute break. 10 minutes break. Okay. Chumma 10-minute break, madam sir. Okay. Neither yours, neither mine. I'm going to give you a 5-minute break. Okay. I'm going to give you a 5 minutes break. Okay. 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 We'll meet after 5 minutes. Okay. Hello people, I'm back. I'm back. Okay. Chalo, let's start. Okay, people. I'm back. Okay, let's go. Okay, back on time. Yes. Sir, can you understand Manglish? Yes, I can. Very good. Okay, please call all your friends that we are back. Okay, let's start with modes of heat transfer. Okay, people. Now, we are going to increase the speed a little bit. Okay. Now, there are technically three modes of heat transfer: conduction, convection, and radiation. Okay, these are the three modes of heat transfer. Okay, now conduction. Okay, now conduction over here, it happens due to the oscillations of the molecules and it travels from molecule to molecule. Okay, now what happens is that it's very simple. Okay, now if I'm heating, just assume this arm to be a molecule. Okay, this arm to be one molecule and this second arm to be second molecule. If I'm heating this, obviously this molecule will start to oscillate. More the heat energy, more will be the oscillation. Now what happens in conduction is, so this arm is oscillating. So just see, because of this arm, the second arm is also oscillating. And so on, the oscillation will travel from one place to another. And this is how the heat energy transfers from one place to another. Are you all able to understand this? People? Yes or no? That is how conduction travels. That is how heat travels in conduction. Now, it is maximum in solids, then in liquids, and then in gases, Are you all able to understand this? It's a very easy thing to understand, because in solids the molecules are packed tightly, liquids, gases. That is the reason conduction, it mostly happens in solids. Okay, people. Okay, let's move ahead. Then let's move on to convection. Convection happens for fluids. Okay, very important point. It happens for fluids. And now what happens is that layers of fluid absorb energy and move away, giving chance to another layer to absorb energy. Okay, now what happens over here is, it's a very interesting and easy thing to understand. If this is the fire, okay, this is the fire. What happens? We know that the cold air is much more dense. So it will come down. Cold air will come down, and due to this heat energy, they will get heated up. And the density decreases. They will become light, and these cold molecules, they will become hot air molecules, and they will travel up. And over here they will cool down, and they're converted into colder molecules. And this current, this convection current takes place over here, and this is how the convection happens over here. Okay, so over here the molecule itself is traveling. In conduction, the molecules are oscillating. Are you all able to understand this? Okay, so this is how convection takes place. Okay, so convection mostly happens in fluids. So in fluids, that means Palakkad. Okay, so convection fluids. Okay, people. And radiation, again, electromagnetic waves do not require any medium. So this is something which I studied detailed in electromagnetic waves. Okay, so sun being the best. So which one depends on gravity? Very good. So gravity is dependent upon convection. Okay, in convection. Okay, people. Chalo, let's understand again. Oops. Okay, let's understand conduction. Okay, now people, conduction occurs due to the oscillation of molecules. That is something which I have already we have discussed. Generally occurs in solids, and that is basically the order which you have to follow. Next, variable state and steady state. This is a very important concept that you have to understand. Now these are all the same rods, but at different times. Okay, so this is the first phase. I'm heating this at this end. So this end is at 10 degrees Celsius, this is at 5 degrees Celsius, this is at 1 degree Celsius. Okay, so I'm heating it, and as I'm heating it, the temperature increases. So this becomes 40, this is 10, and this is 5 degrees Celsius. I'm again heating it, so this becomes 80, this becomes 50, this becomes 30 degrees Celsius. Now I realize I'm again heating it, but there is no change in temperature. Heat transfer. So this comes under thermal properties itself, but this is heat transfer. So you are able to understand that there is no change in temperature. You are again continuously heating it, but there is no change in temperature. Are you all able to understand? So this state in which the temperature is constant for that particular cross section, is called as steady state. All of the other states are called as variable states. Are you all able to understand this? Are you all able to understand this? Yes or no? Are you all able to understand this? Yes or no? Clear? Clear? Very good. So under steady state, what happens is temperature of a different cross sections of the rod remain constant with time. So if somebody tells you the temperature of the whole rod is constant, no. Temperature of a particular cross section is constant. Yes, it is correct. Yes, it is correct. That is what exactly is under steady state. So that means this is at 80, this is at 50, this is at 30 degrees Celsius. So for a particular cross section, it is constant, but for the entire rod, it is not constant. Second, heat passing through each cross section of the rod is same. That is exactly. So heat passing through each cross section is the same heat. Same heat is passing. That is exactly. Right. Temperature is not same across the entire rod. One thing that you have to keep in your mind. Okay, people. Very good. Very good. Next, amount of heat transfer or Q. Now this we are going to compare with current electricity over here. Compare with current electricity over here. Okay. So over here, amount of heat transferred is basically the charge in current electricity. The charge in current electricity is basically the Q over here, or the heat transferred over here. Now, what do? I am true from Palakkad. Oh, very good. So basically, this is the rod. This is basically the rod over here. This is the rod, and this is the cross section. This is the cross section over here. This is at temperature T1. This is at temperature T2, and let's assume that this temperature to be at theta degrees. Okay, people, and Q amount of heat is passing through it in time T. And obviously T1 is greater than T2, and this is in steady state. Okay, so the relation that you get is Q is equal to Ka delta T divided by L into T, where T is the time, where T is the time. You will get it in telegram, Pranav. You will get it in telegram. Q is equal to Ka delta T divided by L multiplied by T. Are you all able to understand this? What is K? K is basically the thermal conductivity. Delta T is T1 minus T2. That's it. Is this clear? Is this clear, people? Yes or no? Okay. Now, this K is called as thermal conductivity and is material dependent. That means it only depends upon the material. That means even if you take 2 kilo copper, 2 kg copper, 2 gram copper, 2 ton copper, 2 gram copper, any copper, the thermal conductivity is going to be same. Are you able to understand? It does not depend upon the dimensions. It only depends upon the material. Okay. Next. Now we're going to talk about rate of heat transfer. That means rate of electron moving, something like that. So rate is basically dq by dt. So if you differentiate this equation with respect to time t, you get heat current or H. You get H is equal to heat current. What is the formula that you're getting? H is equal to Ka delta T divided by L. Very clear. Very clear. Very clear. Is this clear, people? Very good. Next, temperature gradient. Okay, you're going to understand temperature gradient. I hope so. It is chamka for all of you. So it is noticed that in steady state, the temperature varies linearly with length. It varies linearly with length. What do I mean by that? That means this is at steady state right now. This is at 100 degrees Celsius, 80, 60, 40. Okay. So as the length is increasing, so this is x is equal to 0 till x is equal to L. As the length is increasing, you are able to see that the temperature is also decreasing linearly. Are you all able to understand this? That is exactly what I am telling over here. So this graph is basically this thing only. So this is x and this is temperature. So as the x is increasing, the temperature is decreasing linearly. Okay, are you able to understand? And this dt by dx is basically the slope. Chamka. Okay, cool. Very good. Next, now we are going to understand thermal resistance. What is thermal resistance? For that, let's revise electrical resistance first. Now this is a resistance R. I current is flowing. Why is it flowing? Due to the potential difference delta V. According to Ohm's law, we can write I is equal to delta V by R. That means due to some potential difference and some resistance, you are getting a current I. Okay, this is exactly the concept that we're going to use over here. In thermal resistance also, we have a rod over here. At steady state. This is at temperature T1, temperature T2, area of cross section A, thermal conductivity as K, and the heat current is basically H over here with length L. So heat current is Ka delta T divided by L. Now people, I want to convert it into this equation. I want some difference divided by R, some difference divided by R. So I know that delta T is the difference over here, and this Ka by L can be written as L divided by K in the denominator. Are you able to understand this? Are you able to understand this? How did we write this? So this K comes into the denominator. So delta T is basically the difference, and L divided by Ka becomes the thermal resistance. Are you able to understand this? Is this chamka for you all? So this L divided by K is the thermal resistance. So H is equal to delta T divided by RTH, and this RTH is basically L divided by Ka. L divided by Ka. Yes or no? Yes or no? Yes. Okay. Now in current electricity, what did you write? In current electricity, it was R is equal to rho L by A. Rho L by A, where rho was the resistivity. But here this is the conductivity, so it's the inverse thing. So it is the inverse thing. So L divided by K, L divided by K, exactly the same formula. Exactly the same formula. Okay. Chale, next move it. Series combination. Now a very important thing. Very, very important thing. If you have two rods, if you have two rods of thermal conductivities K1 and K2, of thermal conductivities K1 and K2, what is going to be the K equivalent? What is going to be the K equivalent, provided the area is also going to be the same? Now we are going to talk about junction temperature as well. Okay. So this is basically the junction where the two rods are going to divide. Now people, is this very much clear that in series combination that the current is going to be same through all the rods? The current is going to be same through all the rods. Hana. So just we have to use the concept of Ohm's law over here. That means the current is H over here. Due to what? Due to the temperature difference. What is the temperature difference? It is theta minus T1. Theta minus T1 divided by R. What is the R? The R1 resistance of this rod. Are you able to understand this? The same current is passing through this rod as well due to the temperature difference. T2 minus theta divided by the R thermal of this resistance, or R thermal of this rod. That is this thing. Both of them are equal. Equate, and you will get theta, and you will get the value of theta. Is this clear? Yes or no? Okay. Now, in order to find K equivalent over here, so this is the equivalent circuit basically. So the length is L1 plus L2. The temperature is T1 and T2. So the equivalent can be written as T1 minus T2 divided by Re. Okay. And resistance are added in circuits. So Re is equal to R1 plus R2. Everything is same. So this is the, when you solve all of this, you will get K equivalent as this formula. Okay, people. And this is the same thing for junction temperature. Are you all able to understand this, people? Okay. Everything I've given it over here. If you have any problems, when we'll solve the numericals, you'll be able to understand it further. Okay, people. And for parallel combination also, it is the same thing, people. In parallel combination, the temperature difference is the same. R equivalent formula is the same. Everything is same. The current gets divided into H1 plus L2, and this is basically the formula that you get for K equivalent with respect to parallel combination. Okay, I've given everything over here. Now let's understand, people, what is radiation. Okay. So what is radiation? Radiation is the process of heat transfer from one place to another without heating the medium. It's a very important thing, people. So whenever you're getting the sun energy, the thermal energy from the sun, it is traveling through the vacuum, but you have to keep in mind that the vacuum itself is not getting heated up. The space is not getting itself heated up. Very important point. No medium is required for radiation as it is electromagnetic wave. Now you all know why electromagnetic wave does not require a medium, because it's a self-sustaining wave. है ना जी? So the varying electric field produces a varying magnetic field. A varying magnetic field produces a varying electric field. That is the reason they are self-sustaining. That is the reason it does not require a medium. Radiation is a mixture of electromagnetic rays ranging from infrared to UV. Some theory, that is something which you all know. Okay. Prevost's theory of heat exchange, a very important theory. Now very important theory, keep in mind. All body emits radiation at all temperatures, a very important thing. That means what does Prevost say? Prevost says no matter what the temperature of the body is, it will emit radiation. It is gonna emit radiation. All body absorbs heat radiations falling on it at all temperatures. Again, a very important thing. No matter what the temperature is, it is gonna absorb radiation. And no matter what the temperature, it's gonna emit radiation. But the intensities or the rate at which it is absorbing or emitting is gonna be different. And that is exactly what the three cases that we're gonna study. What is the three case? That is the amount of emission absorption depends upon the temperature and the material of the body. Exactly. What is it? Now, if the surrounding temperature is greater than the body, so what is happening? I have ice cream over here. Yeah, I have ice cream over here. This is ice cream. This is ice cream over here. So the temperature of this particular thing is less. The surrounding temperature is more. There is a temperature difference. Heat is gonna flow from the surrounding to the temperature. That means this ice cream is gonna absorb more. It is gonna emit, but the rate of emission is gonna be less. The rate of absorption is gonna be more. Are you able to understand? Now, if I take the case of hot tea. In hot tea, what is the case? So hot tea, this is the hot tea. The temperature of this body is greater than the surrounding. So heat is gonna flow from the body to the surrounding. That means the rate of emission is gonna be greater. It's gonna absorb, but the rate of emission is gonna be greater than the rate of absorption. Chamka. Third case, both the temperature is same, surrounding and as well as the body. So no temperature difference, no heat flow. That means it does not mean that there is not going to be any emission or absorption. It's going to be there, but the rate of emission is equal to the rate of absorption. Chamka. Chamka. Everything chamka. That is the reason body temperature is constant. Very good. Now we are going to talk about emissive power. Okay. What is emissive power? Emissive power is basically the heat radiated by the body per unit surface area per unit time. That is basically the emissive power. So how much heat is getting radiated by a particular body of a particular cross section area and in particular time? That is basically the emissive power. So E is equal to Q divided by AT. Now this emissive power is actually dependent upon the lambda and also on the temperature. So for every color you are gonna get this formula, that is E of lambda is equal to Q of lambda divided by area into T. So for every color you are gonna get some emissive power. Okay, so this is basically that formula. This you can keep in mind. Next is absorptive power. What is absorptive power? Absorptive power is fraction of heat absorbed out of the total heat incident. Out of the total heat incident. Again, a very interesting thing. If I give you 10 chapati, I have given you 10 chapati, but you could only eat 3. So what is your absorptive power or your eating power? Your eating power is 3 out of 10. Chamka. This is exactly what absorptive power is. I have given you some joules of energy, but you have only absorbed some fraction of it. That is exactly what is absorptive power is. Chamka. 2 is enough. So fraction of heat absorbed out of total heat incident. That means heat absorbed divided by heat incident. And obviously both of them are heat, so it becomes a unitless quantity. But again, it depends upon lambda. Okay, so A is equal to Q absorbed by Q incident, and again Q absorbed by Q incident. Okay, chamka. Okay, very good, very good. Okay, so yes, let's all people. Chalo, let's solve it fast. Come on, let's solve it fast. Okay. Let's solve it fast. Okay. What is it? Under steady state, the temperature of the body what? Increases with time, decreases with time, does not change with time, is same at all points, does not change with time, but is different at different cross sections of the body. Acha, tell me. So increases with time, nah. Decreases with time, nah. Does not change with time and is same at all points. No. Yeah, option D is your right answer. Option 4 is your right answer. Okay, very good. Okay, next. The two ends of a metal rod are maintained at 100 degrees and 110 degrees Celsius. The rate of heat flow in the rod is found to be 4 joules per second. If the ends are maintained at temperatures 200 and 210 degrees Celsius, the rate of heat flow is going to be what? Acha. So basically, H is equal to, or H1 is equal to dQ1 by dt. They have got Ka. Just a second. So two ends of the rod are maintained. Okay. Okay, yeah. So this becomes Ka delta T divided by L. Okay, Ka delta T divided by L. So obviously the two ends of a metal rod are maintained at temperatures of 100 degrees and 110. The rate of flow. Acha, see this. So this comes out to be 4. This comes out to be 4. Okay, this comes out to be 4. Now K is same because rod is same, A is same, rod is same, L is same, rod is same. So H is only dependent upon delta T. H is only dependent upon delta T. So in earlier case, delta T is 10. In this one also it is 10. So the heat is going to be same. The heat is going to be same. So it's going to be 4 joules per second. That's it. 4 joules per second. Clear? Clear, people? Clear? Very good. Now let us solve, this one. Let us solve junction temperature question. Let us solve a junction temperature question. I've given a lot of questions, people. Don't worry, you can all solve them at home. Okay, you can all solve them at home. If you have any doubts, you can also message me on Telegram. Okay, people. A metal rod of length 2 meter has cross-sectional areas 2A and A as shown in the figure. The ends are maintained at temperatures 100 degrees Celsius and 70 degrees Celsius. The temperature at the middle point is going to be. So this is at 100, that is at 70. So I'm going to assume that this temperature is at theta degrees. This is at theta degrees. So the same amount of heat current H is going to flow. Same amount of heat current H is going to flow. है ना जी? So what can I say? Can I say temperature difference 100 minus theta divided by R thermal. So what is going to be the R thermal for this particular rod? What is R thermal? It is L divided by Ka. What is the length? L is 1 divided by K. Metal has 2 meter cross section area 2A and as shown in the figure the ends are maintained. Temperature of the two metal meter has. Okay, so K is same. So L divided by K. What is area? It is 2A. So this becomes 2A and this becomes theta minus 70 divided by L. What is L? Again this is K and area is A over here. है ना जी? So K gets cancelled, A gets cancelled. This 2 goes to the upper side. So this becomes 200 minus 2 theta, which is equal to theta minus 70. Okay, theta minus 70. So this becomes 270. 270 is equal to 3 theta and this becomes theta is equal to 90. Theta is equal to 90. Okay. Okay, people. Chamka. Oh my God. Christina, so but children comes under the subset of people, right? So it's okay. It's okay. So yeah, that is it. Okay, and okay, let's solve this. 3 rods made up of the same material and having the same cross section have been joined as shown in the figure. है ना? Each rod is of the same length. The left and the right ends are kept at 0 degrees Celsius and 90 degrees Celsius respectively. The temperature of the junction of the 3 rods. So I'm going to assume that the temperature over here is theta. The temperature is theta. So obviously the current is going to flow from here, that this is H and this is H. So how many of you all understand that the current over here and here is going to be same because same potential difference. है ना, the same potential, sorry, same temperature difference, and both of these are going to join over here and form 2H over here and form 2H over here. Okay, okay, so this is basically H plus H is equal to 2H. H plus H is equal to 2H. Okay, so what is H over here? H over here is basically 90 minus theta divided by, that is the temperature difference divided by resistance, L divided by Ka. What is the L? Okay, same cross sectional area and of same length. So this becomes L divided by K into A. L divided by K into A. So this becomes twice. Okay, this becomes twice. This becomes twice is equal to the current over here. The current over here. So this is theta minus 0. Theta minus 0 divided by L divided by Ka. Yes. So just solve it. L divided by Ka and L divided by K gets cancelled out. Okay, people. Okay, so this becomes 180 minus 2 theta is equal to theta minus 0. This becomes 3 theta is equal to 180. This theta is equal to 60 degrees. 60 degrees, and that is your answer. Yes. Okay. Very good. Very good. Very good. Very good. People, oh, sorry, children. So now, yes, my dear friends, we are gonna start. Acha, you have an option. You have an option. You have an option of. Okay, let's start with thermo. Let's start with thermo. That's what we are gonna do. Okay, let's start with thermo. Okay, people, are you all ready for starting thermodynamics? Are you all ready for starting thermodynamics? Yes or no? Yes. Are you all ready for starting thermodynamics? Yes, thermo. Yes, let's go. Thermodynamics. Okay, thermodynamics it is. Okay, people. So what I'm planning is. So what brightness low? Yeah, I've increased it. So what I'm planning is that we'll complete all the theory as soon as possible. Okay, and then whatever time we left. Okay, whatever time we have. Sir, answer is 30 degrees. Okay, answer is 30s. No, I guess it's 60. It has to be 60. Let's see. So after thermals, we are going to do solids, fluids. Okay, people. So first we are going to do thermodynamics, then we are going to do KTG, then we are going to do solids and fluids, and then we are going to do SHM and waves. Okay. So first we'll do all the theory that is possible, and we'll complete all the formulas that is required, and then we'll do all the question practice that is required. Okay. मोस्ट एक्सपेक्टेड आएगा भाई, माशी टेंशन मत लो, आप गलत चैनल पे आ गए हो. I teach in NEET alchemy. Okay, चलो, let's start with thermo. Okay, चलो. Okay, people. So I often get this question that, sir, what is thermal equilibrium? What is thermal equilibrium? So many people say thermal equilibrium is that state in which the temperature is constant or the temperature is same for both the bodies. I would say, okay. That is actually a half correct definition, I would say. Okay, half correct definition, I would say. Okay, because thermal equilibrium, when you are saying the temperature is same for both the bodies, okay, both the bodies, है ना, both the bodies. So you are using two bodies over here, but thermal equilibrium for one body, the definition is totally different. I'll explain why. Okay, now there are something called as macroscopic properties. Now what are these macroscopic properties? Now for a particular system, now for example, I'll just show, है ना. So this is your Aadhaar card, है ना, this is your Aadhaar card. Now this Aadhaar card has your name, your date of birth, your Aadhaar card ID, है ना, your ID, your address, your QR code and everything. It does have everything. So this basically defines you as a person. Am I right? Yes or no? है ना? This basically gives all, sir. Okay, this basically gives all your. Okay, this basically gives all your information. This basically defines you as a person, है ना? So macroscopic properties basically Macroscopic properties are those properties which actually define a system. So if I have a system over here, and I'm basically saying it has some pressure P, it has volume V, it has number of moles this much, it has temperature this much, the mass is this much. So basically I have defined the system over here. So macroscopic properties are basically the Aadhaar card of the system by which you can define a system. Is it clear? So macroscopic properties like pressure, volume, number of moles, mass, temperature are constant and don't change with time. So thermal equilibrium, okay, thermal equilibrium when it comes to your one body, it is basically at that state in which your macroscopic properties like pressure, volume, temperature, number of moles, mass, they do not change with time, is called as thermal equilibrium. Chamka, everybody chamka. Everybody chamka. Yes or no? Very good. Now, a body is said to be in thermal equilibrium with its surrounding if it is insulated completely. A very important statement. A very important statement. Okay. Now, let me explain this. Now, this is an isolated system. What do I mean by isolated system? This is a gas system. This is a gaseous system. I have surrounded this with a wall, with an insulating wall. Now, whenever I'm going to use insulating wall, I'm going to use a term called as adiabatic wall. What is adiabatic wall? Adiabatic wall is basically no exchange of heat is going to take place. Delta Q is equal to 0. Delta Q is equal to 0. No exchange of heat is going to take place. Okay. So this system is an isolated system. Okay, people. I hope so. I'm very clear. Now let's talk about two bodies are in thermal equilibrium. Now what I'm going to do is, this is one gaseous system. This is the second gaseous system. Okay. This whole system is surrounded by an adiabatic wall, and both of this system are differentiated with a conducting wall over here, which allows heat transfer to take place, or it is also called as a diathermic wall, Is it clear? Now, what happens in diathermic wall? Obviously, this system has the Aadhaar card as P1, V1, T1 or the macroscopic properties, and this system has the Aadhaar card as P2, V2, T2. Okay. Now, due to the temperature difference, as T1 is greater than T2, heat is going to flow from A to B, Now, till what time it will flow? It will flow till the temperature becomes same. So earlier it was P1, V1, T1, P2, V2, T2. After the flow of heat takes place, when will the flow of heat will stop? When the temperature becomes constant or same. That is P dash, V dash. So the pressure volume is going to change, but the temperature is going to be same in both the cases. In this case, you can say both the systems are in thermal equilibrium with each other. Clear? Chamka. Okay, very good. Next. Zeroth law of thermodynamics. Zeroth law of thermodynamics, or what I call is the brother-sister law. Brother-sister law. So what does brother-sister law says? Brother-sister law basically says, if A, B, C, if A and B are brothers and sisters, if A and B are siblings, if B and C are also siblings. So can I basically say A and C are also siblings? This is exactly Zeroth law of thermodynamics. Are you able to understand? If A and B are siblings, B and C are siblings, so that also makes A and C also siblings. That is exactly what Zeroth law of thermodynamics. Okay. So I'll explain this. What is exactly happening? What is happening exactly? So I have a system over here, A, B, C. A, B, C over here. Okay. First of all, what I have done is that this is a adiabatic wall and this is a conducting wall. And due to this being a conducting wall, A and C are going to exchange heat, B and C are going to exchange heat. A will be in thermal equilibrium with C after some time, B will be in thermal equilibrium with C after some time. Then what I do, I exchange the walls. I convert this conducting wall into adiabatic wall, and I convert this adiabatic wall into diathermic wall, into conducting wall. But what you notice over there is that there will be no exchange of heat taking place, because both A and B are in thermal equilibrium with each other. So as A is in thermal equilibrium with B, B is in thermal equilibrium with C, so A and C are also in thermal equilibrium with each other. Chamka. Okay. Is this clear?
Is this clear?
Very good. So zeroth law is also done. Now we are going to talk about internal energy. Now we are going to talk about internal energy. Okay, people, let's talk about internal energy. Okay, now what is internal energy? Now, people, when somebody talks about internal energy is basically due to the potential energy. Now, very important statement. Potential energy of the gas molecules. Gas molecules is a very important term. The sum of potential energies and kinetic energy of the gas molecules is basically the internal energy of the system. Am I clear? Now, why is this potential energy of the molecules a very important term? Now, before coming back to that, why does potential energy takes place? Potential energy basically comes due to the intermolecular forces of attraction. Is this clear? It is basically due to the intermolecular forces of attraction. You must have all studied the equation F is equal to minus du by dx. If force is there, obviously potential energy is there. So, due to the intermolecular forces of attraction, you are getting potential energy. Now, why kinetic energy? Kinetic energy, again, the gas molecules are moving randomly over here and there, and due to that, the kinetic energy is happening over there. Kinetic energy, you are getting kinetic energy over there. So, due to the motion of the molecules, you are getting kinetic energy. Now comes the very important statement. Now, for example, if I have a container over here which is filled with gas molecules. Now, this container, I have given it some v velocity. Now, obviously, the kinetic energy of this whole thing will be half mv square. But should we include this half mv square in the internal energy equation? No, you should not. What did I say? I already said that potential energy of the molecules, gas molecules, kinetic energy of the molecules, internal energy is only for the gas molecules. This kinetic energy is an external kinetic energy. This you cannot include in the internal energy. But if somebody asks you, what is the total energy of the system? The total energy of the system is going to be the internal energy of the gas molecules plus the external energy. Is this clear? Is this clear? Very good. Okay. Next. Now for an ideal gas at rest, now there are some assumptions that we'll also study in KTG, but I'll already tell you what are the assumptions. The first assumption is that obviously we are going to take ideal gas. What is ideal gas? In ideal gas, we do not consider any forces of attraction between the gas molecules. So if there is no forces of attraction, there is no potential energy. There is no potential energy. A very important point over here. Very important point. So the total energy is basically equal to the internal energy. Why? Because the potential energy is zero. Only kinetic energy of the gas molecules is there. Because in ideal gas, we consider that there is no intermolecular forces of attraction. Clear? Chamka. Chamka. And that is the reason you get the internal energy of the gas to be equal to the kinetic energy of the gas. Chamka. Is this clear? Is this clear, people? Yes. Let's move ahead. Now we are going to talk about degree of freedom. Okay, now we are going to talk about degree of freedom, one of the most confused topics in thermodynamics, because many of you all have I don't know Vedant, I don't know. Okay, because many of you all are not able to understand what exactly a degree of freedom means. Okay, so these are some of the definitions that are given in Google. Okay, these are some of the definitions that are given in Google. Let's read it out. Okay, let's read it out. The number of independent terms in the expression of kinetic energy degree of freedom. The number of independent terms in the expression of kinetic energy not dependent on each other. Now, when you all read this statement for the first time, you all be like, "Ye kya ho gaya? Sir, how many chapters will be covered?" Praveen, I've already told you, complete thermal physics, then solids, fluids, then SHM and waves. Okay. So now what exactly is this? I'll tell you. Okay. So this is exactly what I've written. I've written in English. I'll basically explain you. सारे मोशन को काउंट नहीं करना, ओनली उसका जिसका काइनेटिक एनर्जी कंसिडरेबल हो. Now what do I mean by that? Now what I mean by that is basically that you do not have to count every motion. You just have to count those motion. You just have to count those motion whose kinetic energy is considerable. It can be considered. It can't be considered negligible. Are you able to understand? Those motion which are considered amount of kinetic energy, only those motion you have to count. Are you able to understand this? I'll help you explain this. Now, a molecule, a gas molecule can have three, sir, please tell electromagnetic wave. Which electromagnetic wave? Okay. So it can possess three types of motion. First is the translation motion. What is translation motion? X axis, Y axis, and Z axis. This is a translational. Rotational. It can rotate something like this. It can rotate something like this, like this, like this, and like this. So these are the three type of rotation. And then vibrational also. Vibration also. That is not something that you have to study in detail. Okay, that is not something that you have to study in detail. Okay, let's move ahead. Now let's talk about monoatomic gas. Now these are some of the examples of monoatomic gas: helium, neon, argon, and everything. Okay, now I'll basically help you visualize why are you getting degree of freedom as 3 for monoatomic gas. You will be like, wow. Okay, you will be like, wow. See this. This is a monoatomic gas, one atom. Obviously, it can travel in X, it can travel in Y, it can travel in Z. That is the reason it has 3 translational degrees of freedom. Now coming back to rotational. Why only rotate? Why zero rotational? Now in KTG, in ideal gas, you have already assumed that this to be a ideal gas system. And in ideal gas, the gas molecules are considered as solid spheres. Solid spheres. So this is a solid sphere. If I want to calculate the kinetic energy, that is the rotational kinetic energy. What is the rotational kinetic energy? Half I omega square. Half I omega square. So half I omega square, what is the moment of inertia? I 2 by 5 mr square, 2 by 5 mr square. Now people tell me this radius is a very small thing. It's a very small thing. And if you're squaring it, it already becomes more small. It becomes more small. So that means the kinetic energy with respect to the rotation is very small. It cannot be considered. That is the reason you are not considering for rotational. You're not considering it for rotational. Are you able to understand it? Are you able to understand this? Why only 3 translational and no rotational? Chamka. That is the reason 3 translational, 0 rotational. So degree of freedom is 3. Now, when do we have to use vibrational? Only when in the chapter, only when in the question it gives higher temperature. At higher temperature, whenever you get this thing, you just have to add +2 to this degree of freedom. You will get it as 5. Okay. Chamka. Very good. Coming for diatomic. Again, O2, H2, N2, everything. So obviously it can travel in X, Y, and Z. So 3 translation is pakka. Now coming back to 2 rotational. So over here, if you all notice, this is O, this is O. It can rotate something like this, and obviously this time it's going to have rotational kinetic energy also, because it's going to have some distance. So this is valid. This is also valid. But this thing, like this rotation, no, it's not valid. Like this rotation, it's not valid. Are you able to understand? See, because in this rotation, again, the radius is very small. That is the reason this cannot be considered. The kinetic energy is negligible. So only 2 rotational degrees of freedom. So 3 translational, 2 rotational, F is equal to 5. Okay. And at higher temperatures, just add +2, you will get F is equal to 7. Okay. Clear people? Everything is clear? Yes or no? Everything is clear? Yes or no? Clear? Very good. Polyatomic gases. Okay, polyatomic gases. Yes, you can ask something to me. So CO2, SO2, and everything. Okay. Now, obviously, in polyatomic, you must have studied in chemical bonding. Obviously, that is linear molecule and non-linear molecule as well. है ना जी? So आप IPL देखते हैं क्या? हाँ, obviously. Okay. So linear molecule is not considered in NEET, but obviously we'll just take a quick look. Over here. Okay. So linear molecules, so CO2 is a linear molecule. Obviously, it does not have any lone pair. That is the reason it does not have any lone pair, and that is the reason it is a linear molecule. So linear molecule such as CO2 obviously is going to have three translational and only 2 rotational, because over here it cannot rotate in this way, it is a negligible kinetic energy. So 3 rotational, 3 translational, 2 rotational and 2 vibrational degrees of freedom when it comes to higher temperature. Okay, now coming to non-linear. SO2, it has a bent shape, है ना जी, it has a bent shape. Christina Yavar sir has already taken class 12th. Okay, so non-linear SO2 has a bent shape due to the lone pair. It has bent shape, है ना. So over here you have to understand it has 3 translational X, Y, Z, also 3 rotational also. It also has 3 rotational. So the degree of freedom comes out to be 6. But at higher temperatures it is F is equal to 8, because you just have to add +2. Chamka. Okay, clear. Let's move ahead. Now we are going to understand law of equipartition of energy. Okay, now very important statement. The kinetic energy average, or the average kinetic energy associated with each degree of freedom of a molecule is half kBT. What is K? KB? What is KB? Okay, so now KB is basically Boltzmann constant. Now, as many of you all are South Indian students, I'm gonna give you an acronym which you can all remember. Okay, that is basically R is equal to NAK. Okay, R is equal to NAK. Okay, NAK. है ना, tongue, है ना जी. So in many of your South Indian languages, NAK is basically tongue. है ना? So this is the acronym that you should remember. Okay, R is equal to NAK. Okay, R is equal to NAK. If now I don't think so you will forget now, है ना? I don't think so you will forget now. Yes, so R is basically the gas constant. Acha, lick in Telugu. Okay, so no issues. So R is ideal gas equation constant, Na is Avogadro's number, and Kb is the Boltzmann constant. Yes, tongue in Tamil, exactly. Okay, so that is exactly that I want to say. Now what do I mean by this? That means each degree of freedom corresponds to half kBT of kinetic energy. Okay, what did I say? That each degree of freedom corresponds to half kBT of kinetic energy. That means if I'm talking with respect to monoatomic gases, what is the kinetic energy? For each degree of freedom, half kBT. So for 1 it will be half kBT, for 2 it will be 2 times of half kBT, for 3 it will be 3 times of half kBT, and that is the kinetic energy of monoatomic gas, 3/2 kBT. Are you able to understand this? People? So now see, look over here. Now I am not, are you Tamil Nadu? No. Okay, see this, okay, see this, very important. If one molecule, if you are talking about one molecule, it has 1 degree of freedom, and if it has 1 degree of freedom, each degree of freedom corresponds to half kBT. So the kinetic energy is half kBT. Okay, very good. Now if one molecule has F degrees of freedom, so it has F/2 kBT kinetic energy. Yes, this is enough. Yes, I'm not from Tamil Nadu, I'm from Kerala. Now if one molecule with F degrees of freedom, it has kinetic energy F/2 kBT. Now I want to find out 1 mole of a molecule. Now if one molecule is this much, I want to convert it into 1 mole. I just have to multiply it by Na. So 1 mole of a molecule is basically Na times of F/2 kBT. Now I have already told you what is NAK. NAK is basically R. So Na into K becomes R. So 1 mole of a molecule with F degrees of freedom is F/2 RT. Chamka. Is this clear? How did it came to? Now, so kinetic energy of 1 mole of an ideal gas is F/2 RT. And if I want to talk about n moles, just multiply it by n. So it becomes n F/2 RT. That's it. Now this is something which people or which children often found confusing. Often found confusing, but it's very easy to understand. It's very, very easy to understand. Okay. Cool. Now let's move ahead. Let's talk about internal energy and change in internal energy. Let's talk about internal energy and change in internal energy. Okay. Now, people, in ideal gas, if I'm talking with respect to ideal gas, obviously potential energy is not there. If I'm talking about n moles of gas, I know the internal energy is going to be equal to the kinetic energy. है ना? So internal energy is equal to kinetic energy, and just now we calculated the kinetic energy is nF by 2 RT. nF by 2 RT. The change in delta, the change in internal energy, that is delta U, is going to be change in kinetic energy, which is now nF, R and 2 are all constant, so it comes out and T gets differentiated, so this becomes delta T. This becomes delta T. So delta U is equal to delta K, which is equal to nF by 2 R delta T. Chamka. Chamka, people. Is this absolutely clear? Is this absolutely clear? Now you have to keep in mind that U and delta U, obviously NFR2 are all constants, exactly. So you have to keep in mind and you have to understand that U and delta U is only dependent upon temperature and delta T respectively, Very good, very good. Okay, now we are gonna understand. This is a very important slide. This is a very, 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 very important slide, people. Okay, very important slide. Let's understand. Now we have already talked about specific heat capacity. Specific heat capacity is the amount of heat required by the body to increase the temperature by 1 degree centigrade, and also the mass should be 1 unit mass. So delta Q is equal to MC delta T. This is which we are very, very, very clear about this. Very clear. What is molar specific heat capacity? Molar specific heat capacity is the amount of heat required to increase the temperature of 1 mole of a substance by 1 degree. That is the reason I have not divided by mass. I have divided by number of moles over here. Am I clear over here? So C is equal to delta Q divided by N delta T. Now, this N, number of moles, can be written as given by my molar mass. That is basically number of moles formula. So I have given mass divided by molar mass. So M naught is basically the molar mass over here. Hai na? Now this M naught goes to the numerator. So this is the formula that we get. Now what is this formula, people? This delta Q divided by M delta T. Are you all able to understand? This is the specific heat capacity. So can I basically write that capital C, which is basically the molar specific heat capacity, is equal to M naught times small c, that is the specific heat capacity. Chamka, a very, very, very important relation. This is the mole wala, this is the mass wala. So okay, thank you, Simi. This is the mole wala, which is equal to molar mass times the mass wala. Very important relation. Very, 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 very important relation. Okay. Now, when it comes to molar specific heat capacity, they have two variations of it. One is at constant volume and one is at constant pressure. At constant volume, you call it as CV. At constant pressure, you call it CP. At constant volume, it becomes delta Q is equal to NCV delta T. And at constant pressure, delta Q is equal to NCP delta T. I don't think so. It's a problem for you all to understand. Okay. Okay. Now, this note is one of the most important notes in the history of physics. Okay. You have to keep this in mind. I'm not going to the derivation part of it. I'm just going to say that you need to know this. What is it? The value of CV is basically F by 2 times of R, where F is the degree of freedom. The value of CP is just addition plus add 1 to this. So F by 2 plus 1 into R. That is CP for you all. Okay. CP minus CV for any ideal gas is equal to R. And the ratio of CP by CV is basically gamma. We'll talk about gamma, don't worry, or it comes out to be 1 plus 2 by F. Very important. CV is f by 2 into R, Cp is f by 2 plus 1 into R, Cp minus Cv is R, and Cp by Cv gamma is equal to 1 plus 2 by f. Now people, now this Cp by and this Cp and Cv, this is the mole wala. This is the mole wala, not the mass wala. Okay, this is the mole wala. Okay, clear? Okay, let's move ahead. Now let's calculate gamma. Let's calculate gamma. Now people, this 1 plus 2 by f can also be written as f. So this 1 can be written as f by f. So f by f is basically f plus 2 divided by f. That is what I get over here. So you can calculate gamma with this formula as well. Now for monoatomic gas, the degree of freedom is 3 translational. So what is gamma? 3 plus 2 divided by 3. So that is 5 by 3. That is the monoatomic that you get. Okay. Next, for diatomic 3 translational, 2 rotational, 5 is the degree of freedom. So 5 plus 2 divided by 5, that is 7 by 5. Khatam. Polyatomic. What is polyatomic? 3 translational, 3 rotational. Sorry, 3 translational, 3 rotational. That is 6. So 6 plus 2, 8 divided by 6, 4 by 3. Answer. Chamka. Okay. Now, this is also a very important thing. How now we need to find the value of Cp and Cv in terms of R and gamma. We know that Cv is equal to f by 2 into R. Hai na? We also know the value of gamma is equal to 1 plus 2 by f. Now over here, see this. Over here, what happens is, we know that Cv is equal to f by 2 times of R. Hai na? We also know gamma is equal to 1 plus 2 by f. This minus 1 is equal to 2 by f. I'm going to reciprocate. I'm going to use this equation. Over here. So this becomes Cv is equal to value of f by 2 1 minus gamma R divided by gamma minus 1. Are you all clear? How did we get this equation? Yes or no? Are we all clear how did we get this equation? That is how we get it. Cv is equal to R divided by gamma minus 1. Okay. Very good. Now, I need to find it with respect to Cp as well. But we know Cp by Cv is equal to gamma. We already know the value of Cv, that is R divided by gamma minus 1. So Cp is gamma times of Cv. So gamma times the value of Cv, that you get is gamma R divided by gamma minus 1. Yes. Clear. Now let's understand. Okay. Now just tell me people, how many of you, okay, we have approximately 60 people watching. How many of you all have confusion regarding thermodynamics with respect to physics and chemistry? How many of you all have this confusion when it comes to physics and chemistry, thermodynamics with sign? Okay, how many of you all have? Me? I thought to skip it. Christina, Joshua, Tina, yeah, everybody. Okay, I'm gonna teach you chemistry as well. Don't worry. Okay, I'm gonna teach you chemistry as well. Okay, see this, not me. Okay, no problem. See this. Yeah, signs are the major problem. See this slide. After this slide, you will not have any problems with chemistry as well. You will not have any problems with physics as well. Okay. So see, the major difference between physics and chemistry is basically the approach, or basically the frame of reference in which you are sitting. Hai na? So you can use the concepts of physics to solve physics numericals. You can use the concepts of physics to solve chemistry numericals. The only difference is that you will get the sign as opposite. Now I'll tell you why. Okay. Now, has anybody questioned why sir, why in the hell is work is equal to P delta V? How? Why is P delta V is equal to work? Why? It's a very easy why. Why? See this. Work is equal to P delta V. Hai na? I can write this as force divided by area, pressure as force divided by area, and volume I can write it as area into height, area gets cancelled, I get F into H. This is exactly work. This is exactly work. Now you know why work is P delta V. Now you know why P delta V. Okay. Now you know why work is P delta V. Okay. That is clear. That is clear. That is clear. Okay. Now work is P delta V or P into V2 minus V1. Okay. You can only use it, or it is only valid when pressure is constant. You can only use it when pressure is constant. Okay. So is there any other formula that you can use anytime, even if the pressure is constant or volume is constant? Yes. The formula is work is equal to integration of pressure into P into dV, and the limits goes from V1 to V2. Okay. Now coming to the sign. Now coming to the sign. Okay. Now coming to the sign. See this. See this, okay, people? I have gas inside. I have gas inside, people. So this gas has an internal pressure. It's gonna exert force due to this. So the pressure inside the gas is gonna exert force on this piston, and due to this, it is gonna expand. Are you able to understand this, people? Are you able to understand this, people? That force, this is the pressure. So force is in this direction. It's gonna expand. So people, tell me, the force is in this direction, the displacement is in this direction. What should be the value of work? What should be the sign of work? What should be the sign of work? Force here, displacement here. What should be the value of work? Sign of work. Tell me, this is the most easiest question of work, power, energy. Joshua, how is it negative? Force here, displacement over here, work should be positive. That means for expansion, work is positive always. Always. Understood? Now, so now, but if the force, now in physics, we are going to talk about internal only. Okay, we are going to stay inside the system. We're going to stay inside the system. So the pressure is over here, force is over here, but the gas is getting compressed. So force is here, displacement is over here. Both of them are in different directions. So for compression, work is going to be negative. Chamka. Now comes the chemistry thing. Why do we get confusion in chemistry? In chemistry, we are out of the system. We are out of the gas. We are outside. We are talking about the external pressure. Okay. So in chemistry, this is the external pressure, this is the external force, but it is expanding over here, the displacement is over here. That is the reason in chemistry you are getting the expansion as negative. Chamka. And for compression, see, the pressure is over here, force is over here, compression, the displacement also is over here. Compression is positive. Chamka. Clear? Sorted? Yeah, is the sign convention sorted? Yes, good. So see, sign convention with respect to physics, work is equal to P delta V. है ना? If the delta V is positive, obviously work is positive. What is delta V positive? Expansion. So work done is by the gas. Okay. Now delta V is negative, that is compression is taking place. So compression, work done on the gas, so it is negative. Okay, clear. Very good. Now work done by the PV curve. Okay. Okay, work done by the PV curve. Again, so this is the formula that we know. So the area under the curve of P and volume will give you the work done. Okay, will give you the work done. Thank you, Sonali ma'am. Yes, thank you, Sonali ma'am. Okay, will give you the work done. So basically, if this is the curve, this is V1 and this is V2, the area under this will give you the work done. Okay, people. Chalo ji, let's move ahead. Okay, now we are going to talk about work is path dependent, not a state function. Exactly. Okay, so let us understand this. Let us understand this. Work is path dependent. It is not a state function. Now, many of you will be like, yes, what is the state function? What is the state function? State function is a type of function which only depends upon the initial and the final position. Which only depends upon the initial final position. Let me just elaborate. Let me just elaborate. Now, work is path dependent. What do I mean by that? If this is the PV curve, this is A state, this is B state. Now, there are three ways of reaching this A to B. There are three ways of reaching A to B. The first one is a straight line. This is the second one, and this is the third one. Okay. Now, what did I say? The work done is basically the area under the curve. The area under the curve. Now, are you all able to understand? The maximum area will be for the first one. Maximum area will be for the first one. Then for the second one. Then minimum for the third one. Are you all able to agree? Are you all able to agree? So you are getting work done by 1 is greater than work done by 2 greater than work done by 3. That means work is path dependent. It depends upon the path that you're taking. Even though the initial and the final state is the same for all the three cases, but the path is different, the area is different. That is the reason the work is different. The work is different. Chamka. Now coming back to work done in cyclic process. Work done in cyclic process. What is work done in cyclic process? Now this is PV, and this is a cyclic process. Now what is a cyclic process? You start from a particular point, you come back to that particular point. That is basically a cyclic process. Now in cyclic process, you have to keep in mind that if the cycle is clockwise, then you have to take it as positive work. If it is anti-clockwise, you have to take it as negative work. Okay, clockwise is positive, anti-clockwise is negative work. Okay, and what is the work done? Work done is basically going to be the area under the curve. Area under the curve. I hope so I'm clear. I hope so I'm clear over here. Okay, I hope so I'm clear. Chalo, let's go. Now I'm going to talk about okay, now I'm going to talk about now I'm going to talk about internal energy. What is internal energy? Again, potential plus kinetic energy of the molecules. But for an ideal gas of n moles, potential energy is 0. It comes out to be U is equal to NF by 2 RT, and kinetic energy. This is something which I have to tell people. मेरा टेलीग्राम चैनल आप जॉनथन मैथ्यू फिजिक्स आप कर सकते हो, ठीक है. I've already told you that the value of CV is F by 2 into R. F by 2 into R. So I've just substituted the value of F by 2 into R over here. It becomes basically NCVT over here. Okay. And if I want to change, it becomes NF by 2 R delta T. Delta KE is equal to NCV delta T. Okay. Now, a very important statement. The statement is, this is valid for any process, and I mean any process, whether it's isothermal, adiabatic, anything, isobaric, anything, doesn't matter. Even if the pressure is constant or not, even if the volume is constant or not, even if the temperature is constant or not, doesn't matter. The value of delta U is gonna remain NCV delta T. The value of delta U is gonna remain NCV delta T. Clear? Doesn't matter. Doesn't matter what is the process. Every time it's going to be NCV delta T. Every time. Okay. Now let's talk about U. Okay, let's talk about U. Now for ideal gases, U is a state function. That means, what did I discuss about state function? State function is a function which is dependent upon the initial and the final point. It is dependent upon the initial and the final point. It is path independent. Work was path dependent, but it is not a state function. But U is a state function and it is path independent. Am I right? Am I clear? U only depends upon the temperature and delta U depends only upon delta T. That is something which you have already looked. Okay, that is something which you already looked. Now, delta U is path independent and delta U is in a closed cycle is 0. I'm going to prove this point. With the help of this graph. What does this graph say? Now this graph, again we have PV curve, we have A and B over here, we have A and B over here. Again there are three methods of going over here, three methods of going. Now if you all notice, delta U is only dependent upon delta T. Delta U is only dependent upon delta T. So over here, the temperature is T1, over here the temperature is T2. Irrespective of the path you take, the delta T is always going to be T2 minus T1. It's going to be T2 minus T1 for any process, right? So the value of delta U is same. The value of delta T U is same for any process. Are you all able to understand this? That means it does not depend upon which path you take. It does not depend that you're going flying or you're going sleeping or you're walking or anything. Does not depend upon the path that you're taking. It is only dependent upon the initial and the final point. If both the points are same, then the delta U is going to be same. Are you all clear? Are you all clear? Now coming back to this statement, why delta U in a closed cycle is 0. Now in a closed cycle, if I'm starting from A, coming back to A has temperature T1. It has come back to A. What is delta T? T1 minus T1, 0. That is the reason delta U is 0 for a cyclic process. That is the reason delta U is 0 for a cyclic process. Are you all chamka? Chamka? Yes or no? Duration, let's see, Christina, let's see. I'll try to finish as soon as possible. Okay. Now people, see this. This is one formula that you have to keep in mind. You all know that delta U, see, for this process, okay. So from going from A to B, in A it has P1, V1, T1. है ना? It has A1, P1, V1, T1. Yes. And in B it is P2, V2, T2. So it has three methods of going. First, second and third. है ना? Now the delta U is going to be same for everything because again the initial and the final positions are same. So delta U comes out to be NCV delta T. CV can be written as F by 2 into R. है ना? Delta T can be written as C2 minus T1. I multiply this, you get something like this. Now in ideal gas equation, you know nRT2 can be written as P2 V2. nRT1 can be written as P1 V1. So this is one formula that you get when you want to find out the internal energy, change in internal energy when the pressure is given, when the pressure and volume is given. Okay, cool. I hope so this is clear. Heat. We're going to talk about heat right now. Okay, we're going to talk about heat right now. Okay, let's talk about heat. Now people, heat, it is not a state function. Heat is not a state function. Okay, it's not a state function. So heat given to the system is taken as positive. Heat given by the system or the gas is negative. So if it's an exothermic reaction, so heat given by the system is negative. है ना? If the system releases heat, it's negative. If you are giving heat, it's positive. Clear? Chamka. Okay. Now let's talk about FLOT or first law of thermodynamics Okay. Now what is first law of thermodynamics? Again, it is a statement of conservation of energy, that energy can neither be created nor destroyed. It can only be transferred from one form to another. है ना? So what is it? People, very easy. Very easy. Okay. Can I basically say, see over here, I have given heat over here, so I have given some heat delta Q over here. Because of this heat, the temperature inside the gas molecules is increasing. The temperature is increasing, that is delta T is increasing. Delta T is increasing, that means the delta U is also increasing. And delta U is increasing. Why delta U is increasing? Because the gas is oscillating more. And it is going insane. The kinetic energy is also increasing. Kinetic energy increasing, delta U also increasing. So some part of delta U is going into changing the internal energy as well. Okay. And while this is happening, the gas is also expanding. So work is done by the gas. So plus W. Are you all able to understand this relation? How did we come across this? So delta Q is equal to delta U plus W. That is exactly what you're getting over here. Okay. Now the types of processes. We are going to study the types of processes. Types of processes. Isobaric, pressure is constant, bar. Core or isovolumic, it is also called as isovolumic, volume constant. Isothermal, temperature constant. Adiabatic, delta Q is equal to 0. These are some of the processes. Okay. Okay, very good. Next. Now we are going to talk about isobaric process. Now we are going to talk about isobaric process. Okay. Let's talk about isobaric process. Now in isobaric process, the pressure is constant. Now in pressure is constant, you have to look this. If you use the ideal gas equation, PV is equal to nRT, pressure is constant, so I can write it as V is equal to nR by P into T. So this whole fellow is a constant, so V is directly proportional to T. So that is exactly this called as Charles law also. It is also called as Charles law. Now an isobaric process, the pressure and volume, the pressure is constant, so obviously you will get a linear curve. Volume and temperature, you will get a linear curve passing through the origin because V directly proportional to T. Okay. And in P and T graph, you will get again a straight line because pressure is constant. Okay. Now, this is a very important thing. This is a very important thing. If you want to calculate molar specific heat capacity at constant pressure, that is Cp, value of Cp, can anyone say how long this class goes? I don't know, Brinda. Let's see. I'll try to finish it as soon as possible. Okay. So specific heat capacity comes out to be F by 2 plus 1 into R. That is the value of Cp. We have already covered this. And the value of Cp is also gamma into R divided by gamma minus 1. I don't think so. Yes, let's see. Probably till 5. Yeah. I don't think so. Nobody has any problem understanding this because I've already derived this. Yes. Next, delta Q is NCP delta T. And I've already told you, no matter what the process is, the value of delta U is always going to be NCV delta T. Chamka. Yes or no? People, I want the likes to increase. Okay. So is this all clear? Very good. Now coming back to work done. What is work done? From first law of thermodynamics, you can write delta Q minus delta U. Value of delta Q is NCP delta T. Delta U is NCV delta T. N delta T comes out to be common. Cp minus Cv is R. So work done for isobaric process is nR delta T. That's it. You don't have to remember all of these formulas. You can just derive it. Okay. You can just derive it. Okay. Next, isochoric process. So the volume is constant. Volume. Okay. The volume is constant. Now obviously PV is equal to nRT, V goes to the other side, so nR by V is a constant, so P is directly proportional to temperature. This is what you are getting. So volume is constant. So the PV curve, obviously volume is constant, so this is the graph that you are getting. In VT curve, volume is constant, so this is the graph that you are getting. And in PT curve, this is the graph that you are getting because P is directly proportional to temperature. Okay, cool. Next, molar specific heat capacity at constant volume, Cv. The value of Cv is F by 2 into R, or F by 2 can be also written as R divided by gamma minus 1. Again, we have already derived this. Delta Q is equal to NCV delta T. Delta U is NCV delta T. Now, work done will be 0 because there is no change in volume, no displacement, no work. Work is equal to 0. Or you can also do work is equal to delta Q minus delta U. It comes out to be 0 again. That's how you get it. So for isochoric or isovolumic, you get work is 0. That's it. Chamka. Now we're going to talk about isothermal. Now isothermal and adiabatic are very important to understand. Very important to understand. Okay, people. Very important to understand. Isothermal. Now whenever you get this term, very slowly and perfectly conducting boundary, whenever you get these two phrases, okay, you have to understand it's an isothermal process. Okay. So the temperature is constant. So if the temperature is constant, if you use the ideal gas equation, that is PV is equal to nRT, So the temperature is constant. So you get P is directly inversely proportional to volume. That is something which you're going to get. Okay. That is something which you're going to get. Okay. So P is inversely proportional to volume. So obviously this corresponds to a rectangular hyperbola. है ना? So this is P, this is V, and this is the rectangular hyperbola that you're getting. This is for temperature T1, this is for temperature T2, this is for temperature T3. Okay. Okay. Now let's understand. Now these curves have a special name. They are called as isotherms. They are called as isotherms. You'll get it in the Telegram. You'll get it in the NEET English group, Sotej. Okay. Okay, people. Yeah. So isotherms, they are called as isotherms. Now what is the speciality of these isotherms? The speciality of this isotherm is this is isotherms, same temperature. That means anywhere on the curve, you'll get the same temperature as T3. Anywhere on the curve, you'll get the same temperature as T2. Anywhere on the curve, you'll get the same temperature as T1. That is exactly what I mean by isotherm. Over here, temperature T3 is greater than T2, greater than T1. All clear? All clear? Yes or no? Yes or no? Now, the slope of PV or isothermal curve comes out to be minus P by V. That is dP by dV comes out to be minus P by V. A very, 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 very important thing. A very, very important thing when it comes to your exams. Okay, cool. Next. Now, okay, now we're going to talk about the graph. The VT graph, obviously the temperature is constant, so it's going to be something like this. Temperature constant, it's going to be something like this. Okay, so this is very easy. Now, molar specific heat capacity. Now, it's neither constant volume, neither constant pressure. So it's just molar specific heat capacity. What is molar specific heat capacity? Delta C is equal to delta Q divided by N delta T. Now, it is isothermal, that is delta T is 0. That means this denominator becomes a 0. If this denominator becomes 0, the whole thing will become infinite. It will become infinite. That means molar specific heat capacity for isothermal is infinity. Does not change. We have already looked this in this thing. Where is it? This just like Marvel movie. I have already told you about this. Yes. See this. Body specific heat capacity infinity, heat reservoir temperature constant. I've already talked about this. Yes, question. Yes, exactly, Prakhar. Okay. Okay. Next. Delta U is NCV delta T. So again, delta T is 0, no change. So it is going to be 0. W is, now this formula you have to remember. Now this comes out to be, this derived from integration of PdV. Okay, this is the resultant of that. nRT ln of V2 by V1. Now as P is inversely proportional to volume, this order gets changed. You can also write P1 by P2. So for isothermal, it is nRT ln of V2 by V1 or nRT ln of P1 by P2. This is the formula that you have to keep in mind. And as if from first law of thermodynamics, you know delta Q is equal to delta U plus W. Delta U is 0. So delta Q comes out to be equal to work done. So the delta Q value is equal to work done. Okay. Clear? Clear, people? Clear? Is this clear? Let's move ahead. Now we are going to talk about adiabatic. A very, very, very important one. Very, very important one. If you get the terms very rapidly, perfectly insulating boundary, then it's called an adiabatic process. Then it corresponds to adiabatic process. Delta Q is equal to 0. Now over here, you have three equations. What is the equation? The first equation is PV gamma, PV raised to gamma is equal to a constant, where gamma is basically Cp by Cv. Okay. Cp by Cv. Okay. PV gamma is equal to constant. So obviously you can write P1 V1 gamma is equal to P2 V2 gamma. This is one thing that you can get. So this is one equation of adiabatic. But there are two more equations which can come in your exam. Okay, the first one, I'm going to use PV is equal to nRT. I'm going to use PV is equal to nRT over here. I'm going to use PV is equal to nRT over here. So the value of pressure comes out to be nR divided by V into T, and the value of volume comes out to be nR divided by P into T. I'm going to use both of these things. I'm going to use both of these things. My God, this class has some problem with me calling them people. Okay, no issues. I'll call you guys. Hey guys. Now guys, see this. I'm gonna substitute the value of pressure in this equation. That is nRT divided by V. Now when I substitute this, when I solve this, I get TV raised to gamma minus 1 is equal to constant. So this is also one more equation that you have to keep in mind. This is also okay, this is also one equation that you have to keep in mind. Okay, the third, when you substitute the value of volume as nRT divided by P in this equation, you get something like this, that is P raised to 1 minus gamma, T raised to gamma is equal to constant. Okay, 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 okay. So three equations that you have to keep in mind. PV gamma is equal to constant, TV gamma minus 1 is equal to constant, P1 minus gamma, T gamma is equal to constant. These are the three equations that you have to keep in mind for adiabatic process. Okay. Now, coming back. Now graph. Let's understand graph. So graph is again gonna be, see this, PV gamma is equal to constant. So you get P is directly proportional to 1 divided by V raised to gamma. है ना? So obviously you're gonna get a graph something like this. You're gonna get graph something like this. Okay. So over here you have to understand the value of gamma is always greater than 1. We calculated for monoatomic, diatomic, polyatomic. We got it as 5 by 3, 7 by 5 and 8 by 6. It's all greater than 1. So obviously you're going to get graph something like this. And the slope comes out to be minus gamma P divided by B. Minus gamma P divided by B. Are you able to understand this? Now this is a very important thing. Very important thing over here. Because in isothermal process, what did you get? You got isothermal process, the slope as minus P by V. Over here, you get it as minus gamma times of P by V. So basically, the slope of adiabatic process is gamma times more than isothermal. Is gamma times more than isothermal. Are you able to understand this? Where gamma is greater than 1. Where gamma is greater than 1. Yes. Yes. Are you able to understand this? A very important thing. Okay. Okay, people, this just a correction over here. Just a correction over here. Yeah. This is iso, right? This is minus P by V. Minus P by V gets cancelled. So 1 divided by gamma. Yeah. So this is 1 divided by gamma. Okay. That is one correction. Okay. Let's go. Okay. Chalo. So the slope for P for isothermal versus adiabatic. We know slope of isothermal is minus P by V. Slope for adiabatic is minus gamma P by V. Minus gamma P by V. Okay, and gamma being greater than 1, you are able to understand that the slope of adiabatic is much more greater than isothermal. And the slope is much more greater, and the ratio comes out to be 1 divided by gamma. The ratio comes out to be 1 divided by gamma. Okay, chamka. Next, now for adiabatic, you all know molar specific heat capacity will be 0. Why it is 0? Because C is equal to delta Q divided by N delta T. Delta Q is itself is 0. So C comes out to be 0. C comes out to be 0. Are you able to understand this? Are you able to understand this? Then delta Q itself is 0. Delta Q is NCV delta T. Again, same formula and everything. Work done will be delta Q minus delta W, delta Q minus delta U. But delta Q is 0. So work done comes out to be minus of delta U, minus of delta U. So work done is minus of NCV delta T, minus of NCV delta T. Okay. Cool. Let's move ahead. Now, comparison for different processes. Okay. Now I'm going to talk about expansion over here. Now I'm going to talk from expansion, that is from V1 to V2. Okay. Now for isobaric process, obviously pressure is constant, so you'll get a straight line. Isothermal, P is inversely proportional to volume, you will get a hyperbola, rectangular hyperbola. For adiabatic, obviously the slope is going to be more, so you're going to get something like this. Now isochoric, obviously the volume is not going to change, so this is the curve that you're getting over here. So this is the thing that you're getting. Now if you want to calculate the work done, obviously it's going to be area under curve, है ना? So obviously you are able to see that the isobaric has the maximum amount of area, then isothermal, then adiabatic. Are you able to understand? Where isochoric has the least amount of work or zero work. So this is the order that you are getting. This is the order that you are getting. Chamka. This is the order that you are getting. Now with respect to compression, it becomes literally ulta. Now in compression, when it goes from V2 to V1, so isobaric, it's obviously you're going to get this line. Yeah, we can. And in adiabatic, obviously you're going to get this one, and this is the isothermal one. Obviously adiabatic has more slope, and this is isobaric. Over here, adiabatic has the maximum area, then isothermal, then isobaric, and then isochoric. A very important thing to remember. A very important thing to remember. Very important thing to remember. Okay, people. Last but not the least, we are going to talk about second law of thermodynamics. Sir, first question after this topic. Huh? Okay. So we're going to talk about second law of thermodynamics. So second law of thermodynamics, now we have studied this in detail in your chemistry class as well. Okay, we are talking about Gibbs energy, entropy, everything you have studied. But in physics, there's not much in detail. Hai? So second law of thermodynamics, it only talks about logic. It talks about spontaneity and entropy. Okay, now what do I mean by that? Now second law is basically, you have waterfall, waterfall. So waterfall, the water is at some potential energy, it's falling, so it's getting converted into kinetic energy, and it falls on a rock, so it produces sound energy as well, and some amount of heat energy as well, है ना? So this is according to first law of thermodynamics, it's possible. Okay, now what I'm doing, I will play drums on that rock, so I'm producing sound energy. I will also heat that rock. So will that water flow back to the source? Will that water flow back to the source? Yes or no? According to first law, according to the first law, it should take place. It should be possible, because you're giving energy, you're playing sound energy, you're giving heat energy. Why isn't the water going? According to the first law, it's possible, but according to the second law, it is not possible, because it is talking about logic. Are you all able to understand this? Yes, according to first law, it's possible, because you're giving energy, it should take place, but according to the second law, it is not possible. So this is, and second law also says that heat always travels from hotter body to colder body. It does not travel from colder body to hot body. If you need to do from colder body to hotter body, then you have to give energy, then you have to do work. From hot to cold, it's a spontaneous process, but from cold to hot, it's not a spontaneous process. So the delta G gives energy. For hot to cold is negative, but from cold to hot, it is positive. Okay, chamka. Now a very easy question for you all. Okay, very easy question for you all. Are you all ready? Are you all ready for the question? The question is, if I have body A over here, I have body B over here, okay, body A has 200 joules of heat, body B has 100 joules of heat. Tell me the direction of heat transfer from A to B or from B to A. What is the direction of heat transfer? From A to B or from B to A? From A to B or from B to A? Tell me. From A to B or from B to A? Amar says A to B, Prakhar B to A, Tina A to B, A to B, A to B. Okay, okay, okay. So look, so people, A to B. Okay, I'll tell you the correct answer is that this question is only wrong. It's not a valid question. It's not a valid question. No, it's not a valid question. People, I'll tell you. No. People, for heat to flow, what is necessary? Yeah, I'll tell you. For heat to flow, what is necessary? What difference is necessary? See, for current to flow, potential difference is necessary. है ना? For current to flow, potential difference is necessary. For heat to flow, what is necessary? What is necessary? Tell me. Tell me. What is the difference which is necessary for heat to flow from one place to another? From one place to another. Tell me. Temperature difference. Exactly. Have I specified any temperature over here? Have I specified any temperature over here? I have not specified any temperature. Then how can you say it will flow from A to B? Temperature and heat is not the same thing. And I'm telling you that this body A has 200 joules of heat, this body B has 100 joules of heat is invalid. It is not at all correct with respect to physics. I'll tell you how. This is given in your NCERT itself. Just a second. Okay, just a second. It's given in your NCERT fair and square, clear. Okay, just a second. Let me just, yeah. Yes, this is exactly what I wanted. Where did one? Okay, see this, people. I hope so you are able to see this. I'll just zoom in. Okay, see this. What is written? That is a statement like a gas in a given state has a certain amount of heat is meaningless. Heat is a flow of energy, a transit of energy. A body cannot have some amount of heat energy. Nah. It's not like potential energy that a body has certain kind of potential energy. Yeah, a body can have some certain kind of potential energy, but you can't say that this body has 200 joules of heat energy. Nah. You can only give 200 joules or take out 200 joules from it. Are you able to understand this? Next. A gas in a given state has a certain amount of work. This is also meaningless. You can only do work on the system or work done by the system. You cannot say that this has 20 joules of work. Nah, you can only do 20 joules of work on this, or you can extract 20 joules of work from this. Are you able to understand this? But a gas in a given state has a certain amount of internal energy. This is valid. Are you all able to understand the difference? Last, a certain amount of heat is supplied to the system or a certain amount of work was done by the system are perfectly meaningful. Chamka, yes or no? Chamka, yes or no? Yes. Clear? Chamka, very good. Okay. Who? People, Okay. Yes, yes, yes. Tell me, Ram Kumar. Tell me, Ram Kumar. Okay, tell me. Okay, people. Sir, how many questions are left, by the way? Questions. See, questions are there. We'll solve all questions. Don't worry. Okay, we'll solve all questions. Don't worry. Acha, what I was saying that I will give you a break, but just give me 15 minutes and we'll complete KTG. What say? We'll complete KTG and then the whole thermal physics is completed. The whole of thermal physics is completed. What say? Yes. Okay, no issues. Okay, then we'll I mean, this flow is okay, right? This flow is okay, right? Because I want to complete the theory as soon as possible so that I can give maximum time to the question. Maximum time to the questions. We'll solve questions, don't worry. Okay, chalega. Then we can take a break. Okay, then we can take a break. Okay, chalo, let's go. Boyle's law. Again, you have all completed this. Boyle's law. Again, Boyle's law, it's an isothermal process. Again, because the temperature is constant. So PV is equal to K, and this is what you're getting. This we have all covered. We all covered in detail. Minus P by V, everything. Okay, we have all covered this. Boyle's law. We have all covered this in thermodynamics itself. This is part of KTG. Now, coming back to real gas and ideal gas. People, ideal gas, I'm going to denote it by the solid wedge over here. Solid wedge is ideal gas and dotted line is real gas. Okay. So see this. This is the ideal gas curve and this is the real gas curve. So the temperature, this is the temperature T1. At temperature T2, where T2 is much greater. Okay, here T2 is much greater. Here T2 is much greater than T1. T2 is much greater than T1. You are able to notice the difference between the real gas and the ideal gas is very less. That means real gases behaves as ideal gas at HTLP. What is HTLP? HTLP is high temperature, lower pressure. Are you able to understand this? Higher temperature, lower pressure. Chamka, yes or no? Higher temperature, lower pressure. Clear? That means real gases, they behave as ideal gases at higher temperature and lower pressure. HTLP. Okay. So greater the temperature, less will be the deviation. Okay. Let's move ahead. Charles' law, again, we have looked upon this. V directly proportional to T, it's an isobaric process. Everything we have looked upon this. Everything. Now the slope comes out to be NR by P. NR by P, we have already discussed this. Okay. And now in real gases and ideal gas, again, if you look, as soon as the temperature is increasing, the deviation is decreasing between the real gas and the ideal gas. Again, HTLP, higher temperature. At higher temperatures, real gases show ideal gas behavior. Now about pressure, we'll look upon that. Don't worry. Next. Okay, this is something which you have already covered. Now Avogadro hypothesis. This is also something which you have covered in chemistry as well. So what does it say? It basically says at constant temperature and pressure, equal volumes of all gases contain equal number of molecules. Equal volume of all gases contain equal number of molecules. That means if I have CO2, if I have NH3, if I have SO2, all at 100 ml, 100 ml, 100 ml, the number of molecules is going to be X, X and X in all the three cases. That is exactly what is Avogadro's hypothesis. You have already studied this in chemistry as well. That is 1 mole of any gas is equal to 22.4 liters. I hope so you have studied this. Yes, 1 mole of any gas is equal to 22.4 liters. Yes or no? Yes. That is the same thing. Exact same thing. Okay. Now we're going to talk about ideal gas equation. Yes, at STP. We know PV is equal to NRT. है ना? P is in ATM, V is in liter, N is number of moles, R, the value of R is 0.0821 when you're talking with respect to ATM liter. When you're taking with respect to energy, it is 8.314 and temperature is in Kelvin. Okay. Now we're going to calculate the density of the gas. What is density of the gas? It is basically mass by volume. Now we all know PV is equal to nRT. Number of moles can be written as mass divided by given mass given by molar mass. Now this V goes to the other side. So mass by volume becomes density. This m naught is over here. So what is the density equation you are getting? Density is equal to P m naught divided by RT. P m naught divided by RT. Now a very important thing. Okay, I'll talk about it later. Okay. Now over here, people, this R, can I write this R is equal to knock? So R is equal to knock over here. R is equal to knock. Okay. Now can I write this m naught as m into Na? What is m? What is m? Mass of one molecule. Mass of one molecule. M is basically mass of one molecule. Now if the mass of one molecule is m, if I multiply it by Na, so what, that is basically the mass of Na molecule. Mass of Na, that is mass of one mole of molecule. It's going to be molar mass. That is how I wrote this. That is how I wrote this. Yeah, waiting for fluids, don't worry, we'll cover fluids next. Okay. So Na gets cancelled, so I get one more equation, that density is equal to Pm divided by kBt. Now one thing that you have to keep in mind, wherever in KTG, you are getting m naught, obviously it's going to have RT in its place. It's going to have RT. Whenever you have small m, it's going to have KT. Understood? So don't confuse yourself with the formula. Okay. If you have m naught, it's RT. If it is small m, that is mass of one molecule, it is KT. Chamka. Now let's talk about this. This graph is a very important one. What is K? It is Boltzmann constant. PV is equal to nRT. I'm going to talk about 1 mole of gas. So it becomes PV is equal to RT. I'm going to divide it by RT throughout. So I get PV by RT is equal to 1. Now this is a very interesting relation that we have. Thank you Dr. Purple. Thank you Mahalakshmi. Thank you. Okay. Now this is always equal to 1. PV by RT is always equal to 1. Always. Now what do I mean by that? If I'm going to take the graph of PV by RT and pressure, if you can take volume also, it's going to have the same graph. Okay, no issues. If I take pressure over here, this is the PV by RT graph that you're getting, that always you're getting the value of PV by RT, always you're going to get as 1 irrespective of the pressure. This is the line that you're getting. This is for ideal gas. Now I'm going to take two real gases. This dotted line, T1 is the first real gas. This dotted blue line is the second real gas. Now over here, T2 is much greater than T1. You all notice at zero pressure, all of these three lines are coinciding over here. That means at lower pressure, real gases behave as ideal gas. And as temperature T2 is greater than T1, the deviation is very much less. See, this deviation is very much less. As temperature T1 is less, the deviation is more. Are you all able to understand this? So again, at HTLP, higher temperature, lower pressure, you are going to get real gases behave as ideal gases. Clear? Now we are going to talk about KTG postulates. Okay, I'm going to talk about KTG postulates. Okay, people. Now these are all the postulates that is required. Okay, and it will be all clear for you all. Okay, what are the KTG postulates? That gases is made up of atoms and molecules. Wow, what a postulate! Wow, what a postulate! Molecules of the same gas are identical in all aspect, mass, shape, and size. My God. I don't think so. I have to make you explain this all. If you obviously oxygen molecules are going to be same in all aspects. Next, third is an important point. That is, molecules are constantly in random motion along a straight line. That means they are moving randomly here and there. You can't predict where they will be, but you can definitely say wherever they are going, they will be traveling in straight lines. Okay, people. Next, all the collisions of the gas molecules among themselves and walls of the container is elastic in nature. So obviously they're going to collide with each other and then going to collide with the walls of the container. Whatever the collision may be, it's going to be elastic in nature. That means the momentum is going to be conserved throughout the system. Also the kinetic energy initial is going to be equal to the kinetic energy final. Yes, okay. The pressure of a gas. Now what is the pressure of the gas? Okay, for that, just a second, है ना? For that I will basically tell you something. Just a second, people. Let us keep the class a little interesting. Okay. Just a second. Just a second. Yes. Okay, see this, people. Okay, see this. Okay. Okay, see this. See this, people. है ना? See this, people. Okay, if you are able to notice the pressure over here is basically okay. It is increasing. It is increasing. Okay, I'll just increase the temperature over here. I'm increasing the temperature, and due to the increase of temperature the kinetic energy has increased. The kinetic energy has increased, and due to that, due to the kinetic energy being increased, the number of collisions is increasing. The number of collisions is increasing, and because of the number of collisions is increasing, the value of pressure is increasing. See this? Value of pressure is increasing. Are you able to understand this? So more the number of collisions, more will be the value of pressure. So the pressure comes out. The pressure is due to the number of collisions actually. Are you all able to understand this? Are you all able to understand this? See this? The number of collisions, greater the number of collisions, more will be the pressure. Are you able to understand? Okay. Are you all able to understand this? Okay, cool. Yes, very good. Very good. Yes, a pressure cooker. Okay. The pressure of the gas is directly proportional to the number of collisions of molecules per unit area. Okay, that is something which we already know. The kinetic energy of the gas only depends upon the absolute temperature and not on the nature of the gas, which I have already talked about. Ke is equal to Nf by 2 R delta T. है ना जी? L delta T depends upon only delta T. The actual volume of the gas molecule is negligible when compared to the volume occupied by the gas. So basically what I mean over here is, if this is the container that I'm talking about, and obviously this is the gas molecules which are spread out over here. This is the gas molecules which are spread out over here. Now you all know that the volume of the gas is not defined. The volume of the gas is not defined because what happens? Volume of the gas is not defined because it takes the shape, the gas takes the shape of the container. Now over here the volume of the gas is 1 liter because the container is 1 liter. Now if I spread this gas in this particular room, the volume of the gas will be equal to the volume of this room. है ना? So this is the volume of the gas. Now what do I mean over here is, what do I mean if I compress all of these things, if I compress all of this thing into one small area, this something like this. Okay, that is what they have said, that the actual volume of the gas molecules is negligible when compared to the volume occupied by the gas. So this volume is actually negligible when it comes comparison to the volume occupied by the gas. Clear? Clear? Okay, next. There is no interaction of molecular force of attraction among the molecules. This is something which I've already talked about. Gravity is again neglected over here, and molecules of the gas are tiny rigid spheres of negligible volume. Okay, and at absolute temperature molecular motion stops. Again, something which I've already discussed. No one can stop me, Kiran. There is one thing which can stop you, and that is your NEET result. Okay. Okay, so Okay, that is one thing that we can stop you, that is your NEET result. Okay, the day that you see your NEET result, you'll all stop this spamming and everything, and you would have just thought ki I should not have sorry. Okay. Chalo, let's move ahead. Let's learn about kinetic gas equation. Kinetic gas equation. Okay. So the pressure exerted to the walls of the container. Okay. Yes, you will be the first to not get into a government medical college. Yes, that is right, Kiran. Okay, so the pressure. Okay, the pressure exerted by to the walls of the container. है ना? Okay, it is going to be 1/3 m n v RMS square divided by volume. Okay, now I'm going to explain each and everything. M is basically the mass of one molecule. Okay, n is the total number of molecules. Okay, v RMS is the root mean square velocity. I'll be talking about that, and v is basically the volume of the gas. Okay, so don't worry about it. I'll be explaining each and everything. Now, if I want to talk about for 1 mole of gas, if I'm talking about 1 mole of gas, so obviously, so n will be substituted as Na. So m into Na becomes m naught. So this is something which you are getting over here. Okay, people. Okay. Now, if you all notice over here, I'm going to substitute this v over here. So this becomes PV is equal to 1/3 m naught v RMS square. Okay. So PV is equal to, now if you all notice, I want some kind of kinetic energy over here. I have m, I have v square. The only thing which is missing is half. So I multiply and divide by 2 over here. And so 2 over here. So this becomes kinetic energy for 1 mole of gas. So this becomes PV is equal to 2/3 times of kinetic energy. 2/3 times of kinetic energy. And this is a very important equation, people. Very important equation. Okay. So kinetic energy for 1 mole of gas is 3/2 times of PV. That is, this 3 over goes over here, 2 either goes over here. So 3/2 of PV. Are you able to understand this? 3/2 times of PV, and PV can also be substituted as RT for 1 mole. So it becomes 3/2 RT. 3/2 RT. Now comes the Chamka moment. Okay, now comes the Chamka moment. People, see this. Very interesting. Very interesting. Okay, people. Now I'm going to talk about 1 molecule. This is for 1 mole. I want to talk about 1 molecule. So if I want to talk about 1 molecule, I'll have to divide it by Na. So I divide this whole equation by Na. I divide this whole equation by Na. That means 3/2 RT, and I'm going to divide this. By Na. I know R is equal to NAC. Okay, so R by Na comes out to be Kb. So this fellow comes out to be 3/2 kBt. 3/2 kBt. है ना? Yes. Now people, does this similarly look like 3 times of half kBt that you have studied in thermodynamics? Where 3 is the degree of freedom. So this is basically F/2 kBt. F/2 kBt is basically what? Degree of freedom is 3. Monoatomic gases only translational degree of freedom. The KTG postulate also says that, what is it? That it is, where is it? Molecules are constantly in random motion along straight line only straight line. Are you able to understand? This? Is everything connecting now? Whatever we have studied? Yes. Okay. Cool. Yeah, so that is something which we know. Okay. RMS velocity. Okay, people. Now we are going to talk about RMS velocity. Now, actually, RMS velocity should actually be given as SMR velocity, because that is exactly what we are doing. Okay, but RMS sounds more cool. That is the reason RMS velocity. Okay, RMS velocity, root mean square velocity. So whatever velocities we have, if these are the velocities of the gas molecules, we first square it. So V1 square, V2 square, V3 square, Vn square. then we take the mean of it. So we have to add and divide it by the total number of molecules. In order to nullify the square effect, we take the square of it. That is VRMS for you all. That is VRMS for you all. Okay. Okay, people. Very good. My God, we have. Now RMS velocity. Okay, people. So RMS velocity is again square root of 3 RT by m naught. I've already told you where m naught comes, there you have to take RT. There you have to take RT. Okay. Now one more thing that you have to note over here. In chemistry, you all say, sir, the molar mass of hydrogen is 2. Okay. So the molar of hydrogen molecule is 2 grams. But we are physics people. We only take in SI units. So make sure that this m naught is actually in kg. It should be in kg. So please convert it into kg. Are you able to understand this? So whatever value of m naught, you have to convert it into kg when you are finding out the value of URMS or anything. Okay. Now, if you want to write in terms of kT, so this m naught gets converted into small m, that is mass of one molecule. So square root of 3 kT divided by m. Chamka. In terms of pressure and density also you can do. So density is equal to Pm naught divided by RT. Just substitute over here, you will get this as this. Okay. Very good. Next. Average velocity. Again, average velocity is nothing. It's basically you have to find out the average. Okay. Now people, just a second. You should convert this into speed. Okay. This is average speed that you are calculating, because the average velocity is 0. The average velocity is 0 because everything cancels out each other. The average velocity is 0, but the average speed is basically this thing. This is the average speed that we are calculating. Okay, people. So V average comes out to be square root of 8 RT divided by pi m naught. In terms of K, KT, it will be pi into small m. That's it. And here it will be P divided by D. That's it. Okay, cool. Next. Root mean square velocity. Again, we have already talked about this. Most probable velocity. Now, what is most probable velocity? That is maximum fraction of molecules possesses this velocity. Matlab, if I have a gaseous system over here, है ना? If I have 10 molecules having 10 meter per second velocity, if I have 100 molecules having 100 meter per second velocity, if I have 1000 molecules having 1000 meter per second velocity, and if I just close my eyes, if I insert my hand into it and just pick a random molecule, which molecule will have the highest probability to land in my hand? Obviously, it is going to be the 1000 meter per second molecule, because that is the maximum fraction which is available, hai na ji? And that is basically most probable velocity. That is the most probable velocity. So maximum fraction of the molecules possess this velocity, and the formula comes out to be 2 RT by m, square root of 2 RT by m. In terms of KT, it will be small m and KT over here. That's it. Now Maxwell distribution law, Maxwell speed distribution law. What is it? This is fraction of molecules, and this is the velocity over here. You have to understand, people. You have to remember this RAM. You have to remember this RAM, that RMS is greater than average and average is greater than MPS. Okay, in terms of magnitude I'm speaking, RAM or RAM, anything you want to say. Okay, so this is one acronym that you have to remember. Now let's understand this graph right now. So this is the fraction of maximum molecule. So if you see over here, MPS has the least amount of velocity. That's what we are getting also. Yes, and the maximum number of molecules have MPS. That is what we are getting. Then V average comes in the middle, that is the second position, and V RMS has the highest amount of velocity and the least amount of fraction. Okay, people. Clear? Last but not the least, mean free path. This you have already studied in current electricity when you are calculating drift current. Okay, so basically what is mean free path? It is basically the average distance traveled by a molecule before it collides again. That is called as mean free path. So the mean free path comes out to be 1 divided by square root of 2 n pi d square, when n is the number of molecules per unit volume, or the number density, है ना. 1 divided by square root of 2 n pi d square. It's very fascinating to know that NEET has literally asked this question directly. They have asked you the formula directly. So high probability of getting it again. So 1 divided by root 2 n pi d square, where d is also the diameter of the molecule. Okay, molecule. So from that we have completed thermal physics. We have completed thermal physics. Okay. Okay, people. Done and dusted. Okay. Yay. So people, when do you want to return back? When do you want to return back? Yeah. When do you want to return back? Tell me. You can get it on NEET, Unacademy NEET English Telegram group. I'll ask Ryavar sir to send it. Okay. 30 minutes? You want 30 minutes? My good. 15 minutes? Yeah, I guess 15 minutes is okay. है ना? We have to wrap it up fast. है ना? We have to wrap it up fast. है ना? Okay. So, okay, 15, okay, 15, okay, let's do something in between. I'll give you a break. I'll give you a break of 17 minutes. Yeah. 17 minutes, neither yours, neither mine. Yeah. 17 minutes is what you're getting. Okay, people, 17 minutes. Okay. So I want you all to be there here exactly 118. 118. Okay, people. 118. Everyone should be here. Okay. Everyone should be here by 118. Okay. Chalo, let's meet. Okay, let's meet. Okay, chalo, bye bye. Bye bye. Boy, boy, boy. Boy, boy. Mic testing 1 2 3. Good afternoon. Mic testing 1 2 3. Testing 1 2 3. Okay. So, video, audio, PPT all clear? Video, audio, PPT all clear? Yes? All clear? Hello, hello. Very good. Just a second, people. Perfect. Very good. Very good, people. Just give me a second. Okay. Just give me a second. Okay. Chalo, let's start. Great. Can we all start with solid mechanics? Can we all start with solid mechanics, people? Yes. Can we all start with solid mechanics? Yes. Acha, I'm giving you two options. Okay, I'm giving you two options. Okay, I'm giving you two options. Do you want that I should start with solid mechanics first, or should I start with SHM first? Tell me. Do you want solid mechanics first, or do you want SHM first? So if you're starting with SHM, then we're going to do SHM and waves and SHM. Okay, so SHM it is. Chalo ji. SHM, SHM, SHM. Okay, good. So SHM it is. Cool. शुरू करो. अरे. Okay, chalo. Okay, we'll cover everything. Don't worry. Okay, right now we'll start with SHM then. Okay, chalo, we'll start with SHM. Cool. Okay. Chalo. Let's start. Okay, people. So first of all, they are talked about periodic motion. So what is periodic motion? Periodic motion is any motion which repeats itself after regular interval of time. That is called as periodic motion. है ना? So periodic motion is very easy to understand. That is basically revolution of the earth. So the earth completes one revolution in 365 days. So it again repeats the motion after 365. So the time period is of 365. Rotation of the earth 24 hours. After every 24 hours, one day is completed, one rotation is completed. That itself is a periodic motion. है ना? So uniform circular motion, है ना? So the speed is constant. So uniform circular motion, the time period is also same, है ना? So UCM or orbital motion of the sun, है ना? Revolution and the rotation of the planets, motion of a pendulum, it's again all periodic motion. Okay, it is again all periodic motion over here. Okay, next. Then we are to talk about oscillatory or harmonic motion. What is oscillatory or harmonic motion? So oscillatory motion is basically to and fro, back, forth, up and down about a fixed point after regular intervals of time. So is oscillatory motion a periodic motion? Yes, it is a periodic motion because it is getting repeated after equal intervals of time. But what is the difference? In periodic motion, it is not going to and fro about a fixed point. Periodic motion is just a motion. Are you able to understand? But in oscillatory motion, it is doing periodic motion about a fixed point. And that fixed point is called the equilibrium position or the mean position. Are you able to understand this? So the fixed point about which the body oscillates is called the mean position or the equilibrium position. Yes. Chamka. Now, I'm going to show you a graph which is very much important and it can solve any kind of assertion reasoning question when it comes to this. What is the graph? This is the graph. Okay, so I just need a correction over here. Solids इसके बाद, sorry, solids will do after this. Okay, solids will do after this. Okay, okay. So see this. Now this graph is very important when it comes to your association reasoning as well. In your NEET exams also they'll ask, is every UCM a periodic motion? Is every oscillation a periodic motion? Is every SHM a periodic motion and everything? है ना? So let's understand. Okay. So see this graph. Sir, is every periodic motion an oscillatory motion? No, that is wrong. Because every periodic, so because UCM is also a periodic motion. Are you able to understand this? But can you all say that every oscillatory motion is a periodic motion? Yes, you can say that. You can definitely say that. Are you able to understand this? Are you able to understand this? Yes. Sir, is every periodic motion, is every periodic motion an SHM? No, because it can be a UCM as well. But sir, is every SHM a periodic motion? Yes, every SHM is a periodic motion. No problem, Simi, no problem. Okay. Is it clear? Now, sir, what about large frequency, sir? So this large frequency corresponds to vibrations actually. This is actually vibrations. So obviously vibrations are going to have large frequency. Okay, it's also oscillate with large frequency. Yes or no? Yes or no? So is every vibration a periodic motion? Yes. Is every periodic motion a vibration? No. It can be a SHM as well, it can be a UCM as well. Chamka, yes or no? Chamka, yes or no? Yes. So this graph is a very important graph when it comes to your association reasoning. Okay, you can take a note of this. You can take a note of this. Next we are going to understand a very important thing. Condition for any oscillatory or harmonic motion. Condition for any oscillatory or harmonic motion. Now, f is equal to minus kx raised to n is basically the condition for any oscillatory or harmonic motion. And this x is basically the displacement from the mean position. Okay. This displacement from the mean position. So whatever the displacement is, we are gonna take it from the mean position. Are you able to understand this? Are you able to understand this? Okay. Now, what is simple harmonic motion? The simplest case of oscillatory motion is simple harmonic motion. So what is the simplest case? So the simplest case is when the value of n is equal to 1. So substitute n is equal to 1, you get f is equal to minus kx. F is equal to minus kx. And simple also means along a straight line, okay. So the condition for SHM is f is equal to minus kx. Now this force is not a constant force because it is directly dependent upon the displacement. More the displacement, more will be the restoring force. More the displacement, more will be the restoring force. Are you all able to understand this? Are you all able to understand this? Yes or no? Yes. It's not a constant force, it's a variable force. It depends upon the displacement. Okay. Now, this restoring force is always directed towards the mean position. It is always directed towards the mean. Okay, 9 baje se. Okay, it is always directed towards mean position. Like for example, if this is equilibrium position, this is mean position. I have done some work and I have expanded this. So it wants to come back to the mean position. That the restoring force will be over here. If I have compressed it, the restoring force will be over here. So the restoring force will be always directed towards the mean position. That is exactly what I'm gonna say. Sound is less? Is the sound less? Is the sound less? No, I think it's clear from my side, Tina. You can just see your, okay, see this. Now, if the block which is doing SHM is at x is equal to 0, obviously if you put x is equal to 0 over here, you get force as 0. That means the restoring force at equilibrium position is 0. It is at equilibrium, the net force is 0. But if you do a positive displacement, obviously if you do a positive displacement, x is positive, but you get f as negative. F as negative. That means it is directed towards the mean position. Displacement is here, but force is here. It is one dimension motion, no? So this negative sign corresponds to the change in direction. X is over here, but f you are getting negative. X is positive, f is negative. Over here, x is negative, So if x is negative, overall force will be positive. That means force will be over here. Are you able to understand this? Are you able to understand this? Yes or no? Next, basic terms. What is the amplitude? Amplitude is basically the maximum displacement from the mean position. है ना? It can go to plus a or it can go to minus a. Okay. Time period. Again, what is time period? The time taken by the particle to complete one oscillation. है ना? That is basically time period. Next, frequency and angular frequency. What is frequency? Frequency is basically inverse of time period. है ना? The number of oscillations it can do in one unit second, in 1 second. That is frequency. And omega or angular frequency is 2 pi into f, or frequency can also be written as 1 by t. So 2 pi by t also we can do it over here. Okay, clear? Clear, people? The restoring force. Now, people, very important, very important, very important. We know F is equal to minus kx. This k, चमका का मतलब, अरे चमका मतलब दिमाग की बत्ती जलना, वो होता है आर्यन, ठीक है? F is equal to minus kx. Now this k is called the spring constant or the stiffness constant. Okay, and the value of k is basically m omega square, where m is the mass of the particle, omega is the angular frequency. This you have to keep in mind. So if f is equal to minus kx, k is equal to m omega square, you can also write f is equal to minus of m omega square x. F is equal to minus of m omega square x. Okay, people, I need you all to like the session. Okay, now let's talk about acceleration. Now people, f is equal to minus kx. I can basically substitute f as ma and k as m omega square x. है ना? M and m gets cancelled, so what you're getting, a is equal to minus of omega square x. That is what you're getting. Okay, that means as the force is also dependent upon displacement, the acceleration is also dependent upon the displacement. Are you all able to understand this? That means this acceleration itself is not constant, it is a variable acceleration. If it is at the mean position, acceleration is 0. If you'll notice over here, if you put the value of x as amplitude, you'll get the maximum acceleration because it is at the maximum displacement. Are you all able to understand this? Yes or no? So, and this is also same, it is always directed towards the mean position. Yes or no? Okay, now A is maximum at the extreme position. Obviously, as it is dependent upon displacement, if the displacement is maximum, you will get acceleration as maximum. What is the value? It is going to be what? It is going to be minus omega square a or plus minus omega square a. It is going to be minimum at the mean position. It is going to be 0 because x is equal to 0. Yes or no? Now let's talk about velocity. Now what is happening? This is at mean position. So this is basically oscillating. Okay, this is the mean position. Okay, this is the mean position. This pointer is the mean position. Okay, so see, as soon as what is happening over here at the extreme position, it is having maximum acceleration towards the mean position over here, है ना? And the velocity is 0 over here. Velocity is 0, acceleration is maximum. So maximum acceleration, it moves very fast towards the mean position. As the displacement is decreasing, the acceleration decreases, the velocity is increasing. At this point, force is 0. If force is 0, acceleration is 0. But velocity is a maximum. But due to inertia, it again crosses. And as it crosses again, the acceleration keeps on increasing, but in the opposite direction. Velocity is here, acceleration is here. That is the reason the velocity keeps on decreasing, and in this extreme position, the velocity is 0. Chamka. This is exactly what is it. Now, this is a derived quantity, but I'm not going to derive it, but the value of velocity comes out to be v square is equal to omega square a square minus x square. Yes. What is the value of v, maximum v? Obviously, so maximum v will be where? So when x is equal to 0, so you get a omega as the v maximum. V minimum is obviously 0 at the extreme position. Okay. Clear? Clear? Let's move ahead. Now, what is the differential equation for SHM? What is the differential equation for SHM? A is equal to minus omega square x is your differential equation for SHM. Okay. Now, you can all write, just a second people. Just a second. Hello. Okay. So, A is equal to minus omega square x. Now, you can write A as rate of change of velocity, that is dv by dt. dv by dt is equal to minus omega square x. This into the left hand side. So, this equation that you are getting in the x axis is basically the differential equation from, no, I'm not from UP. I'm not from UP. This is for SHM, differential equation for SHM. Okay. Clear, people? Clear? This is the differential equation. Okay. Let's move ahead. Now, equation for SHM. Now, this is the differential equation for SHM. Now, in engineering and everything, you are taught how to solve this equation and everything. It's just like a quadratic equation. So, the solution for this, is x is equal to a sine omega t plus phi. This is the solution that you get. This is the solution that you get. Am I clear? Am I clear? This is the solution that you get. Where a is the amplitude, omega t plus phi is called the phase. I'll explain everything, don't worry. It's called the phase. Now what is this phi? What is this phi? It's very simple to understand. Just substitute the value of t as 0 over here, time as 0. So what do you get? A sine phi. So initial phase. So what is phi? Phi is the initial phase or the phase at t is equal to 0. What is initial phase? Phase at t is equal to 0, that is basically initial phase. Now one thing that you have to keep in mind is that phi, the value of phi ranges from 0 to 2 pi. The value of phi ranges from 0 to 2 pi. Clear? Clear? Just a second, people. Yes, just a second. Just a second, people. Yes, I just want to fill my water bottle. भाई पानी भर दे यार.
तेरा खाना आ गया.
हाँ रखवा रहा हूँ. Okay, chalo. Okay, yeah, this is this. Now this is an equation for SHM. But if you solve this, you will get many equations actually. So a cos omega t plus phi, a sin omega t plus b cos omega t, a plus b sin omega t, all of these equations are valid over here. All of the equations are valid over here. I hope so I'm clear over here. I hope so I'm clear. Let's moving ahead. Okay. So now people, let us understand how to get the equations. Okay. See this. X is equal to a sin omega t plus phi is your equation. Okay. Okay. Now, okay, see ये देखो. So x is equal to a sin omega t plus phi, that is your equation. Okay. Did you understand this? Now we have to do this. Now see what do we have to do this? Okay. Now this is the equation. For this particle. So if this is the amplitude and this is the SHM, and this is at x is equal to 0. This is x is equal to minus a, and this is x is equal to plus a. And this particle right now at t is equal to 0 is at x is equal to 0, and it moves over here. It moves over in this direction. Okay. See this what happens over here. Thank you. Okay, see what happens over here. So right now it is at x is equal to 0. So x is equal to 0, t is equal to 0, you get 0 is equal to a sin phi. That means now phi can take 0 degrees or pi degrees. Phi can take 0 degrees or pi degrees. Am I right over here? Yes, it can take 0 because sine 0 is 0, sine pi is also 0. Now, which angle to take depends upon the velocity direction. Which angle to take depends upon the velocity direction. If you all notice, if I differentiate this fellow, I'll get velocity. I'll get velocity. What I am getting? A omega cos omega t plus phi. That is the velocity that I'm getting. Now, if you all notice, the velocity in this case is in this direction. That means the velocity is positive. The velocity is positive. That means I need to get this value as positive. I need to get this value as positive at t is equal to 0. So V is equal to A omega cos phi should be positive. A is positive, omega is positive. Obviously, cos phi has to be positive. Now, obviously, you have two options over here, 0 and pi. 0 and pi. So which angle to insert over here? Obviously, we will have to insert 0 is equal to 5 over here. Because at cos pi becomes minus 1. Cos pi becomes minus 1. And that is not something which we want. We need a positive velocity. That is the reason if a particle is at mean position and going to the right extreme, that is at the positive amplitude, we use the equation A is equal to A sin omega t. Is this clear? Is this clear? Is this clear, people? Chamka? Yes or no? Let's go. Now, a very important thing. A very, very important thing. If you all notice, this is the graph that you are getting. X is equal to A sin omega t. If you differentiate it, you will get A omega cos omega t. If you differentiate it again, you will get acceleration, that is minus of A omega square sin omega t. Okay. Okay. So this is a sine curve that you are getting. So you are getting a sine curve over here. Now you are getting a cos curve over here. So you are getting a cos curve over here. Are you able to understand this? This is again a sine curve. But a negative sine curve. So you are getting a negative sine curve over here. Now if you all notice that velocity leads the displacement by pi by 2. Acceleration leads the velocity by pi by 2. So acceleration leads the displacement by angle pi. Chamka. Oh, thank you. Thank you, HSP sir. Yes. Are you able to understand this, people? Is this clear? Yes. Now, what do I mean by leading pi by 2 and pi by 2? So basically we can look over here in the graph. Okay, it's very easy to understand. Okay. So over here, this is the sine graph that you are getting. This is the sine graph, sine curve that you are getting. Okay. And this is the velocity equation. This is the cos equation that you are getting. Okay, very good. So if you look over here, okay, if you look over here, are you all able to see? Oh wow, array. So this is exactly how you draw a curve, right? So this is a minus sine curve, this is a cos curve, and this is the sine curve. Exactly. Okay. Okay, see this, people. If you all notice over here, this curve, see this curve, you're already getting over here. Are you all able to see this? Yes. So HSP sir is over here. So can we get some green hearts? Yeah. Can we get some green hearts, people? Okay. Are you all able to understand that? See this curve. See this curve. This curve. You are getting it over here. Are you able to understand this? That means, or I can say something like this, that this curve right over here, I'm getting pi by 2 before. Yes or no? I'm getting pi by 2 before. That is something which you have to understand over here. And then you have to understand that this curve, you're already getting over here. That is pi before pi. Yes, that is exactly what I'm saying over here. Okay, let's move ahead, people. Yeah, these are some of the cases. So if the particle is in the mean position, and if it's going into the left extreme, then you can basically use x is equal to minus a sin omega t. If it is going to the right extreme, you can use x is equal to plus a sin omega t. Okay, that will basically ease your calculations. Okay, these are all some things which we can do. And if it is starting from the right extreme, you can use x is equal to a cos omega t. From the left extreme, x is equal to minus a cos omega t. Okay, people? Yes or no? Yes or no? Okay. Now, let us understand SHM as a projection of UCM. SHM as a projection of UCM. Okay. Uniform circular motion. Okay, people? So, see this. Uniform circular motion is not an SHM. That is not what we are talking. But the shadow projection of UCM is an SHM. The shadow projection of UCM is an SHM. For example, let us take an example in which a particle is doing uniform circular motion over here. Uniform circular motion over here. Hai? If you notice over here, if you try to take projection, so when the particle is over here, the projection is over here. When the particle is over here, the projection is over here. When the particle is over here, the projection over here. Hai na? Similarly, when the particle is over here, the projection is over here. So, are you able to see that the projection is actually doing SHM? The projection is actually doing SHM. The projection is actually doing SHM. Are you all able to see this? The shadow is actually doing SHM over here. So, uniform circular motion is not SHM, but the projection of UCM is an SHM. Chamka? Chamka? Yes or no? Chamka, yes or no? Yes. Now, this is very, very important thing. A very, very important thing. Okay. Let me see if you can understand this. At t is equal to 0, the particle is over here. At t is equal to t, the particle reaches over here. And it is traveling by some angular velocity omega. So, basically, it has traveled this path. Hai na? Or I can even say it has traveled the theta path. It was over here and it has traveled over here. Hai na? So, it was over here first and then it came over here. And this vector is basically the amplitude. This vector is basically the amplitude. So, it has traveled theta. So, if this is A cos theta and this is A sin theta. Are you able to understand this? This is simple projection. This is A cos theta, this is A sin theta. This is A cos theta, this is A sin theta. Hai na? So, it is very much obvious that theta is equal to omega t. Theta is equal to omega t. This is something which I have already studied. So, that means what do we get? X is equal to A sin theta and X is equal to A sin omega t, which is basically the same thing that we are getting over here. Same thing which we are getting over here. Yes or no? So, see, if a particle is starting from here and goes over here, that is exactly the equation that we are getting. Exactly the equation that we are getting. Yes. Please like the session, people. Please like the session. Yes. Again, very, very similar things. Okay. Very, very similar things. Okay. These are all similar things. Now, let's move on to the next part. That is energy in SHM. That is energy in SHM. If you're talking about kinetic energy can be written as half mv square. You will be like, yes, sir. You can all write half mv square. And the value of v already know. V is basically what? V square is equal to omega square root omega square into a square minus x square. Just substitute over this equation in this one. You will get the value of kinetic energy as this thing. Now, we already know m omega square can be written as k. So, it becomes half k a square minus x square. Cool. Chamka. Chamka. Moving ahead. If you all notice, the velocity itself is 0. The velocity is 0 at amplitude, maximum amplitude, obviously. So, if you put x is equal to a over here or x is equal to plus minus a, you will get x is equal to plus minus a, you will get kinetic energy is minimum. So, at maximum amplitudes, you will get the kinetic energy minimum because the velocity itself is minimum. Velocity itself is 0. And kinetic energy maximum, you will get it at mean position. Just substitute x is equal to 0 over here. You will get half k a square as your maximum kinetic energy. Chamka. Chamka. Next. This is a very, 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 very important graph. Very, very, very important graph. So, see, at t is equal to 0, it starts at mean position with maximum kinetic energy. Hai na? Yes. At t by 4, what happens is, at t by 4, it reaches the maximum position, maximum amplitude. see the total time period is t. The total time period is t. So this is 0, t by 4, t by 2, 3t by 4, t. Are you able to understand this? How does the oscillation takes place? T is equal to 0, t by 4, t by 2, 3t by 4, t. So at t by 4 it is at maximum amplitude. So kinetic energy is 0. Then at t by 2 again it is at mean position. So maximum kinetic energy. 3t by 4 again at amplitude. So 0 kinetic energy. Then again at t it is at mean position. So maximum kinetic energy. Now very important thing to note here. One time period में kinetic energy का 2 cycle complete होता है. मतलब when you are basically it's what they are saying is, see this, in just one time period kinetic energy's 2 cycle gets completed. See, this is the one cycle and this is the second cycle. Very important thing, very important thing to understand, very important thing. In just only one time period kinetic energy 2 cycle complete करता है. This is 1 and this is 2. If you all notice, this is 1, maximum 1 over here, है ना? See this maximum, this is first cycle and this is the second cycle. Chamka. Is it clear? Is it clear, people? Yes or no? Clear? Let's go. Now let's talk about, see what you can do. Kinetic energy is half mv square. You can substitute the value of v as a omega cos omega t over here, and what do you get is kinetic energy is half m a square omega square cos square omega t. Now we have already know that this fellow is k max, this is k max, half k a square. See, this m omega square becomes k, so half k a square is k max. So kinetic energy is k max cos square omega t. This is also one equation that you will get over here. Now talking about potential energy. Potential energy, again we all know it is half kx square. Half kx square. Substitute the value of x over here. X is equal to a sin omega t. When you substitute it, this becomes half ka square, that is u max. So this is u max sin square omega t. Chamka. Very good. Now, if you notice half kx square becomes 0 at potential, at mean position. Because no net force is 0. So why potential energy will be there? No potential energy because net force is 0. But at amplitude, maximum amplitude position, potential energy will be maximum, because obviously potential energy will be stored maximum because of the maximum elongation in the spring. So half kx square will be half ka square maximum. That's it. Again, if you notice the graph, at mean position it is at 0. At t by 4 it is at maximum. T by 2 again at 0 because it is at mean position. Amplitude max, the mean position. So again in one time period potential energy also completes 2 cycles. Is it clear? Is it clear? This is the first one and this is the second one. Chamka. Clear? This is the kinetic energy and the potential energy graph. Very important graph. Very important graph. See this. So this is at x is equal to minus a, this is at x is equal to plus a. If you are talking about kinetic energy, obviously kinetic energy is 0 at amplitude, so it starts with over here. Then it starts increasing as it moves towards the main position. At mean position it is maximum. Then again it drops down and goes to 0 at the other extreme. But in potential energy it's the opposite. At x is equal to minus a, it is going to be maximum. It's going to drop down to 0 at the mean position, and then it's going to increase up to the other extreme. Chamka. Is it clear? Let's move on. Now we're going to talk about total mechanical energy. So total energy is basically the kinetic energy plus potential energy. We know kinetic energy is half k a square minus x square. Potential is half k x square. If you solve this, you will get total energy as half k a square, which is itself a constant. Because k is constant, a is also a constant. So that means the total energy is conserved. So half k square is conserved. Okay. So total energy is equal to kinetic energy max plus potential energy max. This is also something which you can use. Now if you want to calculate the time period of an SHM, obviously K is equal to m omega square. Omega square can be written as square root of K by m, है ना? Omega can be written as 2 pi by omega. This omega can be written as 2 pi by t, 2 pi by t. So when you substitute this, you will get the value of time period as 2 pi square root of m by k. 2 pi square root of m by k. That is one formula that you have to keep in mind. Now, the case 1. Okay, you just have a vertical, you just have a spring connected to a mass and it is oscillating. So the time period, obviously it is going to be 2 pi square root of m by k. That is not something which we are concerned of. But over here also, if you get something like this, that it's oscillating something like this, or in an inclined plane it is oscillating, in both the cases also you will get the same time period. 2 pi square root of m by k. Now I'll tell you why. Because in all of the three cases, the spring is directly connected to the mass. The spring is directly connected to the mass. Over here also it's directly connected. Over here also it's directly connected. But over here in case 4, that is the problem. In case 4, if you all notice, the spring is not connected directly to the mass. It is over a pulley and then it is connected. Over here the spring is connected to the pulley, and over here the spring is again connected to the pulley and then a mass is connected. So if you want to find out the time period in all of these cases, then what do we have to do? I have a simple formula for you all. The formula still remains the same, that is T is equal to 2 pi square root of m by k, but over here k dash, over here k is replaced by k dash. Now what is this k dash? K dash is basically tension in the mass divided by tension in the spring ka square into k. What did I do? What is k dash? Tension of the mass divided by tension of the spring, the whole square into k. Chamka. Clear? I'll tell you. Over here, this is the tension, same string, tension. So what is the tension in the mass? It is T. What is the tension in the spring is again T. So again, the k dash will be equal to k. In this case, the T dash will be equal to k. No issues. So for this case, it's going to be 2 pi square root of m by k. Over here, tension T, but in spring it will be 2T. So over here, tension in the mass is T, but tension in the spring will be 2T. So it will be half ka square, that is 1 by 4. Yes, I will solve, don't worry, I will solve. So it will be 1 by 4. So k dash becomes k by 4. Over here, k by 4. Then substitute over here, 2 pi square root of m by k by 4. Over here, tension T. So this becomes tension 2T. So tension in the mass is 2T. Tension in the spring is T. So this becomes k dash is equal to 4 times of k. Just substitute over here and you will get your answer. Chamka. Combination of spring. Okay. Combination of spring. We're going to talk about series combination. Again, it's the ulta of resistors and everything. If it's a series combination, this is the combination formula. And if it's a parallel combination, this is the combination formula. I don't think so. This is difficult. Yes, I will solve, Shania. Don't worry. I have a lot of questions. Lots of questions. Don't worry. I will solve. Okay. I will solve. So once the theory gets completed, I will solve the questions. Okay, Shania? Okay. Chalo. For a simple pendulum, again, the formula is again 2 pi square root of L by G effective. Why is this G effective? Because the value of G can change. Hai na? If it's in an accelerated frame, or if you have a electric field in place. Hai na? So this is G effective. Okay, this we all know. Hai na? Now this angle, now the oscillating pendulum can only be considered as an SHM if the value of theta is less than 5 degrees, because this has to be a straight line. This You know, this cannot be considered as SHM. Only this can be considered as SHM. This can be considered as SHM. Are you able to understand? Yes. Yeah, oscillation of simple pendulum in electric field. This is something which you have to understand. Okay, this is something which you have to understand. if you all notice, if the electric field is upper, is in the upper direction, this is a plus q charge with mass m. So obviously mg will be over here and qe will be the force due to the electric field, है ना? And I am assuming that mg is greater. Mg is greater. So what will be the g effective? Mg minus qe divided by m. This is going to be the g effective. Are you able to understand this? Similarly, if the electric field is down, so mg is down, qe is also down. So g effective will be mg plus qe divided by m. If the electric field is in this direction, so qe is over here, mg is over here. Both are at 90 degrees, so the resultant will be over here. What is the resultant? What is the resultant? Square root of mg square plus qe square, the whole divided by m. That's it. That's it. Chamka? Chamka people? Yes or no? Chamka people, yes or no? Okay. Chalo. This is something very important. Physical pendulum. Physical pendulum. That means if they ask you about a physical pendulum, the formula is 2 pi square root of I divided by mgl, where I is basically the moment of inertia about the pivoted point and L is the distance between the center of gravity and the pivoted point. So if this is the center of gravity and this is the pivoted point, the distance between these two is basically L, and I is the moment of inertia about this fixed point. Okay, that is one formula that you have to keep in mind. Okay, people. Okay, pookie. Okay. Now, SHF of a body in a tunnel along chord of the earth. This thing you have to keep in mind. Okay, so if there's a tunnel along the diameter of the earth, and if you drop a substance, if you drop a thing, it will oscillate in that tunnel, and the time period of that oscillation is basically going to be 84.6 minutes. This you have to remember, है ना? And the formula from how you derived is 2 pi square root of r by g. 2 pi square root of r by g. Okay, and any other chord also, if you take any other chord, the time still remains the same. The time still remains the same. This is something which you have to keep in mind. Okay. Okay. Yes or no? Yes or no? Okay. Now, oscillation of a floating body. Oscillation of a floating body. Okay. So basically, you have a substance. It is floating on the water. And if you just give it one push, it will start oscillating something like this. The time period in that particular case is going to be 2 pi square root of m divided by a rho g, where m is the mass, a is the area. A is the area of cross section, rho is the density of the fluid itself, and g is basically the acceleration due to gravity. It's going to be 2 pi square root of m divided by a rho g. M divided by a rho g. Okay. Chalo. Oscillation of a liquid column. Again, it's a very important thing. So if you all notice, the liquid column में ये मैंने नहीं पढ़ा अभी तक, तो पढ़ लो. तो the oscillation of the liquid column, it oscillates something like this. What is the oscillation? What is the time period of this oscillation? Again, a very important formula. Same thing. 2 pi square root of m divided by a rho g, but sine theta 1 plus sine theta 2. This is a very important one. Now, what is the theta 1, theta 2? This is the theta 1, theta 2 that I'm talking about. Now, in this case, the theta 1 and theta 2 are 90 degrees. In this case, the theta 1 and theta 2 are 90 degrees. Are you all able to understand this? I'll just solve a question. If you all want to. Yeah, this one. Yes, this is the question. What? The period of oscillation of mercury of mass m and density rho poured into a bent tube of cross-sectional area S, whose right arm forms an angle theta with the vertical as shown is given. Okay. As shown in the figure. Acha, what is the time period? So basically, people, this is 90 degrees. Sorry. This is 90. This is 90 degrees. If this is theta, this is basically 90 minus theta. This is 90 minus theta. Are you all able to understand this? So the formula comes out to be T is equal to 2 pi square root of m divided by a, that is a is s, this is rho, sine theta 1 plus sine theta 2. Sine 90 is 1. Sine 90 is 1. So this is 1. Sine of 90 minus theta is cos theta. So m divided by s rho 1 plus cos theta. M rho 1 plus cos theta. A rho g. A rho g. Yes. So option C is your right answer. Okay. Okay, Chamka. Very good. Okay. Now let's talk about waves. Just a second, people. अरे किधर गया? Oh, waves is over here. Just a second, people. Just a second, okay? I have to import it. Yes, just a second. Yes, it is a PYQ. It is a PYQ. Okay. Let it just import and then we'll start with waves, okay? Then only 2 chapters remaining. है ना? Then only 2 chapters remaining. I guess it's a NEET PYQ itself. Okay, chalo. Let's start with waves. We do the PYQs also. Don't worry about that. We'll do the PYQs as well. Okay. Ready? Chalo. Let's start. So what is a wave, people? Wave is nothing but the disturbance from the equilibrium position which travels. है ना? So the particle itself is not traveling, but the disturbance is traveling. The momentum is getting transferred. The energy is getting transferred. Yes or no? Yes, the momentum itself is getting transferred. The particle is not traveling. So the disturbance is traveling, not the particle. Particles only oscillate about their mean position. Are you all able to understand this? Are you all able to understand this, people? Yes or no? Yes or no? Do you want a quick visualization of this? If you want a quick visualization of this, I need fire in the chat box. Okay. So this is a form of energy or momentum transfer. So this is a very good definition of wave. Okay. Now, disturbances can be in the disturbance can be in the form of many things. Okay, it can be of many things. That means, okay, I have many fire in the chat box. Okay, I'll show. So disturbance may be in the form of displacement, that is the wave on a string, the displacement. Pressure also, pressure differences also. So when we are speaking, there is pressure differences, compression, rarefaction. So that is also how a wave can travel. Density variation also. Now this density and pressure variation we are going to talk about in sound waves. And electric and magnetic field, that is we are talking about in electromagnetic waves. Okay, so we have got a lot of fire in the chat box. Okay, chalo. Wait, slow. See this, people. Okay, see this. Very, 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 very important. Very, very important to understand. So see, you are able to see that the wave is traveling, in this direction. है the wave is traveling in this direction. But if you are able to see, if you notice one particle, that particle is doing SHM, this particle is doing SHM, but you feel like the wave is traveling. If you look upon any particle, just grab on that particle, it is just doing SHM. It is just doing SHM. Are you all able to understand this? Are you all able to understand this? So each particle is just doing SHM. The particle is not moving, the particle is just oscillating about the mean position, but the wave is traveling. You feel as if the wave is traveling. So this wave is only responsible. Yeah, so this wave is only responsible for the energy and momentum transfer. You can transfer energy and momentum from one place to another, but the oscillation, but the particle itself is not traveling. Just see this, no, just grab any one particle, just one, this green particle, yeah, this green, yeah, see this is oscillating, yes, chamka, this is a wave, are you able to understand this? Chamka, very good. Okay, so let's move ahead. Types of waves, again people, it's a again very easy thing. Mechanical wave, non-mechanical wave. Mechanical wave actually requires medium. Examples are sound waves, waves on a string, and waves in air column. Okay, non-mechanical wave does not require any medium. So for example, electromagnetic wave. Okay, then transverse and longitudinal wave, again that is very much easy to understand. What is transverse wave? Transverse wave is basically the particle oscillates in this direction, and the particle oscillation is perpendicular to the direction of wave. So oscillation is in this direction, and the particle wave is traveling in this direction. So that is how wave is formed. So if you all notice, I'm basically forming a wave, oscillation, and I'm giving it a push. So if you all notice, I'm forming a wave. Are you able to notice that? Yes, that is transverse wave, and longitudinal wave is this, basically this much. So the direction of oscillation is in parallel to the direction of propagation of wave. Okay. Equation of wave, general equation of wave. Okay, people. So again, y over here corresponds to the displacement, pressure, density, or electromagnetic wave. It can mean anything. है ना जी? And it is the displacement of the particle from the mean position, because the particle itself is doing SHM, people. The particle itself is doing SHM. है ना जी? So now, right now, you have to understand that this y is a function of time. Obviously, in each time it will have different position. Yes or no? See over here, in each time, see at time t1 it is over here, है ना? At time t1 it is over here. At time t2 is over here. At time t3 it is over here. So at different times it is having different positions. You are able to understand this, and it is also function of x, that is displacement, also a function of x. That means for every x you are getting a new particle. See, for every x you are getting a new particle. This is it for x1, this is for x2, this is for x3. For every x1, x2, x3 you are getting a new particle, and for every time you are getting different positions of the particle. Are you all able to understand this? Yes or no? Yes or no? That is the reason this y is a both function of x and t. What is y? Y is the displacement of the particle from the mean position. This is the y. This is y. What is x? This is x. That how far is it from the mean position? How far? Are you able to understand this? And time is basically time. वो तो time है. Okay. So if I want to draw this, it is something like this. If this is the wave, है ना? So this particle is basically at x1 distance. This particle is basically at x2 distance. And what is y? Y is basically this thing, this displacement that I'm talking about. This is the displacement that I'm talking about. Okay, cool, very good. Okay, next. Okay, Now, okay, this thing you can leave right now. Now, this is a very important thing, very important thing. The velocity of wave is basically omega by k, or coefficient of t divided by coefficient of x. Coefficient of t divided by coefficient of x. This is a very important thing that we are going to study right now. Okay. So we are just revising concepts over here. Okay, now let's talk about plane progressive or harmonic wave. Let's talk about plane progressive or harmonic wave. Wave in which all particles do SHM are called plane progressive traveling harmonic wave. Okay, now let's understand. Okay, the equation of this wave is y is equal to a sine kx plus minus omega t. Now, over here, this x corresponds to that it is traveling in the x direction. Now, is it traveling in the positive x direction or in the negative x direction? That we're going to look after. In some time. Okay. So, y is the displacement of the particle from the mean position. So, how much far is it from the mean position? That is y. A is the amplitude. K is the wave number. That is k is equal to 2 pi by lambda. This is something which you have to keep in mind. A very important thing. And omega is the angular frequency. That is 2 pi f is equal to 2 pi by t. Everything is very much clear over here. Okay. And this is the velocity of the wave. Velocity of the wave is coefficient of t divided by coefficient of x. What is the coefficient of t? It is omega. What is the coefficient of x? It is k. So omega by k is the velocity of the wave. Now, velocity of wave and velocity of the particle are totally two different things. What is velocity of the wave? The velocity of the wave is by the velocity by which the wave travels. Velocity of the particle is the velocity of the particle doing SHM in the wave. Are you able to understand this? Okay. And omega can be written as 2 pi f. K can be written as 2 pi by lambda. So, velocity of the wave can also be written as frequency into lambda. Yes or no? Now, the frequency only depends upon the source. It does not depend upon in which refractive index you are. It does not depend. Frequency you can't change. At all. If you change the source, the frequency will change. Other than that, the frequency is never going to change. But lambda, it depends upon the medium as well. Okay, the wavelength. Okay, people. Okay. Yes or no? Now let's talk about the direction. Okay, if it is same sign, if the coefficient has same sign, omega is plus, k is also plus. This is also minus k, this is also minus omega. Same sign, that means it is traveling in the negative x direction. If it is the opposite sign, minus k plus omega, plus k minus omega, then it is different sign, that is wave is traveling in the positive x direction. Clear? Okay. Equation of harmonic wave. So see this, omega t minus kx, opposite sign, that is traveling in positive x direction. Now I can substitute omega as 2 pi by t, k as 2 pi by lambda, so I'll get this variation. I take 2 pi out, I take lambda out. So these are basically all of the variations that I'm getting over here. And all of this is a harmonic wave. All of them are a harmonic wave. Okay. Now let's talk about phase and phase difference. Okay. Now we all know that this is called as phase. Okay. So I'm taking two waves over here. So one wave is y1 is equal to a1 sine omega t. This is the first equation and this is the second equation. What is phase difference? Phase difference is basically the difference between the two phases. So phi 2 minus phi 1, this is basically the phase difference between the two waves. That means that's it. Khatam, baat khatam. Are you able to understand this? Okay. Next, wave velocity and particle velocity. Again, I've already talked about this. But let's look upon it. So if this is the wave, the velocity of the wave is omega by k or n lambda or f lambda. But the particle velocity, so the particle inside the wave which is doing SHM, that obviously it is going to have a omega as the maximum velocity, or exactly the SHM equation, that is v is equal to omega square root of a square minus x square. Same thing over here, Or you can basically differentiate this to get the particle velocity, that is dy by dt. You can even do that. Okay, people. Chamka. Is it clear? Is it clear, people? Is it clear, people? Yes or no? Yes or no? Very good. Okay, now we're going to talk about relationship between wave and particle velocity. So particle velocity is equal to minus of wave velocity multiplied by dou y by dou x, where this is the slope of y by x. Slope of y by x. Again, very important to understand. It's very easy also. It's very easy also. If you all notice over here, the slope is positive over here. So dy by dx is positive. Dy by dx is positive. And the wave is traveling in this direction. That means it is in the positive direction. So this is positive, but we have a negative sign over here. That means the particle velocity is in negative direction. Is in negative direction. So it will have a negative velocity over here. Are you all able to understand this? Are you all able to understand this? See this. See this. So all these things will have positive velocity over here. So dy by dx is positive. And wave velocity is in this direction, that is positive. This is positive, but this is negative. That means velocity of the particle is negative in total. In total, it is negative. That is the reason every particle will have negative direction over here. Now, from over this point to this point, this whole slope is negative. This whole slope is negative. So this is negative. This is positive. This is negative. So that becomes positive. So particle velocity is positive. That is the reason everything is up. Everything is up. Are you all able to understand this? Are you all able to understand this, people? Yes or no? Yes or no? Okay. Now acceleration of the particle. Again, acceleration of the particle is again same. If the velocity is basically minus a omega, then maximum will be minus omega square into y. This is very much intuitive. Again, as it is doing SHM, it is going to have the same formula. It is going to have the same formula. It will have maximum acceleration at the extreme position, omega square into a. Yes or no? Again, very intuitive formulas. Again, very much intuitive formulas. Okay, people. Yeah, now this speed of wave on a string. Okay, so if we have a string and we need to calculate the speed of wave, it is again v is equal to square root of t divided by mu, where mu is the mass per unit length. Mass per unit length. Mass per unit length. Are you all able to understand this? So if you have a string of length L, density rho and radius r, I can write mass as density into volume. So density is rho, volume is pi r square, that is area into length. So this is basically the mass that I'm getting. So mass per unit length is rho pi r square. Rho pi r square. I can basically substitute over here and I get it as v is equal to square root of t divided by rho pi r square. Again, velocity of wave depends upon the medium. But the lambda also depends upon the medium, but the frequency does not depend upon the medium. It only depends upon the source. Okay, clear? Clear? Next, intensity of the wave. What is intensity? Intensity is basically the amount of energy which passes through a particular area in per unit time. It is called as intensity. So intensity is what? Amount of energy passing through per unit area in per unit time is called as intensity. Okay. Now this is one important formula of intensity that you have to keep in mind. 2 pi square f square a square rho into v. This is very important formula that you have to keep in mind. And from this only you are able to understand that intensity is directly proportional to a square. Intensity is directly proportional to a square. Am I clear? Am I clear? Yes or no? Am I clear? Yes or no? Okay. This is the thing that you understand. Now over here, f is frequency, a is amplitude, rho is density of the medium, and v is velocity of the wave. Okay. Let's move ahead. Now intensity with distance from the source. Okay. Now, if it is a point source, so intensity is inversely proportional to the distance square. But if it's a linear source, then it is just inversely proportional to the distance. That is something which we have to talk about. Yes, you can art with Yuan. Yes, you can. Yes, you can. So for point source, it is d square. For linear, it is d. Okay, cool. Chalo. Now see this, people. Now how many of y'all want a visualization of this thing? Reflection and transmission of wave on a string. Do you want that visualization? Do you all want the visualization? Yes or no? If you want the visualization, I need fire in the chat box. I need fire in the chat box. Yes. Okay, good. See this. So let's talk about transmission and reflection of the wave on a string. Okay. So see this. The velocity remains the same in reflection, but in transmission it changes because the medium changes. As I said over here, that the velocity of the wave depends upon the medium. In transmission, as it is changing from one medium to another medium, obviously the velocity is going to change. The frequency only depends upon the source, so it is going to be same across both of them, reflection and transmission. It will improve, Yuvan. You have to give time for that. Wavelength also same for reflection, but again for transmission it will change. Now the phase difference. Let's talk about the phase difference. Now in reflection there is going to be a phase difference of pi. So if the wave is traveling like this, if it gets reflected, it will just rotate and it will travel like this. There will be a 5 phase difference. Okay, there will be a 5 phase difference. Are you able to understand this? Now this will only happen when it is going from rarer to denser medium. If it is going from denser to rarer medium, then there is no phase change which will happen. There will be no phase change that will happen. Now I'll give you a visualization for this. See this over here. Stop. Restart. Fixed end. Yeah, see this, people. Okay, this is a denser medium right now. This is a rarer medium right now. So see what happens. See this, okay? So it's going. Denser medium, phase change. Understood what happened over here? है ना? Rarer medium, rarer, denser medium, phase change, spike. Understood, people? Yes or no? But if this is a rarer medium and if this is a denser medium, let's look upon that. See this. Rarer, sorry, denser. Oh, strike and say. Able to understand this? People? Able to understand this? Clear? Yes or no? Yes. Pakka? Chamka? Yes sir, chamka. Very good. Yep, very good. Yeah, so that is the thing that we have to note. Chamka. Very good. So see over here, reflection of wave from fixed end. What is happening? So see, this is the thing, people. From fixed end. See, 5 phase change. 5 phase change is happening. See this? Able to understand? See a 5 phase change. This is also a fixed end. That is the reason. 5 phase change. So that is what is happening over here also. Reflection of wave from fixed end. No loss of energy. If amplitude A is going there, amplitude A will come back over here with 5 phase change. And see, if the incident wave is A sin kx minus omega t, the reflected wave will be minus of A because obviously it's in the minus direction, and kx plus omega t because it is in the negative x direction. Chamka. Reflection of wave from free end. Now let's talk about free end. If this is a free end, what is happening? See, it will go there, and no phase change. Now this is a fixed end, so phase change will take place. See, phase change has taken place. That is a free end, so no phase change. It will come as yes. Chamka. So reflection of wave from free end, it's going over here, it's going over here, and no phase change, it will come over here. No loss of energy again. So A sin kx minus omega t, and again this is no phase change, so A sin kx plus omega t. Just the direction is reversed. Just the direction is reversed. Chamka. Okay. Reflection and transmission. Again, from rarer to denser medium, what is happening? This is denser medium. So incident ray, denser medium, phase change will take place. Phase change will take place, and obviously it's going to travel also somewhere. Transmission also will takes place over here. Transmission also will takes place. Again, this is something which will not be asked. It's just thoda sa. Okay, now let's talk about standing wave and stationary wave. What is a standing wave or a stationary wave? Standing wave and stationary wave is actually not a wave. Is actually not a wave. Is actually not a wave. Why it is not a wave? Because you cannot transfer energy and momentum. That is the reason it cannot be. Goes against the definition of the wave. No energy or momentum transfer takes place over here. Okay, no energy or momentum transfer takes place over here. So when is a stationary wave or a standing wave produced? When two harmonic wave of equal omega and equal amplitude traveling in the opposite direction superimpose, interfere each other, standing waves are formed. So basically, when is the standing wave formed? When two harmonic waves of equal omega, equal amplitude traveling in opposite direction superimpose or interfere with each other, standing waves are formed. Okay, so what exactly is a standing wave? So what exactly is a standing wave? This is a standing wave. So what is happening? It's something like wing, 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 wing. So basically, all the particles are reaching their maximum amplitudes together. All the particles are reaching their mean positions also together. See this? Wing, 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 wing. Are you able to understand this? Are you able to visualize this, people? Are you able to visualize this, people? Yes. So the wave itself is not moving forward. It is just oscillating over there. It is just oscillating over there. Something like wing, 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 wing. Yes or no? Yes or no? Yes or no? Okay. So what are the conditions required, people? Conditions required, it should be in the same medium, and amplitude, frequency, omega should be same, travel in the opposite direction, k also should be same. K also should be same. Okay. Now let's talk about the equation. Now people, that is when two harmonic waves, so y1 is equal to a sin kx minus omega t is traveling in this direction, y2 is traveling in this direction, they are gonna interfere. Interfere is basically add them up. So what is the thing? This is the equation that you get. This is the equation for the standing wave that you get. That is it, 2 sin kx cos omega t. That is the equation that you get. Now people, you will notice that if somebody asks in which direction is this traveling, you will not be able to say so, because in here you are able to see it is kx minus omega t. Here also you are able to see it is kx plus omega t. But over here there is no such term of kx plus omega t or kx minus omega t. That is the reason this is called a standing wave. Are you all able to understand this? Chamka? Chamka, yes or no? No. Stationary wave, no kx plus minus omega t. Okay, and these are all the formats of stationary wave that you can get. Okay, clear? See this. Now I'm going to use this equation, that is 2a sin kx, k is 2 pi by lambda, omega t, that is omega is 2 pi by t, this equation. Okay, see this, how the standing waves are formed. How the standing waves are formed. If you all notice, at t is equal to 0, at t is equal to 0, you will get y is equal to 2a sin kx. So basically you will get a sine curve. At t is equal to t by 4, you will get y is equal to 0. So all of them reach their mean positions together. Then again at y is equal to t by 2, you will get y is equal to minus 2a sin kx. You will get this curve. You will get this curve. Then again at 3t by 4, again 0. Again at t is equal to t, you will get this equation. So are you all able to understand? So this becomes wing, 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 Are you able to understand this? Are you able to understand this? How the stationary waves are formed over here? How the stationary waves are formed over here? And there are some points which are not oscillating at all. Like for example, this point, 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 this point. These points are called as nodes. These points are called as nodes. They do not oscillate. They do not oscillate. They just remain over there. And there are some points which give us the maximum amplitude. This point, this point, this point, this point, this point. They are called as antinodes. They are called as antinodes. Okay. So see this. Let's talk about some properties over here. All particles, they execute SHM, but with different amplitude. Yes. Yes. See, this particle has different amplitude. This has different amplitude. This has different amplitude. But in harmonic wave, all of them have the same amplitude. In this, they have different amplitudes. Particles having maximum amplitude are called antinodes. Minimum amplitude are called as nodes. They never move from their mean position. Yes. Yes. Like it, people. Now, over here, all the particles in this segment are in phase with each other. Why they are in phase with each other? Because they are reaching their maximum position together. Over here also they are in same phase because they are reaching their maximum position together. But this segment and this segment are in opposite phase to each other, or they have a phase difference of pi, because they are reaching positive amplitude together, they are reaching negative amplitude together. So the difference between them, phase difference, is pi. So the same segment particles have no phase difference, but opposite segments or the corresponding segments have a pi phase difference. Are you able to understand this? So particles of one segment are all in the same phase, but with adjacent segments in opposite phase, that is pi phase difference is there. Okay. All particles reach their maximum displacement simultaneously. 2 in one time period, all particles reach their mean position. Yes. So this is, again, we have all covered this. Okay. Now, this is a very important thing. A very important thing. Nodes and antinodes. So the distance between two consecutive nodes is lambda by 2. Distance between two consecutive antinodes is again lambda by 2. Distance between node and antinode is lambda by 4. Again, this is a very important thing that you have to understand. So this distance, like this distance, is lambda by 4. This is again lambda by 4. This is node, antinode. Lambda by 4, lambda by 4. So the distance between two nodes is lambda by 2. This becomes lambda by 2. So if somebody asks you to calculate what is the distance between this point and this point, it's very easy. Lambda by 4, 2 lambda by 4, 3 lambda by 4, that is your distance. That is your distance, and that is how you should calculate. Chamka? Chamka, yes or no? Chamka, yes or no? Yes or no, people? Chamka? Very good. Just a second, people. Okay, chalo. Now let's talk about stationary waves. In a string. Okay. All of the fixed points will always produce a node, and a free end will always produce an antinode. That is one thing for sure. Now the fundamental mode, or fundamental tone, or principal tone, or first harmonic. Sir, need a break? Okay, just a second, people. Just a second. Okay. We'll complete this. We'll complete this wave. Sound waves I will do after a break. Okay. Sound waves I'll do after a break. Okay. If you all notice, this is the fundamental mode. Like, is it wing, 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 wing? It is going something like this. So if you all notice, the length of the string is L over here. But how did we come across this lambda by 2? We all know distance between node and antinode is lambda by 4. So this is lambda by 4 and this is lambda by 4. So together it is lambda by 2. So can I basically say L is equal to lambda by 2? Lambda comes out to be 2L. Now frequency is basically V divided by lambda. I know this relation. So lambda is 2L. So frequency comes out to be V divided by 2L, and that is basically your fundamental frequency, or your fundamental frequency. F1 is equal to V divided by 2L. Clear? Clear? Next, first overtone or second harmonic. Now in this case, your second harmonic is basically the number of segments basically. The number of segments basically. So second harmonic मतलब two segments. First segment, second segment. है ना? So over here length L, but what is the distance? Lambda by 4, 2 lambda by 4, 3 lambda by 4, 4 lambda by 4, which is exactly lambda, which is lambda. So L is equal to lambda, F is equal to V by lambda, which comes out to be V by lambda. I give 2 upon, I multiply and divide by 2 on the denominator. So I get 2 times of F1. So that is what I get. F2 is equal to 2 times of F1. Similarly, for second overtone or third harmonic, that means 3 segments. 3 segments. 1, 2, 3. L is the length. Lambda by 4, 2 lambda by 4, 3, 4, 5, 6. 6 lambda by 4. That is 3 lambda by 2. That is what you are getting. So L is equal to 3 lambda by 2. Lambda is equal to 12 by 3. F is equal to V by lambda. Just substitute, what do you get? 3F. 3 times of F1. So F3 is equal to 3 times of the fundamental frequency. That is what we are getting. So the number of segments is actually equal to the antinode as well. See, three segments. So 1, 2, 3. 3 antinodes also we are getting over here. And node is basically one more than the antinode. So see this 1, 2, 3. 3 antinodes. 1, 2, 3, 4. 4 nodes we are getting over here. Yes or no? So if somebody asks you 6th overtone, 7 segments, 7th harmonic, we have to find out. है ना? So 7th harmonic मतलब 7 segments. So these are 7 segments over here. What is going to be the value of antinode? 7. 7. Nodes will be 8. Nodes will be 8. If somebody asks you the frequency, so this is lambda by 4, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 lambda by 4. 14 lambda by 4. That is 7 lambda by 2. That is exactly what I have written. 7 lambda by 2. And this comes out to be 7V by 2. Well, 7 lambda by 2. Chamka. Chamka. Okay. So I'm going to give you a 15 minutes break over here, people. Okay. I'm going to give you a 15 minutes break over here. Okay. I'll also eat food fast. Okay. I'll also eat food fast and then I'll come. Okay, people. 15 minutes break for you all. Okay. Okay. I'll come by 3. I'll come by 3. Okay, people. I'll come by 3. Okay. चलेगा? चलेगा? Okay. Mic testing 1 2 3. 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 Yes. Mic testing 1 2 3. People, let's start. Audible. Let's go. Now let's start with sound waves. Okay, let's start with sound waves. Okay. Okay, let's start with sound waves. Okay. Next. So people, what do we have to do? So sound waves is basically it's a longitudinal wave. It can be characterized into three parts basically. Infrasonic wave, so longitudinal waves with frequency less than 20 hertz. Audible wave, so the waves that which we can hear or the human ear can hear is somewhere between 20 hertz to 20 kilohertz, and ultrasonic is basically greater than 20 kilohertz. Okay people, so that is something which we want to know. Okay, so let's move ahead now. Sound waves, they travel due to pressure and density variation. That is something which you should know. Okay, so as I said that the displacement or the Y can have many meanings. It can have displacement, pressure variation, density variation, electromagnetic field variation. These four things that can vary, but for sound waves to travel, it has to have pressure and density variation. Okay people, cool. So in compression the pressure is maximum. Obviously the pressure is maximum, and due to the pressure is maximum, the volume is minimum, so the density is maximum over here. Okay, and in rarefaction the pressure is minimum, the density is also minimum. Okay, cool. Next, this is what is happening. Compression, rarefaction, compression, rarefaction, compression, rarefaction, compression, rarefaction, and this is how the disturbance follows. This is how the disturbance it travels. This is how the disturbance it travels. Okay people, yeah, equation for the sound wave. Equation for sound wave. Now, what is S? S is basically the particle displacement in the x direction. Okay, so basically it's a longitudinal wave, so the oscillation is also in the x direction, and also the direction of propagation is also in the x direction. Okay people, so what do you have to do? What do you have to do is basically this direction is called as forward, this is called as backward. This is forward, this is backward. Forward is plus and this is negative. So see this corresponds to the positive one, this corresponds to the backward one. Positive, backward. So see, it's traveling something like this. It's traveling something like this. Are you able to understand? Yes or no? Are you able to understand it? Yes or no? So it's traveling something like this, something like this, something like this. Okay people, okay. So A sine kx minus omega t again is your equation, where S is basically your particle displacement in the x direction. Now, density and pressure will also have an equation because it changes. It is not constant. It is going to have a very similar equation. It is going to have a very similar equation. Now, one thing which you have to note over here. Pressure wave equation. Here, pressure also varies harmonically. Here also pressure also varies harmonically. Now what is happening? See, in normal conditions the pressure value is 1 atm or 10 raised to 5 pascals, but the pressure maximum is 20 pascals. Over here. Okay, that is the change in pressure. Maximum change in pressure is 20 pascals. So what is happening in compression? If you all notice, the boundary is having delta P as 0. As you're moving inwards, as the air is getting compressed, the delta P is 10 over here, and the maximum change in pressure is 20 over here. Are you able to understand this? In the same way, in rarefaction, the outer boundary has the change in pressure as 0. As you move on inwards, the change in pressure is minus 10. And the maximum change in pressure is minus 20 for the most inward part. Are you able to understand? This people? Yes. And this is how the disturbance it moves forward. Okay. Let's feel the pressure equation right now. Okay, let's feel the pressure equation right now. Now see this is a very important graph to understand. See this people. If you all notice about this particle, we have to look on the neighborhood of it. This particle is going up, this particle is going down. This particle is going up, this particle is going down. That means one particle is going this side and the other particle is going this side. So this is the particle, one particle is going this side, other particle is going this side. That means rarefaction is taking place. Rarefaction is taking place. And due to rarefaction taking place, the delta P is going to be minimum. Are you able to understand this? Now, if I talking about this B particle, talk about the neighborhood. One particle is upwards, this particle is also upwards. Both are upwards, both are in the same direction. So this is B, one particle is over here and the other particle is also over here. Over here, delta P is 0 because this particle is also moving in this direction, this particle is also moving in this direction. The net change is 0. That is the reason delta P is 0 over here. Chamka. If I talk about C particle, one particle is upwards, the other particle is downwards. So upwards, downwards. Compression is taking place. So over here, delta P is maximum. D. Downwards, delta P is again 0 over here. Are you all able to understand this? People? So over here, you are able to understand at A, you are getting A as P, delta P as minimum. So at A, delta P is minimum. At B, it is 0. At C, it is maximum. At D, again, it is 0. So you are getting a sine curve over here. So you are not getting a sine curve, you are getting a cos curve over here. Minus cos curve over here. So the one thing that you understand, when the displacement is node, the pressure is antinode. When the displacement is antinode, the pressure is node. Node, antinode. Antinode, node. That is one thing which you have to keep in mind. It is a very good assertion reasoning question. Okay. Now over here, the equation comes out to be, again, it's a minus cos curve. So obviously delta P is equal to minus delta P naught cos of kx minus omega t. That is basically your equation. Okay. Now speed of sound. Longitudinal wave, speed of longitudinal wave, it's basically V is equal to square root of E divided by rho. Now E is basically coefficient of elasticity. It can be Young's modulus, bulk modulus, anything. It can be anything. Depends upon what you want to do. Okay, that is what. Now, the velocity of the sound in solid is much more greater than in liquid and much more greater than in gas. Now, obviously, this is a very, very intuitive thing because obviously the molecules are very tightly packed with each other, and that is the reason you get the velocity of solid as maximum. Okay. In fluids, you use bulk modulus over here. In solids, you use Young's modulus over here. Okay, people? Very easy to understand. Now, speed of sound in air according to Newton, and obviously this was a mistake, but again, it was a very good mistake so that we could understand everything. Now, according to him, according to Newton, sound traveled in the air isothermally. Now, this was the mistake actually. So he thought that delta T is 0 over here. Whenever sound travels, there is no change in temperature. Temperature is constant. Now, this is one thing that you have to keep in mind, that bulk modulus for an isothermal process comes out to be equal to the pressure. Okay. So V is equal to bulk modulus divided by rho, the square root of it. Bulk modulus is equal to pressure. So this comes out to be 280 meter per second. But practically and experimentally, it came out to be 332 meter per second. So what is this mistake? That was corrected by Laplace himself. So Laplace said, no, it is not isothermally, it travels adiabatically. That is, there is no exchange of heat. That is, delta Q is equal to 0. And adiabatically, the bulk modulus comes out to be gamma times of P. So when you substitute this over here, you get it as 332 meter per second. Are you all clear? And over here, gamma is equal to 1.4 because maximum it is of nitrogen and oxygen. Okay. Maximum air is composed of nitrogen and oxygen. Okay. This is also a very important formula. Very important formula in terms of temperature. Square root of gamma R divided by m naught. Okay, people. Very, very important formula. Now let's understand what are the factors affecting the speed of sound in air. First one is temperature, directly proportional to the square root of temperature. From this formula you are able to understand. Okay. Pressure, At constant temperature, no effect of pressure. This is a very important term. Very important term. Many people, they think it is directly proportional. No, it is not directly proportional. If the temperature is constant, then there is no effect of pressure. That is something which you have to keep in mind. Okay. Humidity. Humidity you have to understand. So a humid air will have more water molecules. So the density is less over there. The density of moist air is less in compared to the density of dry air. So velocity of the sound wave is inversely proportional to the density. Okay. Clear. Now we are going to study about organ pipe. And that's it. Okay, people? And that's it. We're going to study about organ pipe. Let's study about organ pipe. Okay. So organ pipe, there are two types of pipe. Open, that is both ends are open, and closed, that is one end is closed. Okay. Closed organ pipe. What happens in closed organ pipe? In closed organ pipe, the closed end will always form a node, the open end will always form an antinode. Okay, people? So over here you have to understand, closed end will form a displacement node. So here it will be displacement node, but pressure will be maximum over here. That is something which we have already studied. Over here antinode, the displacement is maximum, but the pressure change is 0 over here. And this we have already looked upon in the graph. Clear, people? Clear, people? I need you all to like the session, people. Yes. Let's talk about fundamental tone or first harmonic. Again, very easy. So one node, antinode, this is basically the thing that you're going to get. So over here, this is the length. This is lambda by 4. Distance between antinode and node. L is equal to lambda by 4. Lambda comes out to be 4L. F is equal to V by lambda. Just substitute, you will get F1 is equal to V by 4L. This is the first harmonic. Khatam. Next. First overtone or third harmonic. This is not second harmonic, people. This is third harmonic. Why? Why is it third? I'll tell you. So the second is basically get two nodes. So this is the pattern that you're going to get. Now this is lambda by 4, 2 lambda by 4, 3 lambda by 4. So you're going to get L is equal to 3 lambda by 4. Lambda comes out to be 4L by 3. When you substitute over here, you get, see what you're getting, F1 is equal to V by 4L. So this is V by 4L. So this comes out to be F1 is equal to 3 times of F1. That is the reason you are getting third harmonic over here, not second harmonic. Is this clear? Next. And similarly, for second overtone or fifth harmonic also, similarly, 1, 2, 3, 4, 5. 5 lambda by 4 you're getting L. Lambda comes out to be 4L by 5. When you substitute over here, you get F2 is equal to 5 F1. That is second overtone is equal to fifth harmonic. After this Pravin. Okay. After this. So that is what we are getting. Now let's do some analysis. So harmonics in closed organ pipe, you are getting the fundamental tone of the first harmonics as V divided by 4L. Okay. And all of the overtones or the harmonics you are getting as odd harmonics. You will only get you'll only get closed odd harmonics in closed organ pipe in the ratio of 1:357. Is this clear, people? Even harmonics are missing, and the general formula is basically the nth overtone frequency is equal to 2n plus 1 f1. Okay, so the nth overtone frequency is equal to 2n plus 1 frequency. Okay, harmonic frequency. Okay. Now let's talk about open organ pipe. Fundamental tone or the first harmonic. So open ends will have antinodes. Lambda by 4, that is lambda by 2. I'm getting L is equal to lambda by 2. So lambda is equal to 2L, F is equal to V by lambda, that is V by 2L. This is exactly what I'm getting. No problem, Ajay, no problem. First overtone or second harmonic. Again, see this 1, 2, 3, 4, 5. 5 lambda by 4. No, did I do something mistake? Just a second. 1, 2, 3, 4. Yeah, 4 lambda by 4. That is lambda. L is equal to lambda. F is equal to V by lambda. So what I'm getting over here, first overtone is equal to 2 times of harmonic, or the second harmonic. Okay. Similarly, second overtone, third harmonic. 1, 2, 3, 4, 5, 6. 6 lambda by 4 or 3 lambda by 2. So lambda comes out to be 2L by 3, which is basically second overtone is equal to 3 times of F1. So that is what we are getting. Now if you do the analysis over here, harmonics and open organ pipe, fundamental tone, just a second people. Sir, is frequency and wavelength of the standing wave equal to the two waves merging? Yes, Sharma, yes. Open organ pipe, fundamental tone, F1 is equal to V by 2L. First overtone is 2F1, second overtone 3F1, third is 4F1. So in general formula, nth overtone is equal to n plus 1 times of F1. That is the general formula that you are getting over here. Okay. Okay, people. Okay. Now let's talk about beats. Beat is again very easy, people. So it is basically the mode of difference of frequencies. That is basically the beats. And if anybody asks you about the time period, it is basically the inverse of this. And this is a very cute and important formula. Okay, people. Yes. Thank you, Tina. Now we have completed waves. Now it's time for solid mechanics. Okay. Now it's time for solid mechanics. Okay. No problem. Okay. Let's study. Okay. Let's start solid mechanics. Okay, people. Honestly, people, I'm very tired right now. I'm very tired right now. Yeah. I think so see, it's something like this. See, Yash, this is oscillating something like this. If you put weight on it, so obviously the frequency is going to decrease. If you decrease the weight on it, obviously it will have much more higher frequency. That's it. I guess the effect of medicines are coming to an end. So I'm facing a little bit problem. Yeah, I'm facing a little bit. I'm weak right now. No problem, Savita. No problem. Just a second, people. Okay, chalo. Yeah. I was not feeling well. Actually, I'm right now in medicines also. Okay, chalo. Let's start with solid mechanics. Okay, people. Let's understand. What is deforming force? No need. What is deforming force? A force that changes or tends to change the shape or size of the object is basically a deforming force. Basically, when a force which deforms an object is called as deforming force. What is elasticity? Now, elasticity actually has two definitions. But what are the definitions? This is the most apt one. What is it exactly? The property of a body to regain its original configuration after the removal of the deforming force up to its elastic limit, that is called as elasticity. That means if you have applied a force, it deforms itself. The body deforms, but it is the property of the body to come back to its original position after the deforming force has been removed. Okay, people, are you able to understand? So a deforming force, okay, you have applied a deforming force, this has deformed. See, the shape has been changed, but as soon as you removed it, it has come back to its original configuration. That means that property is called as elasticity. Okay, Now this is again very cliche question. Steel or rubber, which is more elastic? Obviously steel is more elastic because it has its Young's modulus. It's also much more greater than rubber, and also it's come back to its original position. Okay, so again a very cliche question. That is something which we can do. So let's talk about stress. So stress again has very many types of stress are there, like NEET stress, exam stress, wedding stress, and everything. But we are going to talk about physics stress. Okay. So the internal force or the restoring force per unit cross sectional area is called as stress. Okay. Now what happens is, just a second, people. Okay. So what happens is, people, is that if I have a rod over here, and I have applied some F external force over here. So this rod, if this is the area of cross section A, also has F internal force also. Okay. So the stress over here, sigma, is equal to force internal restoring force per unit area. The internal unit force applied per unit area is called the stress. But as this rod is not moving, if I hinge this rod, so obviously I can say that the acceleration is zero. So that means the net force is actually zero. If the net force is zero, I can basically say F external is equal to F internal. And in this condition, I can basically say sigma is equal to F external divided by area. Are you all able to understand this? This is the simple definition of stress. Okay. Now, it can have many types. It can have many different types of types. This is called as tensile stress. Now, tensile stress also has many types. It can be compressive, or it can be elongative one also. That is the compressive one. This is called as the shearing stress. The shearing one. Yes or no? Okay. And this is called as the volumic stress. Okay, people, are you all able to understand this? Yes or no? Yes. Okay. Now let's talk about strain. Strain is nothing. It is basically the ratio of the change in configuration. It is basically the change in configuration divided by the original configuration. This is exactly what strain is. Yes or no? Now obviously if I say over here, if I just a second, people, just give me a second. Okay, just give me a second. Okay, so over here see this. The original length was L. Now the final length is L plus delta L due to the force that you have applied. What is the change? The change is delta L. So the strain over here, okay, if I'm symbolizing with E, strain is change in length, that is delta L, divided by original length, that is, this is the longitudinal strain that I'm talking about. Okay. Now if I want to talk about shearing, shearing is nothing over here, that is, it is basically this delta X divided by the length. This is called as the shearing one, or you can also call as tan theta. Okay. Okay, people. Then we are talking about volumic. If you are going to talk about volumic, earlier it had some volume V. Due to the force or the pressure, it has compressed. So the change in volume is basically delta V over here. I'm taking a minus sign because delta V is negative over here. I don't want to play with negative, so I'm taking a negative sign over here, divided by V over here. So this is the volumic stress that I'm talking about. Are you able to understand this? Are you able to understand this, people? Yes or no? Yes or no? Tell me. Clear? Is this all clear? Yes or no? Chamka? Very good. Now let's talk about Hooke's law. Okay, now let's talk about Hooke's law. Very, 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 very important law. Let's talk about Hooke's law. Okay. What is Hooke's law? For a small deformation, the stress in a body is directly proportional to the corresponding strain. That is what we are getting. That stress is directly proportional to strain. This is what we are getting. And the ratio of stress by strain comes out to be E. Now this is only valid up to the elastic limit, which we'll be studying in future, don't worry. This is only valid up till the elastic limit. Okay, stress is directly proportional to strain, and the ratio of stress by strain comes out to be a constant, which is called as modulus of rigidity, or modulus of elasticity, sorry, modulus of elasticity. Clear? Modulus of elasticity. Okay, people. Okay, and so this will have units. The stress is basically Newton per meter square. Newton per meter square. Strain does not have any units, so the modulus of rigidity also, modulus of elasticity also has Newton per meter square. Okay, cool. Next, let's talk about Young's modulus of elasticity. Let's talk about Young's modulus of elasticity. Again, Young's modulus of elasticity is again very easy, people. Young's modulus is basically F divided by A, the whole divided by delta L by L. And this is basically stress divided by strain. So this comes out to be F divided by A. This is delta L and this is L. So this comes out to be Young's modulus value. Okay, this comes out to be Young's modulus value. Okay, and Young's modulus is again material dependent. It is again dependent upon the material itself, है ना? So even if you take 2 kg copper, 2 meter copper, 2 centimeter copper, no matter what copper you use, the value of Young's modulus is going to be same. The value of Young's modulus is going to be same. Okay, people, is this clear? Is this clear? Yes or no? Now let's talk about bulk modulus of elasticity. Bulk modulus. Again, bulk modulus of elasticity is basically the volume stress divided by the volume strain. Volume stress divided by volume strain. So this becomes F divided by A, and this becomes minus delta V divided by V. So this comes out to be F divided by A, and this is delta V for you, and this V is over here. Now what is this F divided by A? F divided by A can also be termed as pressure. This can be termed as pressure over here, है ना? So this becomes minus PV divided by delta V. This is the bulk modulus value also. Okay, this is the bulk modulus value. Okay. Now bulk modulus. Okay, so this is repeated. Now bulk modulus also done. Now one more thing which I have to tell about over here is there is something also called as compressibility, है ना? There is something called as compressibility. Okay, compressibility, which is basically inverse of bulk modulus. Okay, this is something which you have to keep in mind. Okay, people, yes or no? Now let's understand the relationship between density, pressure and bulk modulus. Okay, so density, pressure and bulk modulus. So the change in density rho dash is equal to rho 1 plus P divided by B. This is one relation that you have to keep in mind. That the change in density, the new density is equal to original multiplied by 1 plus P by B. 1 plus P by B, or you can also write this as change in pressure divided by B. Okay, people, cool. Cool people, is this clear? Is this clear? Is this clear? Okay. Now let's talk about shear modulus. Let's talk about shear modulus. Shear modulus is nothing. It is basically F divided by A and the whole divided by delta x by L. Delta x by L. So this comes out to be FL A delta x. FL A delta x, and this is shear modulus for you. Okay. This is shear modulus for you. Okay, people. And sometimes you can also write this as tan theta. So this becomes F divided by A tan theta. And as theta is very small, you can also write this as F divided by A into theta. Okay. For theta being too small. Okay. Okay, people. Is this clear? Is this clear? Next. Important note, a very, very important note. A solid will have all three moduluses of elasticity. Gamma, beta and n. All. But fluid, in case of liquid or gases, it will only have bulk modulus. It will have only bulk modulus. Okay, people. Now let's talk about potential energy stored in a stretched wire. Potential energy stored in a stretched wire. Okay. So U is equal to half into strain into strain into stress into volume. This is basically the potential energy stored in a stretched wire. Hi Anna. Hi Anna. Now you also know Young's modulus is basically equal to stress by strain. Stress by strain. So stress can be calculated as Y into strain. Stress can be calculated as Y into strain. So you can also write this as U is equal to half into stress. ये हो जाएगा strain का square ना, हाँ जी, strain का square into Young's modulus into volume. Okay. So Tina, only fluid mechanics is left right now, है ना? Fluid mechanics is left right now. So this is one more relation that you know. This is one more relation, and the last relation that people often forget is basically half load into elongation. Okay. Okay, people. Yes or no? Is this clear? Is this clear? Now let's talk about. Just a second. Now let's talk about, where is it? Yes, stress strain curve. Okay, we're gonna talk about stress strain curve, a very, very important curve to understand. A very, very important curve to understand. Okay, let's learn this. So let's talk about the region OA. I'm talking about the region OA right now. Okay. Okay, see this. So in OA, stress is directly proportional to the strain, and A is called as the proportional limit. So basically from O to A, this line is basically a linear line, and in this line the Hooke's law is followed, because after this, good afternoon Karthik, because after this the proportionality limit is not followed. Hooke's law is not followed. It is not linear at all. So from O to A, stress is directly proportional to the strain, or the Hooke's law is followed, and A is called as the proportional limit. I hope so I'm clear over here. Next. Then in AB, if you notice, now we are going to talk about this AB curve. We are going to talk about this AB curve. Nahi bhule bhai, nahi bhule. Okay. So over here, it is not at all proportional. It is not linear. So if you notice, the stress also is increasing, and also because of that, the strain is also increasing. The strain is also increasing. Are you all able to understand this? Okay. ठीक है, चलो, let's move ahead. Now you have to understand, on this B also, if you remove the deforming force, the object will return back to its original position. The object will return back to its original position. Even though Hooke's law is only followed from O to A, but also in B, if you remove the deforming force, it will come back to its original position. It will come back to its original position. That's what it's written. On removing the deforming force, wire returns to the original position. Strain becomes 0 when the stress is reduced to 0. Now elastic limit or yield point. Now this is also called as the elastic limit or the yield point. So even though in elastic limit, even though Hooke's law is only followed from O to A, even if you reach B and remove the deforming force, it will come back to its original position 0. It will come back to its original position 0. Okay. Okay. Next. Now let's talk about the other cases. Property of the elasticity reduces. Tendency to return to original position decreases. That means after B, what is happening after B? Okay. After B, on removal of deforming force, body does not return to its original position. That means obviously this is called as the elastic limit. Before this, if you remove the force, it will return back to its original position. But after this, if you cross this B, even if you remove the deforming force, it will not come back to its original position. It will have some permanent strain over here. It will have some permanent strain over here. It will not reach the original position. Okay, even though the stress is 0, but the strain is not equal to 0. That is what we are able to find out. Okay, people. Now, after B, what is happening? After B is elastic limit. Property of elasticity reduces. Residual strain, even when deforming force is removed, there is a permanent strain. That is exactly what I explained just now. Okay. At point D, now you are talking about point D. Maximum stress is there. Obviously, see, maximum stress is there. There is no more point which is greater than that. Maximum stress is there. It is also called as the ultimate tensile stress, breaking stress. And at E, it is called as fracture point. We are going to talk about it. Don't worry. We are going to talk about it. So people, one thing that you have to keep in mind is ductile material. Ductile material as those materials which can be molded into wires. D and D should be very far apart from each other. So that means in ductile material, this D and this E should have, the distance between them should be maximum in order for it to be a, in order for it to be a ductile material. But if it is a brittle material, then the D and D should be very near. So if you see over here, this is point D, this is point E. The distance is quite large for ductile material. But over here, the D and E are very close to each other. Then that is the reason this is a brittle material. Did you all understood how to identify? Yes or no? Yes or no? Yes or no? Elastomers. Elastomers is basically those substances in which you have this relation. Stress is directly proportional to stress square. Okay, you get a parabola over here. Now, iota of your heart is a perfect example of elastomers. Okay, is a perfect example of elastomers. Iota of your heart. Okay, iota of your heart. Okay, people. Now, over here, if you have a question something like this, okay, people. Which material has a greater Young's modulus? Now, I don't know if you are able to see this or not. Okay, this theta A and this theta B. I don't know if you are able to see it on the screen. But theta A over here, theta A is greater than theta B. So stress by strain is equal to Young's modulus. That is basically the slope. Over here, theta A is greater. So over here, which material has greater Young's modulus? The answer is A over here. Okay. Chamka. Which material is more ductile? Obviously, this is D, this is E, and this is D, and this is E. For it to be ductile, the distance between D and D should be more. So this is option A over here. Which material is more brittle? Obviously, B is more brittle. Okay. Which of the following is the stronger material? That is very easy. The greater the value of D, more will be the stronger. So see this. So if you will notice over here, the value of D for A is much more greater. So that means this is a much more stronger material. So option A is your answer. Okay. Okay, people. So solid mechanics also done. Solid mechanics also done. Okay. Now let's start fluid mechanics. Okay. Now let's start fluid mechanics. Okay. No break required. No break required. Let's finish it. Let's finish it. Okay. We'll do questions. Yeah. Let's start. I'm actually naturally very energetic, but I'm feeling very tired right now. Okay. Let's start. Let's start with fluids. Okay. ठीक है, चलो. Introduction. Okay. So what is it? Liquids and the gases can flow and therefore called as fluid. So fluid also does not generally mean it is just fluids. So it just liquids. So gases also comes under what? Fluids itself. Okay. So an ideal fluid is one which is incompressible and non-viscous. These are properties of an ideal fluid. It is incompressible. That means the volume cannot be changed. And non-viscous. Okay, non-viscous. Okay. Now let's understand what is pressure. Pressure is nothing. The force perpendicular acting per unit area. So if this is the area that I'm talking, okay, and if there's a force over here which is acting at angle theta with the vertical, है ना? So pressure over here is going to be basically F cos theta divided by A. F cos theta divided by A. This is basically the pressure. Over here. Okay, and pressure is a scalar quantity. Okay, chalo, next. Basic units of pressure and volume that they have to understand. Okay, basic units of pressure that you have to understand over here. Okay, so you all know that 1 atm, है ना? 1 atm. What is 1 atm equal to? 1 atm is equal to 10 raised to 5 pascals, है ना? This is one relation that you have to keep in mind, that 1 atm is equal to 10 raised to 5 pascals, and this is also equal to 1 bar. These are all conversions you should know. And it is also equal to 760 mm of Hg, and it is also equal to 760 torselli. Okay, 760 torr. Okay, people. Okay, now this is for pressure. For volume, it is very much easy, that 1 liter is equal to 10 raised to minus 3 meter cube. Okay, this is one relation that you have to keep in mind, and this is also equal to 10 raised to 3 centimeter cube. Okay, and I don't think so you need more. Yeah, I think so this is cool. Okay, people. Okay, let's move ahead. Now let's talk about pressure in fluids. Okay, let's talk about pressure in fluids. So when an object is submerged in a fluid at rest, the fluid exerts a force on its surface, and this force is always normal to the object surface, है ना? So if this is the object, it will have force from all directions. It will have force from all directions, and this force is always perpendicular to the surface. Okay, people, it is always perpendicular to the surface. That is what we are able to find out. Okay, and these are some of the values that you should know. So some of the important values that you should know is of water. Yeah, water is 10 raised to 3 kg per meter cube. Mercury is 13.6 into 10 raised to 3 per meter cube. Air is 1.29, and yeah, that's it. So air, mercury and water are the three things that you have to keep in mind. Now, what is relative density? Relative density is basically the density of the substance divided by the density of water at 4 degrees Celsius. That is basically relative density. Okay, people. Okay, that is something that you have to know. Now let's talk about density of a mixture of two or more liquids. Okay, density of a mixture of two or more liquids. Okay, so suppose we have two liquids. Suppose we have two liquids of density 1, mass 1, density 2, mass 2. So if we mix them together, what is going to be the formula over here? What is going to be the delta mixture? Okay, the density of the mixture over here. Density of the mixture over here. So density of the mixture, okay, density of the mixture is going to be basically m1 plus m2, m1 plus m2, the whole divided by m1 d1 plus m2 d2, m2 d2. Yes, this is the formula that you have to keep in mind. Okay, people. Yes or no? Now, second case, d1 v1 d2 v2. Okay, mass is not given, only the volume and the density is given. Again, this is a very important one. So d mixture, okay, d mixture comes out to be d1 v1 plus d2 v2, the whole divided by v1 plus v2. Okay, so this is the second formula that comes into mind. Okay, people. Okay, so let's move ahead. Next, variation of fluid pressure with depth. Okay, so if the pressure over here is P1, if the pressure over here is P2, and if this is the whole length, h is the whole length, so you can all write that P2 is equal to P1 plus rho gh. This is one thing that you can write over here. Okay, people. Now, sometimes this can be something like this also, है ना? So this is the PA over here. So you can also write P2 is equal to PA plus rho g times of capital H, if this is capital H distance. Okay, people. Is this clear? Now this H has to be the perpendicular distance. This H has to be the perpendicular distance. If I have a pipe something like this, this is the H that I'm going to take. This is the H that I'm going to take. Okay, people. If I have a pipe something like this, this is the H that I'm going to take. This is the vertical height that I'm going to take. Okay. Okay, people. Yes or no? Let's move ahead. Pressure in accelerating fluids. Pressure in accelerating fluids. This is something which you have to understand. Okay, people. Now, before that, over here, if you all notice, this is called as the absolute pressure. This is called as the absolute pressure. Okay. This is called as the absolute pressure, and the difference, that is P2 minus PA is equal to rho GH, is called as the gauge pressure. Okay. Now let's talk about pressure in accelerating fluids. Okay, people. Let's talk about this. My God. Okay. So what is pressure in accelerating fluids, people? This is very easy. This is very easy to understand. Very easy to understand. Okay. Just a second, guys. Okay. So see this. If this is the fluid that I'm talking, if this is the fluid that I'm talking, and if it's accelerating upwards, okay, and this is the cylinder or the imaginary cylinder, energy. So here it is PA, here it is P1, and the length is H. Okay, so obviously the pressure can be written as P1 is equal to PA plus rho into H into G effective. into G effective. Now what is the G effective? Obviously this whole thing is accelerating upwards, so there will be a pseudo force Ma over here, Ma over here, and Mg over here, है ना जी? So the G effective can be written as P1 is equal to Pa rho H into G plus A. Yes, this is one formula that you can get over here. Now if it is accelerating downwards, obviously pseudo force will be upwards, in that case the G effective is going to be, now this is for upwards, है ना? Sorry, this is for accelerating upwards. For downwards it is basically P1 is equal to Pa plus rho into H G minus A if it is accelerating downwards. Yes or no? Yes or no? Okay. Okay. Now if it is accelerating sideways, okay, if it is accelerating sideways, what are we gonna get? So people, when it is accelerating sideways, for example, if it is accelerating in this direction, you will get the fluid to be something like this. In this position, if it's actually like this, the position will be something like this. Why are we getting something like that? I'll explain. If this is the imaginary cylinder that we are talking about, if this is length L, and this is height H, okay, what is happening is that obviously it is very much obvious that the mg component will be over here, the pseudo force component will be over here, Ma, the resultant will be over here. Now this Fr resultant has to be perpendicular to the surface, that is the reason you are getting this shape. Are you able to understand this? This has to be perpendicular, that is the reason you are getting this shape. Yes or no? Yes or no? Okay, over here you are able to understand, that pressure over here is P2 and pressure over here is P1. So the difference in pressure, now over here this P2 is greater than P1, okay, so over here the formula that you are getting is P2 minus P1 is equal to rho LA. This is the formula that you get. Okay people, yes or no? Okay, now let's talk about barometer. In barometer, what is barometer? Barometer is basically a device used to calculate the atmospheric pressure, है ना जी? So it's simple, it's very simple on how they calculate it, Here the pressure is 0, here the pressure is PB. So so can I basically say PB is equal to PA plus rho GH. As PA is 0, we get the value of PB is equal to rho GH, है ना? Okay, so and this PC is equal to PA, PC is equal to PA, है ना? Now as both of them are the same horizontal level, I can also say that PC is equal to PB is equal to PA is equal to rho GH. Just substitute the values and you'll get the value of PA over here. Okay people, chalo, let's move ahead. Now let's talk about Pascal's law. What is Pascal's law, people? Whenever an external pressure is applied on any part of the fluid contained in the vessel, it is transmitted undiminished. That means if I apply F force over here and area of cross section A, the pressure is delta P. Same pressure delta P is gonna get transmitted equally in all directions. That is basically Pascal's law. Okay. Okay. Yes or no? Yes or no? Okay. Let's talk about hydraulic lift. What happens in a hydraulic lift? I am applying force over here. So delta P pressure is getting transmitted equally. What is the pressure over here? The pressure over here is F1 divided by A1, and the pressure over here will be equal to F2 by A2. So the value that we get, F2 over here, F2 comes out to be F1 by A1, F1, and this becomes A2 by A1. Now obviously the value of A2 value of A2 is much more greater than A1. So this becomes a very big value. This becomes a very big value. So F2 comes out to be a big force. So even if you apply a very small force over here, ultimately you are getting a very big force so that you can lift this object. Okay. Okay. Let's talk about Archimedes principle. Let's talk about Archimedes principle. Okay. Let's talk about Archimedes principle. Okay. Chalo, let's talk about Archimedes principle. Now before that, let's talk about buoyancy. Buoyancy diya nahi kya? Okay, I'll just explain what is buoyancy over here. Buoyancy over here. So that U is equal to Vf rho F into G. Okay, this is basically buoyancy over here. है ना जी? So this Vf is basically volume. This is basically volume of fluid displaced. This is basically volume of fluid displaced. है ना जी? So obviously, so when you have anything inside the fluid, this fluid has to displace some volume. How much volume it would displace? It would displace the same amount of volume jitna it is inside the fluid. Okay, are you able to understand? So if the volume is 10 over here, if this is 10, है ना, if this is 10 meter cube, it has some volume. So if we insert it fully inside, then the volume displaced would be 10 meter cube. But if it was only partially or half inside, then the volume displaced would be 5. Are you able to understand this? Are you all able to understand this? Yes. So this is volume of fluid displaced, rho of fluid, and G over here. Okay. And this is equal to volume of body immersed. Volume of body immersed. Cool. Now let's talk about Archimedes principle. Let's talk about Archimedes principle. So when a body is immersed wholly or partially in a fluid, it is lifted up by a force equal to the weight of the fluid displaced by the body. Yes, this is the Archimedes principle. So again, Archimedes principle, what does it state? Archimedes principle, this is Vf rho F into G. Now what is volume into density? That is mass. So U is basically mass of the fluid displaced into G. So that is equal to the upthrust that we are getting. That is basically equal to the upthrust that we are getting. Okay, G. So this is the upthrust that we are getting, and this is mg over here. And due to this, we form the apparent weight of the body. Okay, G. We get the apparent weight of the body. We get the apparent weight. People, just a second, I'll just come in a minute. Okay, I'll just come in a minute. Yeah, I'm so sorry, people. I'm so sorry. I'm back. Hello, 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 hello. Are you all able to hear me? I'm so sorry. Are you all able to hear me? Yes. Okay. Okay. So what is the apparent weight? Apparent weight is basically like this is the fluid, है this is the container, and this is basically the fluid, and inside this obviously there is some object which is kept, and this object has an mg component, है so the original weight is basically W is equal to mg, but as it is inside the fluid, it also has an apparent upthrust over here. Okay, it has an upthrust over here. Okay, so the apparent weight, it comes out to be W, sorry, it comes out to be mg minus the upthrust, and this is basically the apparent weight. Okay, this is basically the apparent weight over here. Okay, people. Now, just a few formulas that you should keep in mind. Over here is that W apparent. Okay, W apparent weight is basically equal to W original. Okay, that this is W original, and this is 1 minus rho of F divided by rho of S. Okay, people, this is one formula that you have to keep in mind, where rho of F is the density of the fluid. This is for the fluid. Okay, and this is for the solid itself. This is of the solid or the body itself. Okay, this is one formula that you can keep in mind. Okay, people, so that is one formula. Now let's talk about law of flotation. Okay, let's talk about law of flotation. So obviously, if this density, the density of the body is rho s, if this is rho f, if the density of solid is less than density of the fluid, है ना, so this will float. Are you all able to understand this? है ना? If the density of the solid is greater than density of the fluid, then this will sink. If the rho of S is equal to rho of F, if both of them are equal, then it will perform limiting flotation. It will perform limiting flotation. What do I mean by limiting flotation? Limiting flotation is basically, it will be something like this. This is called as limiting flotation. This is limiting flotation. Okay, people, are you all able to understand this? Yes or no? Yes. Let's move ahead. Now let's talk about steady flow, streamline flow. Okay, let's talk about steady flow and streamline flow. So at different points, velocities of the fluid particles can be different. So basically, here it has velocity v1, velocity v2, v3, v4. But each particle, when it crosses these velocities, it will have the same velocity. That means if the velocity over here is v1, every particle that comes over here will have velocity v1. Every particle that comes over here will have velocity v2. Every particle that comes over here will have velocity v3. That is something which we are going to have. Okay, but velocity at a given point is constant with time. That is exactly what I'm saying. Okay, the flow of the liquid is said to be steady if at any given point the velocity of each passing fluid particle remains constant in time. That is exactly what I've said. This does not mean that the velocity at different points is same. The velocity of a particular particle may change as it moves from one point to another. So exactly that's what I'm saying. So at one particular point, it will have the same velocity. Each particle which passes through that point will have the same velocity, but at different velocities at different point. That is exactly what my streamline. Okay, that is, at some other point the particle may have different velocity, but every other particle which passes through the same point behaves exactly as the previous particle that has just passed through that point. Okay. Next, so some streamlines for fluid flow. Yes, this is streamline, and this is an example of a turbulent flow. Okay, people. Okay, what is equation of continuity? Equation of continuity, it is based upon conservation of mass. Okay, it is based upon conservation of mass. That means the total mass entering has to leave the total mass outside. And the total mass entering is the total mass leaving, and the formula that you get is A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2. Hello. जस्ट अ सेकंड, मैं क्लास में हूँ रे, क्लास में हूँ. Okay, a1 v1 is equal to a2 v2, and which is equal to a into b, which is equal to a constant. Okay, so from here we are getting that area is inversely proportional to the velocity. So lesser the velocity, more will, so lesser the area, more will be the velocity. That is what we are getting over here. That is what we are getting over here. Clear, people? Clear? Is this clear? Is this clear? Okay, cool. Bernoulli's principle. Again, Bernoulli's principle is based upon conservation of energy. It is based upon conservation of energy. Conservation of energy. है ना जी? What does Bernoulli principle says? It is basically P plus half rho V square plus rho GH is equal to a constant. Is equal to a constant. है ना? Now if I divide it by rho G, I get P divided by rho G. है ना? This becomes V square by 2G, and this becomes H is equal to some constant. This is called as the pressure head. This is called as the velocity head. Okay, people? Yes. Oh my god. Okay, people, are you able to understand this? Okay, so this is the pressure head, velocity head, and the potential head. Okay, that is also equal to a constant. Okay, people, that is something that you have to keep in mind. And okay, now some formulas regarding the venturimeter, because this is something that you have to do. Okay, this is one of the applications. So there are some formulas over here which you have to keep in mind. The formula is over here is, the first formula is a1 v1 is equal to a2 v2. That is the first formula that you have to keep in mind. Okay, the second formula that you have to keep in mind is v2 square is equal to v1 square plus 2 into gh. Okay, this is the second formula that you have to keep in mind. And the third formula, that is the rate of flow, q is equal to, it comes out to be a1 a2, okay, a1 a2 square root of 2gh, and this is a1 square minus a2 square. Okay, this is the three formulas that you have to keep in mind. है ना? So the v1 velocity, this is v2 velocity, and this is the height difference h. Okay, people. Speed of efflux and Torseli's law. Okay, so let's understand this. So the speed of efflux is basically the velocity from which it comes out. This is v is equal to square root of 2gh. Yes, v is equal to square root of 2gh. That is basically speed of efflux, or Torseli's law over here. Okay, and that is Torseli's theorem also, है ना? And the rate of flow can also be written as area into velocity. Area is basically a over there, and the velocity is 2gh. So the rate of flow comes out to be a into 2 root square root of 2gh. Okay, people, is this clear? Now last formulas, no, this is run. Yeah, the last formula is basically the range. Okay, the range of the projectile, basically this one, है ना? The range of the projectile. So this range, what is this range formula? Okay, I'll just write it over here. The range formula, it comes out to be square root of 4 into h minus h. This is the formula, where this is the h and this is the total height h. This is h minus h for you. Okay, people, clear? Is this clear? Now when will we get r as maximum? We'll get r maximum at h is equal to h by 2, and the r maximum value is going to be equal to h. Okay, so now let's talk about viscous force. Okay, now let's talk about viscous force. Now viscosity is basically the internal friction. Internal friction due to the layers of the fluid. So whenever there is relative motion among the layers of the fluid, a viscous force is developed, and that is exactly what is viscosity, है ना? So viscosity is an internal friction in a fluid motion. It occurs due to the relative motion between the layers of the fluid. The internal frictional force in fluids is called viscous force. Viscous force, it depends upon the relative motion between the layers, velocity gradient, area of contact between the two layers, and the type of fluid. I hope so this is very much clear. Now let us talk about Stokes law. Stokes law is only for spherical bodies, है ना? It is only for spherical bodies. It is only for spherical bodies, and the force that you get is basically equal to 6 pi r n v. Okay people, okay people, is this clear? Where v is the velocity, n is the coefficient of viscosity, r is the radius, and that is the force is the viscous force. Okay, and this is the viscous force that I'm talking about. Viscous force that I'm talking about. And there is also terminal velocity. The terminal velocity is the maximum velocity by which a body can drop in a fluid. Okay, that formula comes out to be 2 by 9. Okay, 2 by 9 r square, and this is eta over here, and this is sigma rho minus sigma into g. This is the formula of terminal velocity. Okay people, so that's it people. Yeah, we have completed everything. Now before I go, I want you all to say that do you need any numerical practice of any chapter that you want? Then we can do it right now. Tell me, we have some time, we'll do some numerical chapters, or is this enough? Tell me. Okay, tell me people. And also like the session people, like the session. Fluids, sir, you want for fluids? Yes sir, some questions from past years. Enough I guess sir, please. No, it's okay Dr. Purple, it's okay. Need numericals. Which chapter people? Which chapter? Which chapter? Which chapter? Which chapter? Which chapter? No problems, Tina. Which chapter people? Come on, tell me. Fluid chapters. Okay, chalo, fluid. Let's do fluids then. Let's do fluids. Chalo, let's do fluids. Okay, we're gonna do fluids. Okay, fluids. Chalo, let's do fluids. First question. What is the first question, people? What is the first question? The first question says two thigh bones, each of cross-sectional area. This much support the upper part of the human body of mass 40 kg. Estimate the total pressure sustained by both the femurs, and that is your question, people. Okay, that is your question. Let's solve it. Again, a very easy question. A very easy question. Just a second, people. Okay, chalo, let's solve this. So we know that the pressure is basically force divided by area. Yes, pressure is basically force divided by area, hai na ji? So the force is basically mg, because that is the body, and divided by area. That is the divided by area. What is the mg? Mg is basically 40. So this becomes 40 into 10, the whole divided by area. Area is how much? 10 centimeter square. So that is basically 10 into 10 ki power minus 4. I'm converting into meter square. Okay people, so this 10 gets cancelled, and what we are getting over here is 40 into 10 ki power 4. 40 into 10 k power 4, but again we have to divide it because estimate the total pressure sustained by both the femurs. Acha, they have asked us to calculate about both the femurs. Okay, about both the femurs they have asked us to calculate. Okay, people. So I just divide this by 2. I just divide this by 2. So this becomes 220. So this becomes 2 into 10k 5. 2 into 10k power 5, and that is your answer, option B. Okay, cool. Let's move ahead. Let's move ahead. Okay, let's solve this. Let's solve this. What is it? Two liquids of densities 2 rho and rho having their volumes in the ratio 3:2 are mixed together. Okay, they're mixed together. I need to find out the density of the mixture over here. Okay, people. So the density of the mixture is basically mass of the total mixture, mass divided by the volume. Yes, this is basically. So two liquids having densities 2 rho having their volumes in the ratio 3:2. So can I write the mass as density into volume? Density into volume. So this becomes 2 rho into 3x into some 3x plus rho into 2x. This is basically the mass. This is basically the mass, and the volume is basically 3x plus 2x. So this comes out to be 6 rho x plus 2 rho x divided by 5x. This comes out to be 8 rho x divided by 5x. X and x gets cancelled. So 8 rho by 5 is your correct answer. Option C. Very good. Very good. Next question. This is the question that you have to do. Acha. So we have to calculate the pressure. Okay. We have to calculate the pressure. So if this is 1, this is 1 cos theta. This is 1 cos theta, and this comes out to be 1 sin theta. 1 sin 30. I've just broken it. So P naught, so P can be written as P naught plus rho GH plus rho GH. So P is equal to P naught plus rho GH. H is basically sin 30, 1 sin 30, that is half. So this becomes H by 2. This becomes H by 2 or 1 by 2, sorry, 1 by 2, that is much more answer. 1 by 2, 1 by 2, 1 by 2, that is your answer. Yes, option C. Option C, option C. Okay, I have already told you, Tina, we have to take the vertical height. We have to take the vertical height. Okay, people, we have to take the vertical height. Next, correct relationship between gauge pressure, atmospheric pressure, and absolute pressure. So gauge pressure is equal to atmospheric minus absolute. Okay, now gauge pressure is atmospheric plus absolute. Nah, this is wrong. This is wrong. Absolute pressure is atmospheric pressure plus gauge pressure. Okay, so what do we know? We know that P1 is equal to PA plus rho GH. This is basically the absolute one. This is absolute pressure, hai na ji? So absolute pressure is equal to atmospheric pressure plus gauge pressure. Yes, D is right. Yes, D is right. That is option C. Option C is right, I guess. Yes, option C is right. Option C is right. Absolute pressure is equal to atmospheric pressure plus gauge pressure. Obviously, this is the gauge pressure. This is the gauge pressure. Yes, cool. Next. At a depth of 500 meter under an ocean, what is the absolute pressure given the density of the water is this much? Sir, that pulley one, can you do that please for 2 pi? Okay, ठीक है. Okay, Janvi, I will. Okay, I will do it. Okay, so at a depth of 500 meter under an ocean, okay, chalega, what is the absolute pressure that we have to calculate? That is the absolute pressure we have to calculate over here. So again, absolute pressure is again P is equal to P naught plus rho GH. This is what we have to calculate, hai na ji? Now, what is the value of P naught over here? What is the value of P naught? Acha, P naught comes out to be 1 atm, hai na? 1 atm. This comes out to be 1 atm, and rho is basically how much? So this is this is rho, no? So this is density of water is already given, that is 1.03 into 10 ki power 3. So this becomes 1.03 into 10 ki power 3. Value of G is 10, and H is basically 500 meters. 500 meters, right? So this is 500 for you all. You can all solve and you can get the answer. Okay, you can all solve and you can all get your answer from here. Okay. So okay, this one. The three vessels ABC of different shapes contain a water up to the same in the figure PA, PB and PC. Be the pressure exerted by the water at the bottom of the vessels. Now obviously all of the vertical height is same. All of the vertical height is same over here. All of vertical height is same over here. So the pressure is going to be same. Pressure is going to be same. So D option is your correct answer. D option is your correct answer. Okay. Now let's move on to some good questions. Let's move on to some good questions. Okay. Okay. Now let's do the YouTube problem. Let's do a YouTube problem. In a YouTube experiment, a column AB of water is balanced by a column CD of paraffin. The relative density of paraffin is what they have asked. So over in this type of questions, you have to draw a line. You have to draw a line in the boundary of the two liquids. This line I'm going to talk about. Now obviously this pressure P1 over here will be equal to the pressure P2. That's it. That's what we have to do over here. So I can basically say P1 is equal to P2. Now what can I write about P1? Can I write it is P atmosphere plus rho G H1. You'll be like, yes sir. Then for H2 over here, this will be P2 is equal to, P2 will be equal to some atmospheric pressure plus rho G H2 plus rho G H2. This gets cancelled. Rho G gets cancelled. No, did I do something mistake? Did I do any mistake, people? Did I do any mistake, people? Yes. Just a second. This is P2, H2. This is H2, rho W. Oh, array. This is different liquids, right? This is different liquids. What did I do? So this is basically PA plus rho of paraffin G into H1 is equal to PA plus rho of water G into H2. So PA gets cancelled over here. Okay. So what does it remain? Rho P G H1 is equal to rho W G of H2. है ना? G gets cancelled. So what does it remain? The only thing that remains over here is H1 by H2 is equal to rho of water divided by rho of paraffin. But relative density, yes, but relative density is rho of paraffin divided by rho of water. So rho of paraffin divided by rho of water comes out to be H2 by H1 and that is our answer. H2 by H1 and that is our answer. Very good. Very good. ठीक है. Let's solve this. See, a closed rectangular tank is completely filled with water and is accelerated horizontally with an acceleration A towards right. Pressure is maximum and minimum at. Now, accelerating something like this, it is accelerating over here. So obviously, this side is going to have maximum pressure. This side is going to have maximum pressure. And over here, if we compare A and B is at a larger depth. So obviously B is going to have a larger pressure. So because see, as it is accelerating this side is going to have a larger pressure. And also it is at a height, also at a depth also. So PB is going to be maximum. PB is going to be max. Now when it comes to minimum, obviously A or D has to be the minimum one, but as it is accelerating this side, D has to be at the minimum pressure. So D is the minimum. So PD is at minimum. So B and D is your answer. Option A. Cool. Okay, this one. See this. A non-viscous liquid is flowing through a frictionless duct. Cross section varying as shown in the figure. Which one of the following graph represent the variation of pressure along the axis of the tube? So see, the area is large over here. If the area is large, the velocity would be less. The area is less, the velocity is large. Now as the velocity is less over here, the pressure would be maximum, and over here the pressure would be minimum. That is the graph that we are going to get. That is the graph that you are going to get. Pressure maximum, then pressure minimum. So this is wrong. This is wrong. Over here, pressure is minimum first, then maximum. Then this is wrong. This is your right answer. Pressure is maximum and then minimum. Okay. Okay, people. Now coming back to Janvi's doubt. Okay, coming back to Janvi's doubt. Okay. I think this was an SHM, right? Okay, see this one. See this one. Okay. So see over here how to calculate this. How to calculate this. It's very simple. It's very simple. See, first of all, we have to calculate K dash. We have to calculate K dash. What is K dash over here? Tension in the mass. What is the tension in the mass? It is T. Okay, T divided by tension in the spring. What is this tension in the spring? It is 2T. So this is 2T the whole square. And this is multiplied by K, because the K is the spring constant. Okay. Okay. So this becomes K dash is equal to T and T gets cancelled. 1 by 2 is 1 by 4. So this becomes K by 4. So what is going to be the time period? Time period is going to be 2 pi square root of m divided by k, and this becomes 4. This is your answer. This is your answer. Okay. Okay, people. Yes or no? Yes or no? Okay. Now I just I actually forgot, we need to complete one more topic. We need to complete one more topic, and that topic is basically, it's a very small topic. We'll just complete it fast. That is surface tension. That is surface tension. Okay, people. Last one topic. Okay. What is surface tension? Obviously, it is the property of the liquid. It is property of the liquid at the liquid surface. It is a surface phenomenon. Okay. It is not a bulk phenomenon. It is a surface phenomenon, because both the bulk and the surface of the liquid behave very differently. Okay, people. Now, so property of the liquid by which it tries to attain minimum surface area, is called as surface tension. Are you all able to understand this? Now, you know why a small drop of liquid is spherical in shape? Because the spherical shape has a maximum surface area. That is the reason we see a small drop of liquid is spherical in shape. Okay. Now, what is surface tension? Surface tension is basically the force acting per unit length perpendicular to the imaginary line. So if this is the imaginary line, and if this is the force which is acting, that is basically the surface tension that we are defining over here. Okay. So T is equal to F by L and F is equal to TL. Okay. Now in liquid film, always you have to consider, film always has two layers. It always has two layers. This you have to find out. Okay. This you have to keep in mind. Now over here, force is acting over here, and this is the length. So the surface tension is not basically T into L. The F is not equal to T into L. It is F is equal to T into L into 2, because film has two layers over here. For each layer you have to calculate the force. So F is equal to T into L multiplied by 2. Are you able to understand this? Okay. Now let's understand. Okay. Now let's understand. Let's understand over here. Okay. Important point. Soap decreases the surface tension of water, and that is how we are able to wash the clothes more efficiently. Surface tension decreases with increase in temperature and becomes zero at critical temperature. Now what is critical temperature? Critical temperature is that highest temperature at which substances can coexist as liquid. So basically it can coexist as both liquid and solid. So that is basically highest temperature. So basically highest temperature at which substance can coexist as a liquid is called as critical temperature. So surface tension decreases with increase in temperature and becomes zero at critical temperature. Some of the facts that you should know over here. Okay, surface tension is a scalar quantity, and surface tension depends upon the nature of the liquid and its intermolecular forces. Okay, and it depends upon the impurities added to the liquid as well. Okay, now let's compare about the surface energy. Now we all know molecules on the liquid surface have more energy. Why? Because they are exposed to the air as well, and they are also exposed to the water molecules as well. That is the reason we say molecules on the liquid surface have some extra energy in comparison to the molecules on the interior. Okay, people, and a liquid thus tends to have the least surface to have minimum energy and most stability. Now what exactly is happening is I'll tell you from this slide. You'll be able to understand. That is, see, in the interior it is having zero energy. In the surface it has x amount of energy, and it for to leave it needs 2x amount of energy. Okay, people, so the amount of heat needed to turn the liquid into vapor without rise in temperature of the liquid is actually heat of vaporization. So this over here, the amount of heat energy required for taking out the interior water molecule to the exterior is 2x over here. That is what we are able to calculate over here. Okay, so number of surfaces over here. Film always has two surfaces. This is truth. This you can't change. Bubble, it has one surface, or bubble or drop always has one surface except for soap. Whenever you get soap, you have two surfaces. So film always two surface, soap always has two surface, but the rest, that is bubble or drop, always has one surface. Okay, people, it always has one surface. Now excess pressure in the liquid drop, again it's a very easy topic. Obviously this is P inside, this is P atmospheric pressure, and also the surface tension as well. So excess pressure inside the liquid drop is going to be equal to 2T by R, or P initial is equal to P naught plus 2T by R. This is one formula that you can keep in mind. Okay, people. Yeah, and this is for the bubble. The excess pressure is going to be 4T by R. The excess pressure is going to be 4T by R. P initial minus P naught is equal to 4T by R. Okay, people. And one more thing, that always the concave side is going to have the excess pressure. Always the concave side is always going to have the excess pressure over here. Okay, people. Yes or no? Okay. Yes, and this is a very important topic, the height of capillary rise. This is a very important formula, that H is equal to 2T cos theta divided by R rho g. Okay, divided by R rho g, where T is the surface tension, theta is the contact angle, R is basically a very important thing in order for you all to understand. एक सेकेंड, मैंने दिया नहीं क्या? Just a second. Okay, so over here, over this R is basically the capillary radius that we're talking about. R is the capillary radius, rho is the density of the fluid, and g is the acceleration due to gravity. If you get Hs positive, then it is rising. If you take Hs negative, then it is falling down. So that is exactly what we are getting. I've specified all the points over here. Okay, so that's it, people. We have completed everything. Okay, we have completed everything. Okay, people, so that's it from my side, people. It was amazing teaching you all. Okay, and one more thing, people, please don't leave, please don't leave. It was amazing teaching you all. Yes. So okay, it was amazing teaching you all. So please people, you can give the benchmark test. Okay, so tomorrow is the last Sunday that you are having benchmark test for NEET UG. You can get the literally NEET day experience over here. Yes, you can get the notes on Telegram. I'll ask Yavar sir to send this. Crafted by top educators. You can know your rank. You can predict your dream college. April 27 2 p.m. is the date. Okay people, April 27 2 p.m. is the date. Or those who want to enroll, they can just click on the link on the description and they can enroll over here. Okay people. अरे यार next हो जा. Next in your. Okay, next, your winning streak starts over here. Obviously you can basically tell your juniors that if they want to teach, they learn along with me, they can use the code John21. Okay, John21 is the code that they can use, and they can avail 60% off on all subscriptions. Okay, and all subscriptions. Okay people, and what is happening? Okay, I'm not able to exit. I'm not able to exit. Some issue happening. Just a second. Okay, so again the benchmark test for NEET UG NEET UG. Okay, and the top 50 will get an Amazon voucher. First one a laptop, second prize a smartwatch, third an earphone over here. And you can again please enroll to this. And yeah, and this is the new TG subscription pricing. Everything is given in your app and website also. And this is the iconic and the VIP features that we are giving. You all know about this. We have moved into smart boards. Everything is on smart board right now. And this is the Unacademy Notes 4.0 plus iconic VIP features. Okay, and you can join the NCRT Crux test series for just 799. Okay people, and this is for class 11th, class 11th, 12th droppers, and this is for droppers VIP NEET UG batch for 49,999. Okay people, that's it from my side people. It was amazing teaching y'all. I hope so you all understood everything. Thank you so much people, thank you so much. So this is Jonathan Matthew signing off from Unacademy NEET English. We'll meet once again in the near future. Thank you so much. Bye bye. Thank you all. Love you all. Bye bye. Okay, take care. And please do write your comments in the comment section. I'll personally read all of them. Okay people, so you can write the comments on how did you like it. Okay, bye bye.